link. So virtual world. We will have 6 very nice talks of different kinds. First will be the talks related to retrieval of some essential traits. We will have talks about emulators, emulating atmosphere, radiative transfer as well, some other things. One talk on a leaf level, which I really like to see, because we don't talk much about leaf level modeling, and not enough in my opinion. And then we have 2 talks related to carbon modeling. So we will start with the first speaker, Jochem Verhelst from University of Valencia, and he will talk about the retrieval of essential traits for Sentinel L2, L3, L4 product support. Floor is yours, Jochem.
Thanks, Phoenix, and thanks everyone for being here. And I also want to have a special thank to my collaborators, especially Pablo, Emma, and David. They did most of the work. I will just present it. And maybe it's good, let's have a look to our famous illustration of FLEX. We all know we've seen this for so long, but there's also this other mission there in the back, and that has been largely forgotten so far, the Sentinel-3 mission. And this time I want to talk a bit more about it. So I twisted a bit that illustration, put Sentinel-3 in front, because that mission will greatly support FLEX with the retrieval of essential vegetation traits, amongst other temperature also. And that Sentinel-3 mission has been around already since 2015. The data is already available in the cloud, in Google Earth Engine, top of atmosphere radiance since 2016, but also on European Copernicus data space ecosystem, Synergy data since 2020. So the data is already there, we can already exploit it. So here today I want to present 3 versions of models that we have been developing for Sentinel-3, 3 generations. And the models that have been developed came a bit from previous FLEX projects, where the focus has been always on leaf chlorophyll content, leaf area index, FLPAR, and fractional vegetation cover. But what all these models have in common is that they are developed with this Gaussian process regression. It's a machine learning algorithm I like a lot, because it gives very good performances with relatively few training data. But most of all, it provides also uncertainty. So you get model-based uncertainty for free with that model. But also, at the end, when the model is being trained, it's just a matrix calculation, meaning that it can be very easily being implemented in processing chains or in cloud computing. I want to present 3 generations of models, 2 hybrid models, and 1 more empirical based, 1 based on top of atmosphere radiance, so there's no need for atmospheric correction, and 2 based on the newer Synergy Sentinel-3 data. These 2 are implemented into OpenAO, while the first one into Google Earth Engine. So let's start with the first one. And here these models, they were inherited from past FLEX studies. At that time, we were just using SCOPE and using surface reflectance. We wanted to implement that into the cloud, but it appears that Sentinel-3 in Google Earth Engine only provides top of atmosphere radiance data. So we had to find a way how to bypass that in order to make them running into Google Earth. To do so, we retrained the models, but by coupling SCOPE together with an atmosphere model 6S. In this way, we have top of atmosphere radiance. We trained, we optimized the models. Eventually, we put it into the cloud. And once it's in the cloud, you can do time series. You can easily compare it against other data sets. You can easily do validation, and you can make great maps. Maps that I can show here, for instance, our 4 products over Europe, a monthly composite. Now, leaf area index, fractional vegetation cover, and FLPAR are products that are also provided by Copernicus. So maybe the most interesting product is leaf chlorophyll content. We can run it anywhere, anytime in the world. It's new, but because it's not a Copernicus product, the disadvantage is that there's much fewer validation data of chlorophyll data available, making that it's a bit harder to tune or to validate. But the nice part of these models is that they also provide these uncertainty. So you get it for free. You can quantify it as absolute uncertainty or as relative uncertainty. And with that information, you get information about the robustness of the models. It tells us where the model is doing great, where less. Because it's based on SCOPE, a homogeneous model. It was suffering a little bit on heterogeneous areas, but we can see that. And eventually you can go to those places, take additional data, retrain your model, improve for those areas. So we also did some evaluation because it's in Google Earth. It's relatively easy to do temporal profiles and compare it against MODIS data, for instance. We can compare it against Copernicus data. And we at that time also some validation from field campaigns that led to reasonable good results. We were okay with this model, so we felt we can release it to the community. And to do so, we prepared a package called PyAO-GPR. It's a Python-based package that can run both in Google Earth Engine or on OpenAO. But all you have to do is you have to define your spatial window, your temporal window, and you choose your model, and it runs over the area that you selected. So you can generate this kind of maps all over the world, plus together with uncertainty. Copernicus doesn't provide that. We can see that LAI and FFR provide rather good uncertainties, leave chlorophyll content as it's a bit more challenging product. The uncertainties are a bit higher, but still it's good. And not only that, we also recently developed a visualization tool by Emma. She's over there, she can demonstrate to you. And it's very nice, so you can just, on a GUI, you just have to say the temporal window you are interested in. You can draw your area you want to map, and the maps are provided just within a few seconds. So chlorophyll, anywhere, anytime in the world. So maybe this, let's have a summarize of this first generation of models that we have provided. They are good, they provide consistent all over the world. Just the uncertainties tells us about the robustness and also about the limitations, especially on the limitations of the SCOPE model over heterogeneous areas is still challenging. Another point is that with Gaussian processes to run it into the cloud, we cannot have too many training data, making also that we're limited on the choice of what we put into the training. Now, this brings me to the next generation of models. Meanwhile, the Synergy product was released. Synergy product is a product from Sentinel-3 surface reflectance, but coming from both ALCHI and SLTSR bands. It's normalized, BLDF corrected, harmonized, but with the additional advantage that we have now not just ALCHI data bands, but also SLTSR bands that we can use for training. So it should lead to improved models, right? Since that we have more bands available. So this time I want to also introduce another novelty. We do exactly the same workflow, but in the meantime, also Copernicus provided the so-called GBOV dataset, which is a harmonized ground dataset from all over the world. Data that has been, that is normalized, harmonized, but also 300 meter upscaled. It's perfect for validation. The Copernicus products use that, but it's also provided to the community, meaning that we can also make use of this data set for our validation. And this time I also want to show you about the model training, because I talked about this ALCHI and SLTSR. With Gaussian processes, we also can see what are the relevant bands in the training of the model. And it's very nice to see that both bands of ALCHI as well as SLTSR are the most useful for training these models for FFR and fractional vegetation cover in this case. Because of the GBOV, we can also do rigorous validation. On one hand, we see some temporal profiles per plant functional types of our product, the Copernicus product, and the GBOV ground observations. We see consistency. And on the other hand, we also can validate against this GBOV data. And here we validated not just our product, but also the Copernicus product to know if we are doing a good job, if we are doing better or worse. In general, we are very consistent with the Copernicus product. For some plant functional types, Copernicus may be slightly more accurate. For other plant functional types, our products are more accurate. Altogether, we reach a higher accuracy than the Copernicus products. So in summary, also these two models have been implemented into this PyAO-GPR package. It's freely available to the community. You can mapping anywhere in the world, plus these uncertainties. And these uncertainties still we see they are generally good, but there are also still these regions with high uncertainty due to more heterogeneous surfaces, especially because of bare soil and so on. So we felt like we should still come up with a third generation of models to improve that. This time, we were inspired by the Sentinel-2 community. They already tried by applying the GBOV data for training. So we moved away from the SCOPE model, which was our main limiting factor. And now instead, we use real data, empirical data from the GBOV dataset, which is ideal because it has observations. But this you can then associate with the overpassing images from synergy, meaning that also your reflectance data is exactly the same as your image, leading you to way better maps. Another novelty that we also introduced is so far we talk about uncertainty as model-based uncertainty, epistemic uncertainty. But here in this room for the last few days, when people talk about uncertainty, they talk about propagated uncertainty, aleatoric uncertainty. Ideally, you need to have both sources of uncertainty together, coming from the model, but also from the noises from the radiometric data that is being propagated. How we can get both types of uncertainty, we did a pragmatic approach with the assumption that taking a time windows of 10 days, within these 10 days we have multiple overpasses, meaning that we have the noises, so we have the variance of this region, assuming that our land cover stays stationary. So in this way, we get our mean reflectance, our standard deviation, and that data you can then propagate into Monte Carlo, run multiple GPR models, and eventually you get your mean estimate plus your aleatoric uncertainty. A few words about the data. It's very well distributed for all these three variables. And also, we made sure that our training data is nicely distributed along the plant functional types, but also that our validation data is from other sites as well, other years, to make sure that it's really independent. You see here a map of where the GBOV data came from. Also, you see this land cover map with these three regions where we did this aleatoric uncertainty. Since Monte Carlo takes a lot of time, you cannot immediately process entire Europe on your computer. We chose 3 regions across Europe. And also the bottom right is this map where that sees a number of acquisitions within this 10 days time window. That is the 10 days that we chose for collecting the variability for propagating through Monte Carlo. Validation is very good also on these, for these models, both for as a whole as per plant functional type, meaning that we can nicely map those models for, again, this is for LAI. And compared to the models before, we see that our uncertainties are way lower. And again, because moving away from SCOPE towards GBOV data, we are much more realistic in training models, leading to more consistent models for. Also, the comparison against Copernicus is very good this time. We have that for FAPA also, as well for fractional vegetation cover. Finally, so far we're showing epistemic uncertainty, which gives us an idea of where surfaces are more heterogeneous, gets higher uncertainty. But as well now we have also this propagated uncertainty, generally lower than epistemic uncertainty. It follows more the patterns of the estimate. But what really matters is that then afterwards you can calculate the total uncertainty. And that's the uncertainty we are interested in. You can express it as total or relative, and same for the other variables. So finally, you can have this data distribution. We see the estimates for these 3 regions, the aleatoric uncertainty, which is generally low, epistemic uncertainty, which is a bit higher, and what really matters is the total uncertainty. If interested in knowing about uncertainty, how to quantify, what is good practices, we just published a paper about the theoretical framework. So in conclusion, we present 3 generations of models, 2 hybrids, 1 empirical, 1 without the need for atmospheric correction running in Google Earth Engine, 2 running in the European Open AO. All of them provide epistemic uncertainty. In the future, we also hope to add aleatoric uncertainty. They are publicly available, all of them within the PyAO GPR package. And the idea is that these models are for the community to support the FLEX mission. With this, I would like to thank you.
Thank you very much, Joachim. I would first give a chance to the audience to ask questions. We have enough time.
Hi, hello. So I'm not very familiar with all these processes, but I was very surprised to see the map of uncertainties with very low uncertainties for the tropics. Can you explain why? I thought that it's one of the regions when you have the most uncertainties.
I guess you refer to the
global map of LAI.
This one, right?
Yes.
Right, so I would say in general the uncertainties are very low, especially if we see it for fractional vegetation cover and for leaf area index. We see some higher uncertainties in the transition zones, the savannas. That I would say because of the training model is not so well prepared for transition zones where there is more influence of bare soil. At the end, models were trained with simulated data of a vegetation model. We also added bare soil into the training, but probably not enough to cover all those kind of regions. So about the tropics, I would say since this is a vegetated surface overall, I think our models do reasonably well since we are especially prepared for vegetated surfaces.
Okay.
Thank you. Any other question? Over there.
Another mission like biomass, for example, in ESA, mainly motivating to better sampling the parametric space in your hybrid approach. Do you think about to improve the hybrid modeling workflow using another mission, not optical only, for example, forest hike, whatever?
Yes, hybrid models or the GPR models, the trained models, they're very convenient because at the end it does whatever you put into it, you trade with that and it developed a model. You only need to make sure that your training data, the type of training data is the same as your observations. For instance, yesterday we saw some GPP models by Pablo. These GPP models are prepared by multiple inputs variables from Sentinel-3, from fluorescence, tropo-SIF, ERA data. So as long as you prepare your training data the same as your satellite data, you can combine anything.
Thank you, Joachim. I have one more question from my side. All these retrievals are per pixel, am I right?
Yeah, absolutely.
So what about convolutional type of networks?
Yes,
What is your vision on that? Do you think they would be implementable for this type of retrievals?
I'm not so much in favor of those kind of models for the simple reason that we want to quantify the uncertainty of all these products. I'm not sure how you will do that with convolutional neural networks, but because you need to have two types of uncertainties, so the uncertainties of the model itself plus uncertainty of propagation, it's complicated with those more black box kind of models.
If you would use them as a black box, yes, but if you open them up, and that's what's actually the current trend to my best understanding, I'm not a machine learning expert, maybe there is a way. They actually are working towards uncertainties with CNN as well as we speak. So
right. I've not yet seen
just wanted to know if you are experimenting with those as well or not. So.
Yeah, we can talk about it.
Thank you. So thank you very much, Joachim.
So our next speaker is Jorge Vincent Severa, and he will talk about the atmospheric radiative transfer emulation challenge.
Yeah, thanks for the introduction. So good morning, everyone. So I hope that you don't have too much hangover after the party yesterday night. Well, I'm going to talk about a slightly different topic. So I'm moving out from vegetation and come back to atmosphere. So Pekka, I think you will enjoy it a little bit more. One person in the room at least might be a bit interested now. I'm just joking. I will present this activity on a challenge for comparison of atmospheric radiative transfer emulators. And we are now going to start the second edition that as a test case scenario, we are going to be using the FLEX mission. So, well, just to put you on the context, we are talking here about atmospheric radiative transfer model. These are computer codes that simulate the atmospheric propagation of light through the atmosphere and how it interacts with the atmospheric constituents. So we are talking about the gas molecules, the aerosols, and so on. And these models, of course, they are widely used in several application domains. So we can use them for data processing. We can think about atmospheric correction, retrieval of atmospheric properties. But also we can use them for generating synthetic SINs. And this is a clear example on the FLEX, for instance, when we are doing the the end-to-end simulator for FLEX, and we are using that for validating our algorithms. We are using them also for different applications, such as atmospheric chemistry, physics, but also climate modeling and weather forecasting. So these models in general, yeah, they are physically based, accurate models that we can use them for all these applications. But of course, these models, this accuracy and this physical realism comes at a cost, and basically that they are quite slow. So typical approach is we generate a large lookup table, and then this large lookup table we are going to do interpolation. So of course this also puts other problems than when we are working towards very high spectral resolution data, and we have very accurate mission, very precise stringent mission requirements, and then we have the issue of, okay, we need better, higher, bigger lookup tables to do an accurate interpolation. And of course this comes also with other effects of big memory consumption, large time for generating those lookup tables, and so on and so forth. So the question that we put here is, can we use machine learning models to replace the traditional lookup table interpolation approach? The short answer is yes. So I will then introduce the concept of emulators or surrogate modeling. So emulators are machine learning algorithms that they basically reproduce the way they work deterministic models such as an atmospheric RTM. And this replacement, let's say, is going through statistical and regression models at the very core of these algorithms. No? The benefits of these emulators is that they produce high accurate results, and they are computationally quite efficient. They are also memory-wise also quite efficient, and as Jochen, for example, was showing, also this kind of machine learning models, they are also very efficient to put them on this kind of processing pipelines. So we can think that we can use them as an alternative to the traditional lookup table interpolation approach. Still, the challenge here is that we are working with very high dimensional data. We are working with several input dimensions. We are talking about geometry, aerosol parameters, other atmospheric parameters, and also very large spectral data that we have to simulate in the context of, for example, the FLEX mission. So also these models, they have to reproduce the physical complexity of their relative transfer model counterparts. So we have here the complex processes of absorption, scattering on the atmosphere, which has very complex spectral signature. And for that, well, in the past years, there are many different teams that they have been working on this kind of research activities, and they have come out with different solutions for these emulators, which use different regression algorithms, different architectures. If we are talking more about neural networks, machine learning methods, feature selection, dimensionality reduction, and many other design choices. So we thought, okay, maybe what we can do is try to benchmark all these efforts, and having a kind of a competition, a benchmark to compare these atmospheric RTM emulators with the common evaluation protocols and the same data sets. And it comes to me to present this first edition of the Atmospheric Machine Learning Emulation Challenge, AMLEC 1, which was the main goals was to benchmark these emulators for atmospheric RTMs, but also to promote the collaboration and the sharing of the information between the community working on these models, and to basically advance on the design concepts of emulations, finding some let's say some limitations, some strategies that could be improving the results, and also to build this kind of community around this challenge to further exploit that and gain some momentum to further evolve in the design of future emulators. The activity of this first edition of the challenge was already done, was lasting for 2 months between May and June this last year. We had a total number of 8 models participating to the challenge, and it was done in the framework of a machine learning conference called ECML-PKD 2025 that was done in Porto, Portugal this last year. In that moment, the challenge was only aimed at evaluating the accuracy of emulators through astrometric mean relative error. And well, you have here the website if you want to know a little bit more about the challenge, about the protocols, about the metrics, and also you can have access to the data. In this particular case, we use two scenarios to test the accuracy of emulators. We use one scenario that was dedicated more to the atmospheric correction of hyperspectral data and time-like configuration, 400 to 2,500 nanometers. And then we have another scenario more aimed to resolve the CO2 band in the Sweet spectral range. Well, I'm not going to go to describe all the results, the table and the figure, just to give you an overview of what kind of results we got from this experience, from this first edition of the challenge. We got 4 Gaussian process-based model approaches. That basically the main differences were the kind of kernels that they were used behind, the kind of dimensionality reduction, how many PCs, principal components, they were used for this dimensionality reduction. And in general, the main outcome from this was that the SGP models were pretty accurate when we have low number of training samples, typically below 2,000. Then on the other side, we also had 4 different neural network-based approaches, which has different architectures, some based on RNNs and convolutional variational autoencoders. But these models perform a little bit worse when you have scarce data sets, but when they were trained with the biggest data set available, they started to provide relatively good results. In the figure that you can see here on the bottom right, basically you can see a heat map, and that represents the relative error, the mean relative error for all the wavelengths and the different models on the y-axis. And this is for a particular scenario. I'm not going to go into the details to compare the different models, but basically out of this kind of plots, we then summarize, we average the spectral error and provide a ranking of the different models based on the different scenarios for the atmospheric correction scenario, for the CO2 retrieval scenario in both interpolation and extrapolation tracks. So from these mean relative errors, we can get a ranking, and then we can basically see which is the method that is winning. We were also tracking runtime, but runtime was mostly based on the numbers provided by the participants. So the participants were running the models on their computer, and of course, but they could eventually cheat and put whatever number there. We hope that they were not cheating, but anyway, the thing that they were using still different hardware for running their models made this comparison a little bit less precise, let's say. So we didn't use at this time the runtime to make the ranking. So well, what we learned from this first edition of the challenge is that, well, still we got 8 models. In practice, there were only 4 participants with 2 models each. We believe that this was because, well, it's quite a technical, specialized topic, so maybe had not so much interest for the broader community. We believe that maybe having some prizes or some industrial sponsorship, maybe that will increase the visibility and the interest for participants to participate and for industry to be interested into these kind of activities. And to progress into that, so attract more participants for next editions. We also had a constrained timeline, so we got accepted by the conference where we were going to present the results, and this of course get a very short time window before the launch of the challenge, and to promote this activity in special venues like today, for example. Also, the platform that we were using, it was Hugging Face. It was not the best platform to run a challenge. I got this feedback from the participants and from other people that could have been interested. So the idea here is instead making a collaboration with the FILAB and with the ESA FILAB and running a second edition of the challenge in collaboration with them to deploy the evaluation activities within their platform. Anyway, the good points of the benefits that we had here on the successes of the first edition of AMLEC, it was that the educational impact, so basically we have this collaboration between the people participating into the challenge, and well, even there were some master students participating into this, so they were also learning a bit about the radiative transfer modeling, about emulation, participating into these kind of activities. we had this technical foundation, so the deployment of the data sets and the implementation of metrics, how to run a challenge. Well, it was the first time I'm doing this kind of activity, so it was quite a good learning experience. And the research output, so we are working currently on a publication, so it's currently under review. And yeah, basically with this first edition proved a bit of the interest on the scientific viability of doing emulation. And then we are thinking, okay, maybe we can move towards a second edition to learn from these experiences and to focus now more on operational readiness, not only evaluating accuracy, but also uncertainty and runtime. So it comes to propose a second edition now for the FLEX mission scenario, and that's why I'm here. So on the first one, we standardized the benchmarking. Now we are going to be more mission-oriented and focusing on the FLEX scenario, on the FLEX perspectral mission as an application scenario where these emulators can actually play a role. The idea is, again, not only evaluating the emulators in terms of accuracy for atmospheric correction, but also in terms of accuracy prediction and also runtime. So the organizers is University of Valencia on the Image and Signal Processing Group in collaboration with the ESA field lab. We are aiming to start the challenge in July 2026, but to be honest, I think we have to postpone it because it will be summertime, so I think that would be the best to move it towards September probably. So it's still something to be confirmed and decided together with the field lab. Again, the metrics will not be only accuracy, but will also uncertainty quantification and evaluation runtime. And the concept will be, the scenario will be on the atmospheric correction of FLEX like satellite data. We are now currently on the definition of the protocols. We'll be soon going to start implementation, deploying all these metrics and data sets on the platform. And then towards July, September, we will start running the challenge for the public. That will be lasting 3 months. This challenge will be shown on this website here, AI for EO. But still, you can access the website, but there is no indication about this challenge AMLEC 2. You will find other challenges. As a participant, what you will be doing basically, well, you will have access to this website. You will register. You will say that accept the terms and conditions, and basically you can access to the training data set. Here we are thinking about providing 3 different data sets: small 1,000 samples, medium 3,000, and large 10,000 samples. Sorry for the typo here. Then you will have some time to configure and train your models. You can train several times. You can improve them. The idea here is that every participant participates with only 2 models to avoid having small changes or small variations on the same kind of model, but actually to promote variability on the kind of models. And then when you're happy with the models, you submit them. And of course, you will be able to submit improvements of those models through all these 3 months. And the idea is that on the platform, you will upload your model, and then we will run your model directly on this platform so that we can track runtime under the same hardware conditions. And then you will have a public leaderboard where you will see your results, the kind of plots that I was showing you before, the kind of error metrics that I was showing you before, as well, and the ranking. And the evaluation will be done in terms of 3 metrics: accuracy, so atmospheric correction. We want to check the reflectance. I finish in 1 second. Uncertainty quantification, so how confident you are with the prediction, and efficiency. And yeah, with that, I think I'm finished here, and thank you for your attention.
Thanks very much. So in the interest of time, I think we need to move on to the next speaker. Thank you.
Okay, so the next speaker will be Miguel Padot from the DLR. He will stay in the topic, and he will introduce actually a new scheme for retrieving fluorescence using combination physically informed neural network atmospheric simulations. Floor is yours.
Okay, thank you. Good morning. So yes, I'll be talking about physics-based emulation of head sensor radiance. as a tool for novel SIF retrieval schemes. This is work done in collaboration with these colleagues here. All of them are sitting in this room. And I'll start with our motivation. So as you all know, SIF retrieval requires accurate modeling of sensor, atmosphere, and surface effects. And part of this modeling relies on radiative transfer, routinely used for a long time, but this is a slow step, as we've also seen in Jorge's talk. And this is really a fundamental obstacle to include physics-based simulation in retrieval methods. Usually you do lookup tables offline with limited scope, and you cannot really apply this simulation step in retrieval methods, at least easily. So our work tried to realize a both fast and accurate emulator of head sensor radiances, and we focus on a very well-defined case study and very limited. We focused only on the O2A absorption band and these two different instruments. iPlant, you've heard a lot about it in the last days, a prototypical airborne instrument of very high spectral resolution and also spatial resolution. And then DESIS, which is installed in the International Space Station, space-based instrument, moderate spectral resolution, and provides spatial resolutions of about 30 meters. On that note, I want to spend one slide on DESIS. So you all know that SIF measurements have been routinely performed, done with high spectral resolution instruments that can provide you either very high spatial resolution, ground-based airborne instruments, or a large coverage over the globe with space-based instruments. And we have a gap there. FLEX will certainly eat a little bit upon that gap, but will not close it completely. And on that scope, moderate spectral resolution instruments can really play a good role. And DESIS is one of that instruments. I put here some characteristics of DESIS, but there will be a dedicated talk which will also cover DESIS in detail by my colleague Emiliano Carmona in a couple of hours. I want to mention that there are some advantages, potential advantages for SIF from DESIS. It's not a mapping mission, but in principle it can cover basically the whole globe apart from very high latitudes. You have a regional coverage there. There's a large archive of data since 2018. And also because it's the ISS orbit, it covers different hours of the day. Maybe even more importantly, it is possible to derive SIF from DESIS, SIF at O2A, at a 30-meter resolution. And this really provides an intermediate step between pixels, flex pixels, 300 meters, 2-meter scale ground or airborne data. And if you want to know more details, you have the poster by my colleague Jim Buffa, the poster just back there. So I invite you to go and check it out if you are interested. Okay, so we wanted to simulate head sensor radiances, so we set up a simulation framework. We have a simplified head sensor radiance model, and we focus only on the O2A band. We model all the atmosphere and geometry with these two different radiative transfer models, Motran 6, LibRadTran 2.0.6. Then we come up with a realistic but simplified reflectance and fluorescence parametric models, just in this very narrow spectral range. And we use the knowledge that we have from DESIS and iPlant in our team to try to create realistic simulated spectra. One note here, I know that there are other specialized simulation codes that one could use here. That's not the novelty here, but we opted to design our own so that we can use it for our own needs. Yeah, so we have our simulation framework, so we can start simulating head sensor radiances, and that's what we've done. First of all, we did a quite extensive sensitivity analysis to select all the key parameters in our very special case study and to define their ranges. That's what you see in the table, separately for DESIS and iPlant. We end up with an input space of 12 or 13 dimensions in the two cases. And we try to sample this parameter space with 3 different sampling methods so that we can cover it well enough for our purposes. And after lots of work, we end up with 2 data sets, one for DESIS, one for iPlant, with a few million sample spectra over this 12 or 13 input dimension space. You can see some examples here on the plots to the bottom. One important point that I want you to keep in mind is that the simulation time is a few minutes per sample spectra in a very standard virtual machine. And this is almost completely dominated by the radiative transfer part, so either Motran 6 or Liberatran. At this point, I want to make one parenthesis here. So in doing this work, we noticed that when you simulate high-resolution spectra with the help of Motran or Liberatran, you obtain slightly different results, especially in the O2A band. That's the plot that I showed there. It's a difference plot between Liberatran and Motran-based simulations. The difference is, if you go to high resolutions, can be up to 20%. And this even with the same input. The same I have here to put between inverted commas because it's the same from the point of view of average user, which is me. Internally in the code, I cannot be sure that the input is exactly the same. The important point here is that at this point, I cannot tell which one is the more correct version of this simulation. Both softwares are based, or the absorption in both softwares are based in ITRAN database, but at different points in time with different treatments. The atmosphere and the aerosols are in principle the same, but probably treated differently within the code. I don't think this is new, but the key point is that if you use high spectral resolution data to retrieve any parameter, SIF included, you should be aware of these systematic differences. Okay, parenthesis closed. Now, what I wanted to do here, we wanted to do here is to try to realize an emulator that can replace in certain circumstances the physics-based simulation. So basically to replace all that complex box with a simplified model. As we've seen also in the previous talk, this is a regression in more or less high dimensions, these 12 to 13 input dimensions, and the number of bands, which are tens or hundreds of bands in our cases. We threw at this regression problem just very simplified machine learning models that I put them there, and you'll see that we didn't really have to go more complex than that. Okay, we split the data sets that we had in training, validation, and test, and we asked the question which of these models can perform well enough, accurately, and fast. The results are in those two tables, one's for DESIS, one's for iPlant, and okay, many numbers, but what you have there is the error of the emulator with respect to the physics-based simulation, and also the time performance. The error you can compare to a typical SIF signal that I put there on the right. And the time performance you can compare to these couple of minutes that the physics-based simulation takes. I'll go through the table with you. So in terms of accuracy, linear models, polynomial models of second degree, nearest neighbors, and support vector regression do not work in our case. Simple neural networks, kernel ridge regression, Gaussian process regression, they have borderline accuracies of the magnitude of the SIF signal, and polynomials of degree 4 or higher seem to be very accurate and very fast. So in the end, we settled with a baseline emulator that is basically a 4th degree polynomial, which is fast and accurate. Just one note here, polynomial models are of course very simple but because there are many dimensions here, there are actually quite a number of parameters. In any case, the conclusion is that we didn't have to go much further than that because simplified models seem to do the job. Okay. Just a couple more details on the performance of the baseline emulator. You can see on the plots to the left and center that accuracy is about 1 order of magnitude below a typical at sensor radiance SIF signal. So the The band there is 1 order of magnitude below the green line. It's of course much faster than the physics-based simulation. Just some numbers: with a very regular virtual machine, you can predict 1 spectra in about 1 millisecond. If you produce in bulk, since these are just matrix multiplications, you can achieve 10 microseconds per spectrum. This can for sure be improved in a more fancy machine. There's also room for improvement in terms of accuracy. You can improve up to a factor 2 or 3. I don't show results, but you can ask me if you want. But you pay the price of either speed or scope in terms of the applicability of your emulator to a part or a subset of the input parameter space. One important point is that these emulators can be used to reproduce accurately DESIs and I-plant real measurements in a range of different surfaces. And this means that the simulations, and therefore the emulators, are realistic and can be used in a retrieval method. And that brings me to the outlook. So I'll just mention 3 applications of this type of emulators that are not easily possible with a physics-based simulation. First, you can realize a fast and accurate online simulation step in a SIF retrieval method. And again, I direct you to the poster by my colleague Jim Buffa there in the back, which has exactly a SIF retrieval method that is emulation-based with these emulators, and that has been applied to derive SIF in the O2A band from iPlant and also from DESIs with very good results. Another application is to create tailored data sets that can be large and that can be created in a very short amount of time, and you can use them for training or for assessment of performance of retrievals. And also it can potentially aid in the uncertainty estimation. So the scope of our work was very well defined, as I said, O2A band only, and only these 2 sensors, iPlant and DESIs. But it is possible to extend this work to other sensors, for example. And one of the variants of the DESIs emulator that we created can also be applied to other space-based sensors. So what I put in this plot is the result of that emulator applied to a FLEX-like sensor. And you can also extend to other spectral ranges, like the O2B band. But here, some more work is needed, and we are not quite there yet. And with that, thank you.
Thank you very much, Miguel. We have a time for 1 question.
There's one.
Thank Miguel, very interesting talk. You know, in the past we also worked with emulators, and for us it was very important, you know, to deal with the high dimensionality of data, especially for GPRs, so that do not scale so well, to first convert the data into PCA and actually train on the PCA and then afterwards reconstruct. You preserve the same data, but you are much faster, and yeah, in this way you can train with more data and so on. What's your take on that?
I must say that since the results were good enough with the polynomials, we did not invest too much time in many of the other, in some of the other models, including GPR. So it's well possible that these are not the results I show here are not completely representative from the full potential of what GPR and KRR can do. So I didn't try to PCA and then apply GPR or any other things. Yeah.
Okay. 1 more question, Ross? Oh, too many. Oh. We take 1 and very quick, please.
Okay, yeah, I had 2, but I was asked only 1 and the other in the coffee break. This is about the difference between the 2 spectra that you have, LIP-TRAN and MATRAN 6, right? And you said it's potentially important. So maybe also for the FLEX study is important. So I want to know if you, from high-plant data, you actually found out which of the 2 works better, even if you don't know which one is true.
Yeah, I mean, ideally you have a difference there. You can compare it to a very good high-resolution spectrometer and try to tell which is more correct. We are in the process of doing that, but because the sensor itself included, we have high-plant data, so we could compare it to high-plant data. But you also have to allow for potential sensor spectral shifts, and that makes, at the moment, I don't have a reply. I cannot really tell the difference. I don't know if it's possible. Yeah, but
in any case, thanks for pointing it out, and
yeah, sure.
we can talk in coffee break.
Thanks.
Yeah, thanks.
So our next speaker is Stefan Meyer. We've heard a lot about scope. Now this time it's slope.
Thanks, Georg. Well, I don't know whether you noticed all the presentations in the last couple of days, all that work was referring to radiative transfer models. It's pretty much every work requires radiative transfer models. Even sometimes it's not explicitly mentioned. But what I also noticed was that it was the same 2 or 3 models that have been used. Now, this can mean 2 things. Either these models work so perfectly that we don't need anything else. The other option is that there are just no alternatives. And I think, and also thinking about Miguel's presentation, I think the problem is there are no alternatives. And that's why I want to present an alternative at the leaf level. And it sounds pretty similar to SCOPE, but I picked that name actually before Christian picked the SCOPE name. All right, so what were the objectives for that model? We wanted it to be a deterministic model based on physical laws. We didn't want any empirical model, but we didn't want it to be too complex. And what I mean with that is we didn't want it to require input variables that are not easy to get, like, I don't know, the shape of a leaf cell or something like that. So it needs to be reasonably simple to use. But we still wanted it to take into account relevant properties. And I'm mentioning, for example, clumping of pigments. A leaf is not just a soup of chlorophyll where chlorophyll is homogeneously distributed. The chlorophyll actually sits in chloroplasts and is quite clumped. And that has got an effect on the radiative transfer. And that's quite often forgotten. And even something very simple, vertical inhomogeneities. I mean, there are some leaves which are pretty homogeneous in their pigment distribution, but the vast majority of leaves have not a homogeneous distribution of pigments and also scattering properties across a leaf section. One thing we said, the model doesn't have to be easily invertible analytically, because these days there are so many inversion methods that are really efficient. We still want it to be reasonably fast, so we can do a lot of simulations in a reasonable amount of time. The other thing is we don't want to use leaf level measurements to actually develop the model. We only want to use the leaf level measurements to validate the model, to have that independence of model development and validation. One key component are specific absorption coefficients of the pigments or constituents of a leaf, and we want them to determine them independent of the model, so we don't create this circular dependency. And then obviously, that's why we're here, we wanted to include fluorescence, and not just sun-induced fluorescence, but also with lab-based light sources and also laser-induced fluorescence. That's actually where I got in touch with chlorophyll fluorescence many years ago for the first time. So how does that leaf model look like? So in the center, you can see my artistic interpretation of a leaf cross-section. We've got multiple layers. Usually, we divide them into 4 layers. For some leaves, these middle layers, the palisade and spongy layers, they're basically 1 in terms of structure, but even then in that case, the pigments might still not be equally distributed. And for the model, we just treat them as multiple layers. But again, as I mentioned before, we don't treat the pigments to be just in a homogeneous soup. We got these pigments located in chloroplasts, so quite clumped. And then for these leaf layers, I don't want to go into the details, but in each of these leaf layers, the light can be in 3 different states. It's either traveling down through the leaf, up, or it has been absorbed. And then the transition from in between these states, that's described by physical laws, mostly Bayes' law. And what the model then looks like is the light states are described by a vector. These transition probabilities are in the elements of a matrix. And the radiative transfer modeling comes down to a series of matrix multiplications. All this is done wavelength by wavelength, and the fluorescence basically transfers light from the shorter wavelengths, where the light has been absorbed, into the up and down states at the longer wavelengths. So as I mentioned before, one key component are specific absorption coefficients, and I've just picked one example here. They're actually not so easy to measure. Chlorophyll, for example, is a very complex molecule. Its absorption properties are highly dependent on the chemical environment. And here's just an example. The solid line is the absorption coefficient in the core pigment, or in the core protein. The dotted line in a light harvesting protein environment, and the dashed line is in solution, or the dashed dotted line is in solution. And you can see they differ quite a lot. So you can't just take the pigment in solution and make these measurements and use that in a leaf model. What turned out, we actually had to distinguish between 2 different chlorophyll A absorption coefficients. And we had to distinguish between the core protein environment and the light harvesting environment. Only by doing that we could reproduce measurements reasonably well. Fluorescence, that's what we take as a fluorescence spectrum, obviously without any reabsorption. And then we get to something like this. For those of you not familiar with these diagrams, so the bottom lines are reflectance with the left-hand side scale. The top lines are transmittance with the right-hand scale, and I point out that this is inverted. And by doing that, it's basically a bit in the middle is what's absorbed. So that's a very convenient way of describing where the light goes, whether it gets absorbed, reflected, or transmitted. And now I just show some examples. And I mentioned before, chloroplasts, so chlorophyll is not equally distributed. The other thing is that chloroplasts are actually not static. They're actually moving around in the leaf. Depending on the light, they might expose a wider area to the light, or they might hide from the light. And don't pay too much attention to these numbers here. That's just kind of the effective cross-section. And you can see that actually has an impact on the leaf reflectance and transmittance. Yeah, now you may say, this is pretty small, but it's small at an absolute level. If you look at the relative level of the relative variation, that's actually quite significant. And I come back to this a bit later when when I show some examples of chlorophyll fluorescence. A byproduct of modeling the radiative transfer that way is that we can actually extract light fluxes within the leaf. And these are things that people have measured in the lab with a fiber optic probe as well. And you can utilize that also to get some more physiological insight why leaves are built in that way. They are. We did some studies where we actually optimized leaves in the computer for a certain light environment, and it turned out the pigment distribution and scattering was exactly what nature has come up with. So leaves are optimized for light absorption. Then obviously that's why we're here, fluorescence. These are examples with just a flat light source. So a halogen lamp in the lab, for example. This is what we all know when we do measurements out in the field, solar-induced fluorescence. And this is an example of laser-induced fluorescence. So we hit the leaf with light in the blue or green, and that's what we get. One other thing as well, quite often neglected, a leaf has got two sides, and that's how fluorescence differs depending on whether we look at the top of the leaf or the bottom of the leaf. Yeah. And I'm almost through. One thing that I mentioned before, chloroplasts again, and that's the impact on the chlorophyll fluorescence spectrum. Now, obviously, in the near-infrared, in the far red, the relative impact is relatively small, but in the red, it makes a difference of 20 to 30% when these chloroplasts are moving around in the leaf. So something we so far have not really looked into. Now, just an outlook. Currently, the model is implemented in C, but we're currently re-implementing it in Python to make it more accessible. We're currently defining the interfaces, how we get the parameters into the model and how we get the results out. So if you have any ideas or suggestions how that should look like, get in touch so we can build that accordingly. We want to make the model available, widely available on GitHub. There are no licensing restrictions or anything on that. We really want it to be used. And finally, we're seeking collaboration to further validate the fluorescence component. We did a lot of work with the reflectance and transmittance, but there's still scope to do more validation with the fluorescence component. And what we learned from the reflective component is that just taking a data set and using that to validate doesn't work too well because there is always some information missing. So you actually have to work with the people who have done the measurements. And that's why I'm seeking collaboration with people who have actually done measurements and further validate the model. And with that, I want to close, hopefully within time, and I'm happy to take any questions.
Thanks. There's, in fact, time for questions.
Thanks, Stefan. You said a lot about the theory behind the model, and I think we have many groups here that have data available for validation, but can you say something about what is the input of the model? What do you need to run the model?
Well, we sort of set it up in different ways. So ideally, you have information about, for example, where the chlorophyll or the chlorophyll concentrations in the different layers. But we do also have the option of using defaults for that. So it is basically pigment concentrations that you need. That's the main information. With fluorescence, obviously, you also need information about the light source. You need to know with what light you illuminated the leaf, because that makes a big difference. Okay. As you've seen, I mean, obviously, lab spectra look very different from outdoor spectra.
Because it's not only about the accessibility to the model or the availability of models, it's also about the complexity to parameterize the model. But I think I will come back to you later.
And that's why I said it's important that the model doesn't require parameters that you can't really get to, because then it becomes unusable. Yeah.
Christian has a question, of course.
Of course. Thank you for the great presentation and all the development. I was wondering still, what I did not fully grasp is how you do the specific absorption coefficients, because in Prospect you tune them because they're model specific, and you mentioned these different in different conditions. How you get the input for your model so that you actually reproduce the leaf spectra without tuning them?
And that actually was the bulk of the work to get to this point, to get this specific absorption coefficient. So we did a lot of investigations on how that spectrum is changing in different solutions, but there is also work where people extracted these proteins and measured absorption coefficients. And that's for chlorophyll basically what we ended up using. And it turned out we actually need that to be consistent with observations. We really needed these two separate types of chlorophyll A. And that's something you can't get when you're just tuning the specific absorption coefficients from a few measurements. You don't really get to that. But yeah, this was the most tricky part. And for the centrophils, I still don't have much information how they change in terms of specific absorption depending on the chemical environment. Yeah. But it's less critical than with chlorophyll.
So great progress.
Thank you very much. I have tons of questions, but we're gonna catch up at the coffee. And the next speaker I would like to introduce. We will move to a different scale, very, very different from leaves all the way to the landscapes. And we have Tristan Quaife talking about the implementation of SIF in the JULES model. Tristan, the floor is yours.
Thank you. Okay, so I'm going to talk about modeling SIF from JULES. I'm from the UK National Centre for Earth Observation, as is my colleague Natalie, who did the JULES runs, and my colleague Patrick is actually a member of the National Centre for Atmospheric Science, but he did the modifications to the JULES code. Okay, I could do a whole talk on what JULES is. It's a land surface model. It contains loads of different processes. It models the exchange of mass and energy between the atmosphere and the land surface. It's used for numerical weather prediction in the UK weather prediction models, and it also sits underneath our climate models, including UKASM, which is our flagship climate model, which contributes to CMIP, etc. The important things from the point of view of this talk, I mean, there's loads of ways of defining JULES, right? But the important things from this talk is it uses the Sellers two-stream radiative transfer model for light interception by the canopy. You can have either the Farquhar or the Collatz scheme for GPP, and I'm using Collatz in this case. And just to mention that in this presentation, all the runs have been done offline, so no dynamic atmosphere in these runs. I'm forcing with reanalysis data. Okay, so we'd like to be able to predict a SIF from JULES to be able to do model testing. Now, there's a really important point about my design concept here, which is what we've tried to do is make the physics of the predictions of SIF as close as possible to the physics inside JULES itself. So that way, when we see a discrepancy between the observations and what the model is predicting, we're confident as we can be, that this is a problem inside JULES and not a problem inside the way we've predicted SIF from JULES, if that makes sense. So the good news is JULES already predicts a whole load of things which are useful to us for predicting fluorescence, and we have two stages. We first pass the number of absorbed photons, electron transport, leaf temperature over to a leaf level SIF model, and then the leaf level SIF at various levels in the canopy. And then that leaf level SIF model is used to predict the emissions inside a radiative transfer model that predicts the canopy leaving SIF. And I'm going to explain those two parts as quickly as I can right now. Okay. Leaf scale SIF model is split into two parts. We have a module which predicts the overall SIF leaving the leaf. This is done using the Van der Tol model that many of us are familiar with. And essentially, we're taking the electron transport and the absorbed radiation from JULES to do that part, and then simply scaling up to the layer level using this equation. the implementation you're about to see uses pretty much the kind of the equations from the 2014 paper, but we have scope to change for example, the MPQ in the model too. Okay, I'm kind of, having just seen Stefan's presentation, I'm almost embarrassed to show this slide. This is how I do the leaf level radiative transfer, and it's the simplest solution I could think of, and numerically incredibly efficient. And essentially my starting point is to input leaf level spectra. So I need a source of input spectra to drive this, and a chlorophyll fluorescence spectra, and then I split the leaf into 2 layers that have equal optical depth, put the fluorescence emission in the middle of the leaves, and then recombine those 2 layers using adding to predict what comes out at the end of the SIF leaf. Now, in principle, the code, you can put in any leaf level spectra you want and to do this with. What's interesting, and I wasn't going to mention this, but given that Stefan was talking about these things, in the examples that I'm going to show you, I've used a sample spectrum that I took from Prospect. Okay, the dashed line, so arbitrary units, these are all normalized. The dashed line is my fluorescence spectra, and the dark solid line, this one, is an example output from that leaf level model. And you can see it's kind of doing a reasonably good job. These faint lines underneath it are data that I've taken from some of Troy Magny's work, and they're normalized so that we've got the same amount of energy in each of these cases. Otherwise, it's really difficult to make that comparison. And you can see in the far red part, we're doing a pretty good job of getting that the SIF signal right spectrally. And kind of from the examples, the comparisons I'm going to show you with Tropomi, they're all at 740. So I think for what I'm going to show you, this is good enough. The interesting thing is there's a shift in that, the laser's dying on this pointer. There's a shift in that peak, right, that you can see. And when I gave this talk at AGU a couple of months ago, I said I didn't know what was causing that. My hunch was it's because I was not splitting the leaf into enough levels. That turns out to be a very small amount of the problem. But in fact, this is caused because Prospect's doing far too much absorption in the chlorophyll. And when I've repeated this, I'm afraid I didn't get a chance to put the slide in, using observed reflectance and transmission data, it almost entirely corrects that peak back to where it should be. Okay, so I'm not going to go into much of the detail here, but essentially, the canopy level radiative transfer model is done by combining slabs of 2-stream media, from which I use the solutions, well-known solutions from Mead or Weaver. And for the SIF component, there's a paper that describes how you do this for reflectance and transmission, but for the SIF component specifically, it's this equation here. Really very simple, it's an analytical solution to the problem. But from the point of view of this talk, okay, so this is an illustration of how that's working. There's I put the fluorescence in the middle of each layer, and then I apply that equation, and it predicts what's coming out of the top of the canopy. But from the point of view of this talk, the really important thing is this plot here. This is the, not predictions of SIF, but predictions of the absorption at various points in the canopy. And this is zoomed in to a really, really fine detail compared to what you would get if you ran the Sellers radiative transfer model. So this is now the absorption in the canopy, and the correspondence, right? This is a Monte Carlo experiment, and the correspondence is almost perfect. The difference is down at numerical computer precision levels. Now, the reason for that is essentially because I've rederived the Sellers model, but allowing me to predict emissions from it. And this means that my model is physically consistent with what's inside JULES. Okay, final thing I need to point out. We don't have a good way of implementing water stress for the SIF. And I'd argue we don't have a good way of implementing water stress in JULES. And that's in common with most land surface models. So we're using in JULES to modulate GPP, we use a really simple function of soil moisture, which goes from complete stress to uninhibited by the amount of soil moisture. So that is in JULES anyway. And so my decision to apply this to SIF was essentially to reproduce the same strategy. So I take this function of soil moisture and I apply it to the SIF predicted by that processing chain to get the actual SIF with the water stress included. Okay, Haran showed these results yesterday. I'm not cherry picking here. In fact, I've selected results that show a range of JULES behavior. And I anonymized the models just in case, but Haran actually said what all these models were yesterday, so you can actually work out who is who. But these are summer mean diurnal cycles for all the models from Old Black Spruce on the far side, Niwot Ridge, and Delta Junction on my side of the slides. And you can see that JULES, which are the dark green ones, we're overestimating in Old Black Spruce, not out of the range of the main pack of the models. Niwot Ridge, we're doing really badly. We're underestimating quite significantly. And just to be clear, this is a really complex site, high elevation, very, very dry, very, very sandy soils. And I think this is absolutely pointing at the fact we're getting that water stress function wrong in JULES. And at Delta Junction, magically, we are absolutely bang on the observations, but I wouldn't read a huge amount into that. Luck rather than judgment, I suspect. Okay, comparisons against Tropomi. There's a whole range of issues here. I'm using the monthly data from SIF for this example, and I've tried to replicate the compositing algorithm for the monthly SIF using JULES. This is slightly complicated for various reasons, partly because I'm using reanalysis to drive the JULES SIF. What it's not possible to do reliably is, so I'm running JULES at a half-hourly time step, so in principle I could take out the exact half-hour time step of the overpass of the SIF instrument. But what I can't guarantee is that the reanalysis data is actually replicating the state of the atmosphere at that time. Perfect, thanks. And so what I actually do is within that monthly period, I take the highest APAR, not the highest SIF, the highest APAR in the model, to get the highest, essentially the highest sunlight visible to the model during that time period, which I think is roughly reproducing the SIF compositing algorithm. But if there's anybody in this room that knows that algorithm reasonably well, I'd really, really like to have a chat at some point. Okay, so this is now for South America, and it's that for that in June, which is in the Amazon dry season. The magnitudes are reasonable. JULES is overestimating the rainforest, but we underestimate in the Cerrado and the Pantanal, and I've put those arrows on there so that you can, I'm sure most of you know where those things are, but just in case, so you can orientate yourself. Okay, however, when we get to the wet season, magnitudes are not as good. Okay, we're underestimating now in large parts of the continent, and we're not capturing the gradient in the rainforest, and we remain, surprisingly, too low in both the Cerrado and the Pantanal. And the Pantanal, in particular, is almost zero. So, I'm going to... So we spent the last... Again, I showed this at AGU, and I said, I don't know what's doing this, and we've spent some of the last couple of months working this out. I've got some line plots to illustrate what's going on. This takes a little bit of time to kind of get your head around what's going on here, but essentially the red lines are the SIF data and the blue lines are the JULES predictions. The solid lines are for the yellow box in that map, and the dashed lines are for the gray box in that map. And actually, I think this shows things aren't as bad as they originally look in the Amazon. So the solid lines, they're kind of roughly in the same thing. Neither of them has a great seasonal cycle, and there's a level of uncertainty in the retrieved SIF anyway. And in the southern Amazon, so the dashed lines, so we're getting the seasonal signal from JULES about right, but maybe the magnitude of that seasonal signal is too much. I think the interesting thing, though, is when we move to looking at that kind of sub-Amazon region, so the Cerrado and the Pantanal. So the Cerrado is the yellow box, so that's the solid lines, and the Pantanal is the dark blocks, so the dashed lines. And interestingly, in SIF, they look almost exactly the same when you average over those boxes. And we're clearly getting something wrong. Now, there was a moment of, and the story is about water, right? We're getting that water stress way too hard. We're hitting it way too hard in the Cerrado. But in the Pantanal, the interesting thing here is, So although JULES has overland flow in it, we typically don't turn it on. And so unless we have a specific reason for doing so, in these runs, I have no overland hydrology turned on in the model. And the Pantanal is a wetland, but it's completely driven by overland flow. So in these JULES runs, it's completely dry because I have no water entering it. So the model is cutting off the fluorescence because of that water stress function I've applied to it. So kind of a relief, and I hope when I turn it on, we get better results, but we haven't tried that yet. Right, that's kind of me done. The code is available. It's probably not much use to you if you're not a JULES user, but my offer to you is if anybody's sat there thinking they might like to play with some of this, well, I'm happy to help implement this in another model. There are examples in Quincy, and Thomas is going to talk about D&B in the next talk, and some of this is in D&B as well. So I've talked about the spectral model. There's also MPQ in there, and the possibility to switch the MPQ model around counts for all orders of scattering. And what we've demonstrated is it is capable of, even though it's kind of accidental artificial example, we have demonstrated that it is capable of picking up shortcomings in JULES, and that is why we're doing this, right? We do this because we want to test our model. We don't if it agreed perfectly, that would, not be doing what we wanted. And at the moment, we're working on a bunch of things. In particular, what we don't have at the moment is we're not separating out the sunlit and shaded components. Right. Thank you very much.
Thanks, Tristan. A quick question.
Thanks for the presentation. Some of the biases, do you think they might come from the fact that SIF we can only observe during clear sky conditions, and in the tropics, obviously in the wet season, GPP might be light limited, and so it's not necessarily representative what the SIF observation provides? Right, so this is a really difficult problem, is to try and replicate that with the model, try and replicate the actual observations. And so I've tried my best by only selecting, I'm using this maximum APAR to do the compositing from my, so I've got a whole month of half-hourly modeled predictions, and I just take a handful of the ones which have the maximum APAR, and I'm assuming that corresponds to cloud-free conditions. But there's definitely problems doing that, and that's going to affect all modeling. It's way more complex than I thought it was going to be when I started out on this.
Thank you. I have one short question regarding the needle leaf type of forest boreal plant functional types. Do you think that Peter Seller model can really basically mimic this type of high-level scattering? And secondly, would there be an open space to implement escape factor somewhere in your scheme?
I think that, this is a really long, I don't have a short answer for you. And but I guess the issue is that, using a two-stream model to represent forests, full stop, is going to be problematic. But it is what is inside JULES. So my feeling is that's how we have to stick with it to try and tease apart any differences. But definitely not ideal for needle leaf forests.
Thank you. And we will proceed with the last speaker, Thomas Kaminski from the Inverse Lab. He will talk about the terrestrial carbon community assimilation system. Floor is yours.
Thank you, Spinek. So the first thing to mention here is that this is work of a large team, and it is composed of experts in fieldwork, experts in satellite observations, experts in modeling and in data assimilation. And quite a few of the co-authors are in this room, actually. It's about TCAS, the Terrestrial Carbon Community Assimilation System. And the system is built around a newly developed model called DNB. And is new implemented, but based on 2 existing models. You see the graph on the right-hand side, and you see photos of the fathers of the component models. So on the left-hand side, Matt Williams for the Dalek component, that's the D, and on the right-hand side, Wolfgang Knorr for the BT component, that's the B. And we developed this model with the aim to allow a combination of a diverse array of observational data streams to be combined with that model to yield a consistent picture of the carbon, water, and energy cycles. And all this development was funded by ESA. This is an open source community system, and the laser pointer works again, good. So it contains observation operators to compute equivalence of the observational data streams we assimilate. And the flow of information is as follows. So we have the model. It provides state variables to the observation operators that are sometimes additional modules, and sometimes they are embedded in the model, like the Zellers model for the FAPA simulation is embedded, and we put together a cost function quantifying the misfit to each of the observational data streams, and then we minimize that cost function by adjusting parameters in the process formulation of the core model and also in the observation operators. We also optimize the initial sizes of the carbon pools. Most relevant for today is obviously what we do with the solar-induced fluorescence. And here the most important thing to say is that you can guess that this already, Tristan Quave has developed this modeling concept here for this observation operator. So we have 3 leaf level source formulations, Gu, Van der Tol, and Lee. You saw the Van der Tol equations in Tristan's presentation already, and they differ in how they are linked to the core model, which variables from the core model they use. And then it includes the L2SM radiative transfer code that Tristan has just presented. And in the end, we have a spectral conversion to get to the spectral range that is observed. I show you one example of an assimilation experiment. It's over a savanna site in Extremadura in Spain. We run the model with 2 PFTs, C3 grass and temperate evergreen trees. And we run it in total for 7 years. 2 years are spin up, and then we have a single long assimilation window of 5 years, where we ingest all our observations simultaneously to simultaneously constrain the slow and the fast processes. And we use these 4 data streams, so an FAPA product derived by the JRC tip package, then the TropoSIF product. We use the GU model here for the source function, and then VOD and surface layer soil moisture from SMOS. So you see that also here. And this is how a typical result looks like. On the left-hand side, you see the 4 data streams that we assimilate, and see observations in green, prior in red, and the posterior in blue. And then you also see the error bars for the observations. And you see that as it should be, the posterior is closer to the observations, so the model managed to absorb the observational information. It's a bit hard to see maybe for the fractional water content in the surface layer, but here you see the statistics. You see nicely that the assimilation has adapted the amplitude of the seasonal cycle and also the phase a bit. But what's more relevant is actually then how these changes look like when we compare against independent observations. Here's the eddy covariance data for GBP and NEP, and you really see that translates the change from prior to posterior really translates into an improved GPP simulation. With NEP we are a bit lucky because none of our observations really constrains the respiration component. Yeah, this is actually bonus slides following your request. Jochen said we also should say something on uncertainty ranges, uncertainty propagation. So it's a complicated experiment. We don't have to go much into the detail. It's really only a few bonus slides. The idea is here to test the effect of an intervention in the landscape. So we are in the model world here, and we can do anything, and what we do here is we remove the grass component at the majadas and plant baby trees. And then we run that for 25 years, and we see what is the effect of that intervention on the carbon uptake. So that's how our baby trees grow. Here you see how the biomass grows, and here's the GPP, and then you can calculate. We have that for each of the carbon pools, but just have a look at the total, then we can calculate the difference. So we calculate the change over 25 years in the carbon pool, so that's the uptake then, and then we calculate the difference of intervention minus baseline. So that's the effect then of the intervention. And we saw, okay, that there was a bit of an uptake of carbon through the intervention, and now we have 2 cases. One is we have not done any data assimilation, so we did not constrain the parameters in the model. They still have their large prior uncertainty ranges, and we propagate these uncertainties then forward in the forecast, the 25-year forecast, and then you see we end up with a large uncertainty range. So that in that context, this value here is not so useful. But then, if we use the model after calibration against SIF, VOD, soil moisture, and FA-PAR, we get a reasonable uncertainty range. 5 minutes, perfect. So just as an example. Here is, that is something I wanted to show you. It's how we can simulate an equivalent of an observation on the observational footprint. So the starting point is a land cover map as a high resolution, and then we run for each for a given meteorological forcing, we run each of the relevant the model for each of the relevant PFTs, And then afterwards, we can compose according to the PFT fractions. We can exactly compose the signal that is seen in the footprint of the measurement. That's here illustrated for SMOS, but we can do the same for tropomi, and we know that the footprints are varying from overpass to overpass, and then we can aggregate, actually that is what we see at 100-meter resolution, and we can aggregate to the resolution of the footprints of the sensor, and at that level here, then we can make the comparison. And then with the calibrated model, we can also do forward runs at the resolution of the land cover map. So that is 100-meter resolution for an area around Majadas. So there's documentation for the system, manual with example, frequently asked questions, publications, and here we also list, that's the website, right? Here we also list when there are upcoming training events. Here's a list of training events we have already conducted. Here I highlight this one. That was in the seminar of our chairman, arranged by our colleague Pia Mailänder. And yeah, that's the summary. So the system provides an integrated perspective on carbon, water, and energy cycles. So today I focused on carbon, obviously. It can combine information from multiple missions with the process understanding in DNB, can monitor relevant variables, including gross and net carbon fluxes, continuously in space and time. We tested it with tropomi in preparation for FLEX. It's documented in open source, and you can get further information if you like. Thank you.
Yeah, there's time for 1 or 2 questions.
Thanks, Thomas. I really enjoyed the intervention experiment. I was wondering, I was not quite sure I understood. I saw the increase in the woody biomass, which makes sense, but I don't understand why you didn't see an increase in the root biomass and why you instead saw a decrease in soil organic matter. Can you kind of explain that?
Root biomass is I mean, the trees were growing, right? So that is, we can understand that. And soil organic matter, we actually see the effect of the initial state, right? It was, we did not change the soil organic matter, right? We took out the grass, put in the baby trees, but we only changed the living biomass. And so the respiration was still the respiration initiated by the grass, if you like.
Okay.
Any other questions?
I would have one short. I just noticed when you were presenting the prior, posterior and prior graphs for SIF, you had really, after the assimilation, quite a good posterior fit, but for FA par, it was highly overestimating. How can you explain a little bit why that could happen?
So the model parameters had to be adjusted to fit these 4 data streams simultaneously, and that is, as for FA par, then it was as good as it could do, I would say.
So the model is better in readjusting SIF than the broad flux of, I mean, than FA par in a way.
if you, yeah, or you can say the signal in the data matched better the dynamics in the model. Yeah. But you also see there's a large uncertainty range in the FA part. So in that context, we are not doing a bad job. And you see also the statistics here. They have improved quite a bit, the RMSE statistics.
Okay. Thank you. With that, I would like to give a hand to all the presenters once more, please. And we will close the session. The coffee is ready. We will reconvene in 20 minutes. Please be on time and enjoy your coffee.
Hello, everybody. Could you please take again your seats? We would start with the next session.
Can you come back to your seats, please, so that we can start in time?
Yeah. Yeah.
Okay, good morning. So we are sharing together, or I'm sharing together with Timon. And it's a session on bridging temporal and spatial scales by combining multiple data streams from Earth observation missions. And I'm not really sure why I'm doing it, because I'm always very skeptical when it comes to putting together different data streams. So for SIF, I remember at some point I said when we were talking about ECVs and CCI, that first you should walk before you start to run. And we don't have any FLEX data yet, and we shouldn't talk about ECVs before we have reliable SIF products. But then Christian van der Tol stood up and said, yeah, but if you want to fly, at some point you have to jump off the cliff, because otherwise you will never learn it. And I couldn't argue with this. So it's probably very good to do it, because at some point we have to do it, the community wants it, and we know that each satellite data stream in itself will have some limitations in space and time. So I think combining it makes sense. So I'm happy that we get a few interesting presentations this morning, and that we are not overlooking this topic. And our first presentation will be given by Shang?
Okay. Good morning, everyone. Let me introduce myself.
And for all speakers, just please stay in time.
Okay.
And we will give you a sign when you are running out of time. So thanks, and the floor is yours.
Okay, thank you. So just a brief introduction of myself. I'm Zhao Yinzhang, and I'm from Nanjing University, China. And I'm now visiting Max Planck Institute for Biogeochemistry with Greg Duvey. And Yong Gongzhang was my PhD supervisor, and he's now my colleague because he didn't get his visa, so I'm here on behalf of him to give this presentation. So the topic is retrieval of solar-induced chlorophorescence from Chinese Gong satellite. So the first part is satellite-based SIF remote sensing. And we know traditional remote sensing usually measures the reflectance. So we can use the reflectance to estimate the structure parameter and the biochemical parameter, and further the GBP of photosynthesis. So traditional remote sensing indirectly estimates the photosynthesis. But for SIF, because we know after the absorption of the sunlight, and the sunlight has 3 directions, for photosynthesis and for chlorophorescence and for heat dissipation. So chlorophorescence is closely related to the photosynthesis at the photosynthetic system. And we can use the chlorophorescence to estimate photosynthesis. It is a direct probe of the photosynthesis. And it's been a long time period for the photosynthesis measurement. And for example, at the deep level, we have the they call 68000. And at the canopy level, we have the FLEX tower. So for global level, we have the network. And for example, there are over 1,000 FLEX tower but they cannot represent the whole area of the landscape. And so we use remote sensing to monitor the global level photosynthesis. And they can use to, for example, estimate the APAR and GBP, NPP, but they are potential GBP or NPP. So chlorophyll fluorescence provide another aspect to estimate the photosynthesis globally. Then we know there are series of SIF products, and all these SIF products are designed for the atmospheric components monitoring, but not especially designed for SIF. And before the FLEX, we have already launched the GOMANG satellite in China in 2022, and it is called GOMANG. And so this satellite has a sensor especially designed for SIF retrieval, and it covers both red band and far red band. And the spatial resolution is 800 by 730 meter. So I will introduce this more. So it was launched in August 4th, 2022. It is called GOMANG, and it has a sensor especially designed for SIF retrieval. So this is the general parameters of a GOMANG satellite and its high spectral payloads. And it has a revisit cycle almost 5 days. The spectral resolution is 0.0323, and the spectral range is 669 to 780 nanometer. And spatial resolution 0.8 kilometer multiple 0.3 kilometer. And the swath is 33.7 kilometer. And so this is effective observations of the high spectral sensor payloads, and we see this is for 1 year, and they cannot cover the whole region of the globe. These are the effective observations. And then we want to test whether the radiance is suitable for SIF retrieval, and we just plot the radiance based on 1 pixel. We see it can clearly capture the absorption line. For example, the solar Fraunhofer lines and the atmospheric absorption lines, like we see the O2B absorption line and water vapor absorption line and O2A absorption line. So this data set provide high quality suitable for SIF retrieval. And the second part is SIF retrieval based on GOMANG satellite. And there are generally 2 methods for SIF retrieval. The first one is a traditional atmospheric radiation transfer model. So we know usually satellite measures top of atmosphere readings. And so if we use Earth's atmospheric absorption lines, we need to calculate the atmospheric parameter, for example, using the Moultrie model, and we convert the top of atmosphere readings to the surface readings, and then SIF can be retrieved. Another commonly used method is a data-driven model. And so the first we go with top of atmosphere readings, and we select a narrow window to retrieve SIF based on the solar Fraunhofer line. And then we conduct the SVD method, and we train the model like SVD or principal components on non-vegetation pixels, and we apply them on the vegetation pixels, and then SIF can be further retrieved. So for this satellite, we use SVD method, and we choose a retrieval window on the 743 to 758 nanometer. And we train the models based on like snow, desert, and sea clouds, and we conduct SVD, and we select 4 principal components, and then SIF can be retrieved globally. This is our first global retrieval of the SIF from GOMANG satellite. They are sparsely distributed for each month, but we still can see the photosynthesis phenology globally. Like if we see for the northern hemisphere, And in spring, the SIF values are relatively low, and it's gradually increase in and peak in summertime, and then gradually decrease in autumn and decrease to 0 in wintertime. And we further averaged this SIF values from different seasons into 1 year, and we see it can generally depict the spatial pattern of the photosynthesis. Like if we say your tropical regions, the SIF values are relatively high, and in east of the Americas, the SIF values are also relatively high, and in arid or semi-arid area, the values are relatively low. So we see the Gong satellite can generally depict the photosynthesis pattern globally. And then we want to further compare the Gong SIF with FLEX-Tower GPP and compare it with SCOPE-SYN-GPR. So here we define 1 kilometer buffer, and we find there are 5 sites have Gong SIF overpasses. So we all SIF values following the buffer were averaged to compare with the FLEX-Tower GBP, and we see the R square is 0.87. And then we define a 10 kilometer buffer because SIF has relative cost, special resolution. We need to use 10 kilometer buffer to average more SIF. And then there are more FLEX-Tower having SIF overpasses, and we compare the SIF with FLEX-Tower GBP, and the R square is 0.82. So the higher spatial resolution of the Gong can better capture the local vegetation photosynthetic activity. And then we further compared the Gong SIF with near VR for each month. We see they generally shows a strong agreement with the NRVR. And then we want to further compare the spatial pattern of the Gong SIF, and we then compare it with OCO2 and TRPOMI. We selected a region with all 3 satellite overpasses. And this region is ecological gradients transacting from the Indiana to the suburb of Chicago. And we see the Gong satellite outperforms OCO2 and TRPOMI in its ability to resolve the fine-scale ecological gradients. And then we compare the Gong SIF with TRPOMI SIF and OCO2 SIF based on per pixel. And we see Gong SIF shows strong spatial temporal agreement with TRPOMI and OCO2 SIF across most of the region over the world. And finally, we compared the Gong SIF with OCO2 and TRPOMI SIF for each vegetation types and compare their seasonal patterns. And in most of the vegetation types, we see the strong agreement among them. The last part, we did experiment, and we conducted the integrated satellite airborne ground validation experiment for safe remote sensing. In 2020 through September 11th, 10 a.m., Gong passed over Saihanba in Hebei province in China. And the shaded area is a Gong satellite overpass area, and we conduct the airborne flight at the same time of the Gong satellite to validate its SIF and radiance. And the blue line is the Gong overpass route, and we conduct the airborne flight at the same time as a satellite overpass satellite track. So we also designed another 4 airborne road to investigate the diurnal variation of the SIF from the airborne. And then we also selected 2 relative homogeneous areas. One is middle, another one is sampling. And then we installed the tower here. And we installed two towers for SIF measurements, and we also fly the drone over here at the same time. And then we get the results. First one is the blue line is the black line is SIF retrieved from tower, and it's the diurnal pattern. And the blue line is the SIF retrieved UAV without atmospheric correction. And the red line is the SIF retrieved from the UAV after atmospheric correction. And we show the red line is more consistent with the black line. And we want to emphasize that there's a necessity for atmospheric correction. We will use UAV to retrieve SIF. And we further want to ensure whether the airborne platform detects the fluorescence signal, and we select 3 vegetation types, and we see we plot their reflectance. We see there's a clear filling effect, which is a fluorescence filling effect. And then we want to further ensure the accuracy of the airborne radiance measurement, and we put 3 targets with different levels of reflectance, and we put there, and the airborne flow over there, and also the UAV flow over there, and we compare the readings from the airborne and the UAV, and we show they have high consistency. And this is a result from airborne, and we retrieved the SIF from airborne. And just take the cropland as an example, we show that they have relative low value in morning time, and this value gradually increase, and it reaches higher value in the noon time. And we could see the SIF shows the diurnal pattern from the airborne data set. This is another result of the airborne data set. And first row is the RGB, and the second row is NDVI, and third row is SIF. NDVI shows saturation effect, but SIF not. And we see SIF can generally capture the high photosynthesis area of cropland. And finally, we compare the readings and the SIF retrieved from the airborne and the satellite, and we see they show relative high consistency. So our data set from the Gaumont satellite are available on this website. So we are warmly welcome anyone who wants to download and use this data set and give us immediate feedback. So in the future, there are more SIF data sets, and hopefully we could do more. Thank you.
Thanks a lot, and also thanks for staying in time. I'm sure there are questions, because this seems like a look into the future. It's almost like FLEX. Yes?
Hi, thank you for the presentation. My question is regarding the UAV data that you collected. Maybe I missed it, but which sensor did you use? And when you said UAV corrected and uncorrected, what do you mean with corrector, or how did you make the correction?
Okay, so we use the atmospheric correction method, which is based on the motion model, and we calculated the atmospheric transmittance. So we corrected before to retrieve SIF. We corrected based on the radiance. At first, collect the radiance, and we did the atmospheric correction, and then we retrieve SIF. Thank you.
One more question? Yes?
My question was also about UAV, so half of the question has already been answered. Can you also tell us what height you flew those flights?
Okay, so around 1 kilometer height. Yeah.
Okay.
Yeah.
All right.
Okay, I think we will have a discussion session right after this session, so there's certainly room for more questions. I've got a very, very quick one. Are the level 1 data also available? So the radiance measurements.
It's not available. Yeah, just a SIF are available online.
But it will become available, or?
Because I don't know whether it will be available or not, so maybe in the future it will be available.
Okay.
Yeah. Thank you.
Then I think you will stay on stage for the second presentation as well.
Yeah.
And then it's about geostationary, if I understand that correctly, and about the diurnal cycle. So another interesting mission. Again, floor is yours, 15 minutes.
Okay, thank you. Another topic I'm going to show is diurnal variation in red solid-induced chlorophorescence retrieved from the temple geostationary mission. And we know most of the SIF products are polar orbiting satellite, and we except the O03 satellite, which is on board the International Space Station, and it provides SIF observations at different time of day, and it can provide the first opportunity to investigate the diurnal photosynthesis. So we did this work based on O03 in 2023, and this is one of our work about simulating the global flower band diurnal SIF total. And before doing this work, we convert the SIF observation to the SIF total because SIF observation is more sensitive to the sun target viewing geometry. And then we got SIF total, and we see the footprint of the O03 is sparsely distributed globally. So we wanna generate the spatial temporal continuous product. And then we use the some meteorological data set and FPAR product, and we train the artificial neural network to estimate the SIF total. And then after calibrating the model, and we applied on the referred data set, and we got the global diurnal SIF total product. So this is a flower band. And this time we want to further retrieve the red band SIF. So red band SIF theoretically contains more photosynthetic system 2 information, and it is more correlated with photosynthesis. But red band suffers strong chlorophyll absorption, and the signal is relatively weak. And for the red band SIF retrieval method, we know it's based on the O2B absorption line, and it's relatively narrow and shallow. So it's hard to retrieve red band SIF. So this time we wanna try to retrieve red band SIF based on the tempo instrument, and it is a geostationary mission, and it provides hourly observations of atmospheric components. And the spectral range is 295 to 741, and the spectral resolution is 0.6 nanometer, and the spatial resolution is 2 kilometer multiplied by 4.37 kilometer. And so we use a satellite to retrieve red band SIF. And this is an overview of the spectral coverage of the temple, and it scans from the west to from east to west. And for each scan, it generated 10 flares, and so each flare represents one region. So, and for the viewing zenith angle, it is fixed on each latitude, and from south to north, and the viewing zenith angle gradually decrease, so gradually increase. So we, in order to make sure the accuracy of the red band SIF retrieval, we only return footprint with viewing zenith angle less than 60 degrees. So we exclude the Canada area. And the spectral range of tempo is from the 293 to 641, and there's 40 nanometer scapping. And the green line, the SIF emission line in this finger, and the red SIF emission peak around 685 nanometer. So we use the SVD method to retrieve SIF, but we don't know which retrieve window is better to retrieve red band SIF, so we try these three retrieve window, and all these three retrieve window are on the left-hand side of the O2B region, and they have relative high atmospheric transmittance. This is a retrieval result based on the retrieve window 640 to 685 nanometer. We see there are clear strips distributed on the map. And it generally can depict the dino pattern, but not that clear. And then we change to another window on 650 to 685 nanometer. For this retrieval, we see the strips were clearly reduced, but we cannot see the higher SIF values in US compound. So theoretically, the SIF values in US compound are relatively high. So we don't find the phenomena, so we continue to change another retrieval window, which is 660 to 685. So this retrieval window is the same window as Philip used for Chupami red band SIF retrieval. We see the strips were clearly reduced, and then we can clearly see the high SIF values in American compound. And we also see the clear dino pattern, and like SIF value shows relative low values in the morning and peak in the noontime and gradually decrease in the afternoon. So we further evaluate the retrieval accuracy, and so we firstly calculate the R-square, and the range is from 0.5 to 1.5, and with median value 1.09, which is very close to 1, so which indicates that the model fitting performance is relatively good. And then the retrieval error, we also calculate the retrieval error. We know we see the retrieval error has a median value of 0.86. So this retrieval value is relatively high compared with far red band SIF. And then we further explore the red band SIF based on the tempo SIF for each vegetation type. And we see for SIF value generally shows the similar pattern, but for the needle forest and the savanna and the DBF, they show the highest value in the afternoon. And for EBF, grassland, they show the highest value in the morning. And cropland, they show the highest value in the noontime. But for the shrubland and wetland, the dino pattern is not really clear. So we will further investigate the reason behind this. And then we want to compare the tempo SIF with flux tower GBP. We select relative homogeneous sites because tempo SIF has relative cost spatial resolution, and we need to use multiple red band SIF to be averaged to represent this area. And so we define a buffer with a radius of 10 kilometers, and all tempo SIF falling inside of this circle were averaged to compare the flux tower GBP. And we see the result in the right-hand finger, and we see both SIF and the GP values shows the relative high values in the morning and relative low values in the afternoon. So the R square is 0.89. And then we continue to find another homogeneous site, which is a chopland. We also define a 10-kilometer buffer, and we compare SIF GBP diagonal pattern. But in this time, we found that SIF values shows relative high value in the morning and relative low values in the afternoon. But GBP not, it shows the opposite pattern. So we will further investigate the reason behind this. And finally, we compared the tempo red band SIF with also two SIF at far red band and then troponin SIF at far red band. Because this, we averaged tempo SIF from average scale to the daily scale. And we convert also two SIF from instantaneous scale to the daily scale and also the troponin SIF. We use the daily correction factor to convert it to the daily scale. And finally, we compare them and we show moderate R square between this. And the R square is 0.6 for OCO2 and 0.83 for troponin. And take-home message, so the tempo provides a first global, geostationary view of diagonal red SIF. And red SIF retrieval is feasible, but still affected by noise and stripping. And averaging all observations improves the signal, and it's linked to GBP. And in the future, we will further improve the retrieval stability and reduce artifacts. And we will further validate the diagonal patterns across seasons and years. So strengthen the links between red SIF and ecosystem photosynthesis. Thank you.
Thanks again. And again, we've got time for questions. Yes, there's one.
Hi, thanks. That was super impressive. Both talks were super impressive. For the tempo talk, I'm curious, what version of the radiance, tempo radiance, did you use?
Version 4. Yeah, I originally using version 3. Yeah, but version 4 is better.
Okay, yeah, what happened? Did I lose it? No. Did you see significant improvement with version 4?
Yeah, the artifacts effects are clearly reduced.
Okay, is there another question? Good. If not, I've got one short one for the for both talks. You did the comparison against FluxNet sites. Can we compare sort of the comparisons, or do we learn something?
Yeah, maybe we need to pay more attention to its spatial mismatch. Yeah.
Okay. Because I think this is one point maybe also for discussion, how we validate or how we compare a product that was data fused from multiple streams. Whether we do it at level 1, at level 2, and or at level 2, and how we find a common metric to quality control the data that go into a fusion product. So it was nice to see that in both approaches you used the FluxNet sites to compare. Okay. Good. And with this, I'm handing over to Timon.
Yes. Thanks again. The next talk will be given by Emiliano Carmona-Flores, and he will talk about how other hyperspectral imaging spectrometer missions will be complementary to FLEX and how they can work together.
Yeah. Okay, thank you. Yeah, this is a presentation we put together a few colleagues from the German Aerospace Center, where we wanted to share with you this information about these two imaging spectrometers where DLR is heavily involved And we think that can be of use with the FLEX mission. Actually, in the last few days, I have seen several presentations, that contributions or posters that they make use of Prisma, EMMAP, but I would like first to draw your attention to the DESIS instrument. This is a small instrument that was the result of the collaboration between DLR and Teledyne Brown Engineering, a US company, to be installed in the ISS in the MUSES platform that was built by Teledyne. As I said, it's a small instrument. The operations, the platform and the operations are handled by Teledyne, and DLR provided the instrument and the processors. What makes this interesting, perhaps, is, as it was mentioned in a previous talk by my colleague, Miguel Pato, is that the spectral resolution is somehow between it's not the final resolution that you will have in FLEX, but it's better than what you can achieve in similar imaging spectrometers. I mean, in this case, the spectral sampling distance is 2.55 nanometers. There is the possibility to group them through binning up to 10 nanometers, but you can have this fine resolution, and you will see how this is interesting, or could be interesting for FLEX. Other parameters is we have an spectral accuracy and stability around 0.5 nanometers. The platform, this is not a mapping instrument, it's something that has to be tasked, and the platform allows for off-nadir tilting between minus 45 degrees backboard, plus 5 starboard. The spatial resolution is 30 meters, also something that could be of high interest for FLEX. And yeah, the signal-to-noise ratio is 195 at 550 nanometers. The products of DESIS are tiled in squares of tiles of 30 by 30 kilometers. On the other hand, EMMAP is a different. It's different in the sense that this is a mission with much more resources. It's a German satellite. It was built from the very beginning with the objective to provide high-quality data. In this case, we have two spectrometers, one working on the Vernier from 420 to 1,000 nanometers. I forgot to mention before that DESIS only operates in this range, and SVR from 900 to 2,445 nanometers. Average spectral sampling distance in Vernier, 6.5 nanometers, in SVR, 10 nanometers. The full width half maximum, you can see it varies in Vernier between 6 and 11, 7 and 11 in SVR. Again, spectral stability is better than 0.5 nanometers. I will show some results later. The spectral SMILE is better than 0.2 nanometers, and signal-to-noise ratio is significantly better than in the case of DESIS, above 500 at 495 nanometers, above 150 at 2,200. Radiometric accuracy is better than 5%, stability better than 2.5. Actually, you will see much better than that. And we have to pay attention to the Vernier SVR co-registration, and in this case, the requirement was better than 0.2 pixels, but this is, yeah, it's even better in practice. With the again, we have off-nadir capability. It's not mapping, it has to be tasked, and the off-nadir is between minus 30 to plus 30 degrees, which allows a revisit time of, on average, 4 days. Again, the ground sampling distance is 30 meters, and our products are tiled in 30 by 30 kilometers. So the one main difference that makes them complementary is that while MUSES is in the ISS, what that means is that it is a non-synchronous, sun-synchronous orbit. We cover only between 55 degrees north and 52 degrees south. And then the orbit period is 93 minutes. The revisit time in this case is between 3 and 5 days, but depends on the latitude, and can be even in some cases up to 10 or 12 days. On the other hand, EMMAP is in a sun-synchronous orbit. The repetition cycle is 27 days. We cross the equator at the local time of 11 hours, plus minus 18 minutes. And the revisit time with using the off-nadir tilting capability is 4 days. With, you can restrict it to only plus minus 5 degrees, and then the revisit time will be 21 days. And in this case, we can cover between plus minus 84 degrees in latitude. So there are important differences between the two instruments. derived from the size of the mission. In the case of DESIS, we don't have much equipment for calibration. We only have 9 different LEDs in the onboard calibration unit, but still, it's good. It's enough to show that our spectral stability is better than 0.5 nanometers between measurements, and actually the RMS, when we make corrections for temperature, is around 0.1 nanometers. We can see that from the beginning of the mission, in the first year or something, there was a small variation of the offset in the spectral calibration, but then it has been very stable. It has not been stable in terms of radiometry. Here we have seen that the first bands below 500 nanometers have experienced a change over the mission lifetime with a special degradation of the first bands. But above 500 nanometers, we see that they have been pretty stable during the mission lifetime. The absolute calibration is done vicariously, and what I just said about the radiometry is something that we also see with the calibration coefficients that we derive from the vicarious calibration. In the case of EMMAP, it's very different because in this case, we have 5 onboard calibration and monitoring methods. We have a spectral, radiometric, lamp, linearity, and the possibility to look into deep space. And what we see from the spectral calibration on your left is that for Veneer and SBR, it is very stable. What you can see there is the difference in the spectral calibration for the different bands between consecutive calibrations, which are performed, monitoring, which is performed every 2 weeks. And actually, there has been no need for update the spectral calibration since roughly 2 years. In terms of radiometric calibration, this is done with the sun diffuser. And at the very beginning of the mission on Veneer, we observed during the first months what we call the degradation that reduced on average like around 8% or something like that, if I remember correctly. But since a few months after launch, it has been very stable, and you can see that the difference between the consecutive calibrations has been reducing, and we are now performing a calibration every 2 months, and the differences are, well, as you can see in the number 0.4, 0.3, 0.03 in the last one. In the case of SBR, it's a very different story. This has been very, very stable from the beginning of the mission, as you can see here. And the scale that you see, although it may seem similar, it's 10 times lower. We monitor the relative behavior of the different calibrations and the lamps, the LEDs, in the instrument, and if we use some point, arbitrary 200 days or 200-something days after launch as a reference, and we monitor the response of the sensor to the different calibration light sources on board, you can see how stable they are. The variations are smaller than 3% after 3 years in orbit, and it's roughly 1 order of magnitude smaller in the case of the SBR. So very, very stable calibration. What we have observed, well, depends on the orbit, of course. This is the footprint of the DESIS acquisitions. They are until 2024. I will explain later why. But you can see what has been observed. You can see that, for instance, Central Europe and Germany has been well covered because DLR was involved and there was interest in these areas. But there are other places in the world that have been observed up to 120 times. In the case of EMMAP, data has been acquired since launch in April 2022. We have now more than 200,000 products, and this is the coverage map achieved with EMMAP. The products, we have the similar processing chain. It's a little bit more sophisticated in the case of EMMAP, but essentially you have always an archive with level 0, level 1A products. Then we process them to top of atmosphere radiance, the level 1B products that can be ordered by the users. The ortho-rectified level 1C products, again, top of atmosphere radiance, ortho-rectified. The reference databases using DESIS and EMMAP are different. EMMAP has better accuracy. In the case of level 2A, they use very similar atmospheric correction based on PACO. And yeah, in the case of EMMAP, there is a dedicated level 2A water product. These are just some parameters of, in the case of DESIS, the top of atmosphere reflectance we can achieve around 5%, 20 meters spectral, spatial accuracy, and bottom of atmosphere better than 5%. The products are level 2A COS ARD at threshold specification, as well as they are the ones of EMMAP. In this case, 5% top of atmosphere better than that radiance. The geometric accuracy is actually better than 0.5 pixel RMS, with the nearest VR co-registration 0.1 pixel. Is half of the requirement. Some parameters of the requirements for land and water that we systematically check, and they are fulfilled. Concerning data access, the data are open. You only need to register in DLR to have access to the data. In the case of EMMAP, you register in the instrument planning portal, which also is used to submit acquisitions for EMMAP once you have a proposal that has been approved. In EOWeb, you find the catalog where you can order level 1B, level 1C, level 2A products with processing parameters that you can change. And we have also a service that offers level 2A analysis-ready data for direct download. The same is true in the case of DESIS, with the difference that the tasking is done on the Teledyne portal. However, what happened is that at the end of May, Teledyne stopped the DESIS tasking portal, and in the moment, although the instrument is still operational and continues to take data, and calibration data is received every week, it is not possible to task with that interface. The services at DLR continue to be available and will continue. And it's still possible to access all the catalog and not only the products of DLR, but it has to be untasking, but it has to be done through DLR, through us. You contact us, and my colleague Uta Hayden will take care of that. So the synergies, this is obvious, and it has been presented in some presentations. Obviously, the comparison of the TOA radiance, BOA reflectance products, it's something that can help the FLEX mission to compare with long validated instruments and processing software. And it's actually one of the ideas that will be exploited in this validation proposal in Germany that Julian presented on Tuesday. The EMMAP DESIS 30 meters final spatial resolution obviously can overcome some of the limitations of the 300-meter pixels in FLEX on heterogeneous areas. And you can derive from EMMAP DESIS stress indices, chlorophyll pigments, leaf canopy structure that could be studied, that could be then incorporated on FLEX for interpretation of the data, or maybe to improve the uncertainty estimation. Or you can use derive end-member libraries for F-cover with 30-meter resolution that can be of use with 300. Obviously, another advantage will be to create denser time series. EMMAP DESIS can be tasked with new acquisitions, with limitations in the case of DESIS, admittedly, but in the case of EMMAP, there is no limitation. In theory, we have this 4 days repetition cycle with EMMAP. Yeah. And then you have access to a long-term archive, which is of the order, it's 4 years in the case of EMMAP, 7 years in the case of DESIS. And definitely in the future, I guess there will be many opportunities for data fusion to combine the sensors, and maybe the algorithms that one day will be tried with CHIME can already be tested today with EMMAP and DESIS. In EMMAP, we have EMMAP Box, which is a plugin in QGIS that you can use to represent data and spectral data, and contains many algorithms that you can use with EMMAP data, but you can use on DESIS, Prisma, EMIT, Landsat, Sentinel, and PlanetScope. There are readers for all these, and it will be great in the future to have a reader for FLEX. And finally, probably the most important thing is that DESIS data has been successfully employed to derive SIF over the O2A band, making use of this realistic sensor simulation framework that Miguel presented before. These are the results. They are covered in a poster of our colleague, Jim Buffat. You have here the references, but the point is this is probably the only example of 30-meter SIF estimation from space that was verified with simultaneous high plant SIF data. So I think I'm over the time. So I just want to say that these two missions have similar characteristics, but also complementary, and definitely there is a high potential to enhance the results of the FLEX mission. Thank you.
Thank you very much. We have time for a question.
Yes, I have a question. Thank you for the very, very interesting. I have a question on the DESIS SIF that you show in the last. Do you know if it uses a similar algorithm as Highplant with non-fluorescent ground pixels, something like that?
I think the best to answer this question probably will be Jim.
Is he in the room?
He's in the room, yes.
It's not SFM, but it's a similar framework where we sort of replaced the least squares optimization with neural network training. You specifically asked for soil pixels. We don't make use of soil pixels. Yeah.
Okay, I think in the interest of time, we would suggest to move the other questions to the coffee break or lunch break. Thank you very much again. The next speaker is Yuxin Chang. Sorry if I pronounced it badly. It's about the cloud computing framework using Sentinel-3 and TropoSIF.
Okay, thank you. Okay, good morning everyone. I'm Yuxin Zhang from the University of Valencia, Spain. Today I will present a cloud computing framework developed to generate the first global 3-meter 4-day SIF product by fusing Sentinel-3 OC and TropoSYN-GPR using a random forest model on Google Earth Engine. As we know, SIF is one of the most powerful indicators for photosynthetic activity. The problem is resolution, which limited their use for monitoring especially heterogeneous landscape like irrigated fields. While there have been many downscaled SIF products, they all have limited resolution or spatial coverage. FLEX mission will address this by its 300-meter for spectral SIF data, but until then, the scientific community urgently needs the sub-kilometer dataset to develop the methods, the workflows that will maximize the FLEX scientific return. Another challenge is the computational cost of working with global high-resolution data. Our solution addressed this advanced way fuse Sentinel-3 OC, which already has a 300 meters resolution with TropoSYN-GPR through a random forest model running entirely with Google Earth Engine, producing a global 340 SIF product. And so in this study, first we generated our data and then validated it with against ground-based SIF data and as well as against the TropoSYN SIF data. Then we show that the 300 meters resolution resolves the landscape features, including the irrigated cropland and the constructing phenological patterns and climate zones. Our project matches the FLEX 300-meter resolution and use Sentinel-3 data that FLEX will fly in tandem with and provide a baseline for upcoming FLEX cross-validation. So to generate the data, first the target is retrieve the TropoSYN SIF using the 743 to 758 nanometer spectral fitting window. We choose this window because it's higher quality. Before training, we applied quality filtering, and then the filtered data would resemble to a 0.05 degree and aggregated to 4 days. And all the features are from the Sentinel-3 OC at its native 300 meters resolution, include the band 12 and band 13, which fall within or nearby the TropoSYN SIF retrieved window, and also the oxygen A absorption region that are very safe, sensitive band. Then the band 17 and 18, which help correct the atmospheric effect. Then we calculate several indices. One is a ratio between band 10 and band 15, which are located in the 2 peaks of the SIF. And another one is a oxygen A absorption depth and NVI and near VR, which has a strong relationship with SIF. And then the leaf calorific content and fractional vegetation calorie from the previous our developed Gaussian process models that are processed by Johan and by Pablo. And the mean radiance occurs 400 to 700 nanometer because they are photosynthetically active radiation bands. And finally, the latitude and longitude to give the geographic context for global generalization. Okay, so on the test set, the model performed well with the R-square of 0.76. Predictions closely follow the one-to-one line when transformative is positive. However, the high SIF value are underestimate, likely due to the property of random forest model called regression to mean, where the ensemble average comprises the extreme prediction towards the center of the training distribution. And the negative transformative values mainly caused by the retrieval noise are not well reproduced. The latter can be viewed positively because it suggests that the signal SIF captures the physically meaningful SIF patterns rather than the noise. So this, in fact, together results in a fitted slope less than 1. And to validate the seasonal dynamics, we compared signal SIF with tower-based SIF at 4 sets span 3 ecosystem. One is in Mahada, in Spain, Mediterranean savanna, and one is Xiaotangshan copland in China, and USNE2 also copland in the United States, and Hualai, mixed grassland and tree ecosystem in China. Across the four sets, signal SIF captures the seasonal circle, matching the timing and shape of the abortion. Here, our SIF value are consistently lower in observed magnet than the tower measurement, but it's an accept consequence of the spatial scale mismatch and the observation value. So moving to the spatial validation, the signal SIF and topolomy SIF have great constants at the global scale. Both identify the same SIF cosmos and low SIF region. But also there are some differences. The signal SIF tends to show slightly higher values in the Amazon and slightly lower values in over Europe. According to the pixel-wise R-square map, the highest agreement is in the temperate copland achieved R-square above 0.8. In boreal forest and the grassland, the R-square fall in 0.4 to 0.6, and in the arid region and tropical forest drop below 0.4 may reflect the foundational challenge of satellite retrievals in this environment. And over the annual cycle occurs 8 main vegetation types. The blue line is signal SIF and the orange line is topolomy SIF with a shaded band of 1 standard deviation. The signal SIF shaded bands are consistently narrower than those of topolomy SIF across all the vegetation types, which indicate a reduction of retrieval noise. The strongest R-square values appear where seasonal dynamics are sharpest, like in the deciduous buried and needle-leaf forest and coffland and grassland, where spring growing up and autumn filling create large, clearly safe swings that random forest can learn reliably. And the weakest agreement is in the evergreen broadleaf forest, probably the complex tropical environment with a relatively flat seasonal SIF single, making both training and prediction challenging. And here we show the monthly SIF maps and 300 meters resolution in Iberica Peninsula for a fine-scale, detailed spatial study. From January to March, SIF is near dominant across the peninsula, and April to June, there is a rapid growing up as the temperature rise, and from July to August, there is a most striking transition in the central and southern peninsula. The hotter summer Mediterranean domain SIF values decreases sharply. Photosynthesis is downregulated due to the water stress. And in the sun maps scattered across the otherwise stressed landscape, we can see bright patterns or parts or elevated SIF. These are irrigated agricultural zones. So this shows the capability of the 300 meters product to capture the water management effect. This slide highlights the climate sensitivity of SIF SIF by comparing to contrasting carbon climate zones in the peninsula. In the hot summer, Mediterranean, in the central and the southern peninsula, which has wet winters and dry summer with strong water limitation, and the temperate oceanic along the northern Atlantic coast, which has more evenly distributed rainfall. And the SIF SIF clearly captures the patterns more clearly, where the Tropomi SIF reproduce the general seasonal pattern, but less distinct single, with a weaker summer decline in hot summer Mediterranean and a flatter prolonged peak in temperate oceanic, and due to the coastal resolution and maybe the higher noise. So we qualified the spatial advantage of SIF SIF using two metrics in irrigated cropland. The first standard deviation represents the average local spatial variability and show how much inter-details is perceived within the land cover. The second one, the sober gradient magnitude along the boundaries between the irrigate and non-irrigate areas, indicating age sharpness and how clearly the product distinguishes the transition between field and the surrounding landscape. Across the year, the SIF SIF show higher variability and sharper edges. The monthly average map for the August on the right provides a more visual example. So our SIF data is not a resembled variant of Tropomi SIF, but contains the sub-kilometer spatial information derived from 300 meters SIF observation. Okay, in conclusion, the key strength of this work launching is for implement in Google Earth Engine enable the generation of 300 meters global SIF product without local computing, and the framework is scalable and openly accessible. By using SNO3 OLC consistent with the flex mission flying in tandem with it provides a neutral bridge towards flexive monitoring. However, the random forest model shows regression to mean, so it estimates the high value, and the training was limited to Europe. Because tropomorphic retrieval quantity in tropical and arid region is relatively poor, which would introduce large uncertainty. In addition, the current products retrieve only far-right SIF, and post-2021 SNO3 data quality issued in Google Earth Engine limited its temporary continuity. Future work will focus on the for spectral SIF reconstruction using outer bands and enhancing the transparency through platforms like OpenEO, and finally develop a fusion framework with FLEX. And so in this study, we developed our SIF data, which has grown good agreement with both ground-based and tropomorphic, and our data resolved the sub-kilometer heterogeneity and showed reduced retrieval noise compared to tropomorphic. We hope that our products can be a direct bridge to flex mission by matching the resolution and provide a baseline for data like cross validation. Okay, thank you. I'm very happy to take any questions.
Thank you very much. We have time for a quick question.
Thanks. Yep, thanks. Quite impressive work. I was wondering, do you know, I would have quite some questions and I'll ask them later, but in the quickly, did you use also the land surface temperature or thermal information from Sentinel-3 in the work you did, or is it only from OLCI?
Only from OLCI.
Only from OLCI.
Yeah.
Okay.
Because they are available on Google Earth Engine.
Yeah. So yeah, okay. But you didn't explore it outside of it,
No.
because I think it could help a lot. Also, maybe.
Yeah, maybe on OpenEO or
exactly.
some other platform, it will be easier.
Yeah, but then there's other problems too. But yes, we should talk.
Yeah, we should talk.
Other questions? Yes, please.
Yeah, nice talk. So can your model consider C3 and C4 together? So if you show the time series in the United States, I found that there is a soybean corn rotation, but your SIF data was no difference between 2 years, but inside the SIF showed very difference. So I think there was a rotation of the corn and soybean. So I was curious whether your model could capture C3 and C4 activity together.
Let me have a look.
Yeah, here, see?
Yeah, here.
The next.
And
the next, there is time series.
Here, I didn't show the time series. Oh, okay. So the next one.
The before.
This one?
No. Back.
Back, okay.
One more back. Okay, here,
okay,
C.
Here, yeah.
C is the cropland, corn soybean rotation. And your orange line is yours, and there was not so much difference between 2 years. But blue dot, that is the measured SIF, and I believe 2017 is likely soybean, and 2018 is likely corn. So overall, my question is, your model seems to not include land cover as forcing. So I was curious whether your model could capture SIF between C3 and C4 together.
Here, I just, I think my SIF can capture the time series between the in the side, and for the future study, maybe we can have a look to the fan scale, the performance.
Okay. Thank you very much. I think we move on to the next speaker.
Yes, so the next speaker will be Kiki Deng. And you are posing a question whether drought stress is better to be detected from original measurements or from gridded products. If the answer is yes, I'm happy. If the answer is no, then we need to talk.
Yeah, I'm sorry for now. I will not have an answer for this question since, yeah, today I'm gonna present the so far status of my PhD study I studied last year and held by the Max Planck. And I also was, my project was supported by a next generation carbon and also partly from the Open Earth Monitor, which will later detailed maybe explained by my supervisor. And so today for my topic is, can extracting the fluorescence yield before grading can help the estimating the drought stress? Well, for these days, we multiple to say that SIF plays a sensitive response to the stress from the soil moisture, like from the drought for the solar radiation, which is mostly talked about here. However, comparing to the vegetation indices, apparently yes, because it's directed from the photosystem, which is give us a more direct signal from the health status of the vegetation. However, if we moving from the scale to from 8-day scales to the daily, it plays a weaker performance, and this brings the question for should we use a SIF or like SIF yield? As a SIF is a complexity, it's a complex signal of from live to the signal to the space. It can be first decided by illumination condition and also the plant health, and then the canopy structure decide the escaped photons to the space, and later the atmospheric condition and geometries will decide the signal captured by the sensor. So we call that SIF oscillation is a combination of a radiation, structure, and photophysiology and others. So with things like maybe a photosynthetic yield can bring us more direct condition of the stress response. And let us take in detail into the Tsupomi SIF footprint. Because of the orbit of the Tsupomi, it has bring us a daily different overpassing time, which results into the slightly different footprint, which can first decide the illumination of the different overpassing time, and also the contents inside this criteria, which later be calculated for the canopy structure. So we raise out a question: can we extract the yield before grading, and then to asking do it performs better? To answer this question, we use a method developed by Zheng in 2019, and we calculate the fluorescence yield by the SIF observations, mainly infrared, and also the PAR with a near V, which is near V PAR. The SIF observations, the resolutions can be from the 40 kilometers to 300 meters, which is now it's for the FLEX, and time resolution can be from monthly to daily. And for PAR, which is illumination conditions, we taking it as can be from 5 kilometers to 10 kilometers, which can be verified as geostationary from 50 minutes per day, and also can be hourly globally. And the canopy structure, which is more finer resolution of from 10 meters to 5 meters, and while the 10 resolution can be quite a little bit coarse. However, based on our consumption, we want to comparing to the moderate and spatial temporal resolution of the SIF. The PAR, we propose that we want a coarser spatial resolution, but accurate by overpassing time, fine time resolution. And we consider if the stress response is quite quite quick, then within this kind of time period, we think that the near view will not change a lot, which can see the time resolution can be coarse as a stable near view. And the data, so we built our data set. First, from the SIF far right, we mainly use the Sentinel-5P Tsupomi, but we use a different retrieval method. The first one is from an artificial neural network from Lidong last year, and also the classical product from ESA, from Luis Guantia, and another one from Caltech. And it's an interesting part to see here, like the neural network generated, the retrieval SIF is much more cleaner, so that's why we want to compare in different triple retrieval products here. And later for the PAR, we first consider the geostationary data from MSG Savory, which is every 15 minutes give us the observations mainly over Africa, but also the Europe with a 5-kilometer resolution. And next we're going to do thinking about the Area 5 land, which is hourly but a global. And the last for the near V, we first consider the Sentinel-2 with a 10-meter really fine resolution, but also we will consider Sentinel-3 and MODIS with a coarser, a little bit coarser, but not so much. So after we combining the difference of the fluorescence yield, how we decide which is better, we first direct compare with other SIF yield products generated or calculated by others, and the second, we would like to say, can we test with its sensitivities in the extreme events? For the SIF yield product, we use our colleague's product given by the Zhao Ying before, she presented before, and it is machine learning based interpolation method which use a SD sensor to interpolate to daily resolution of a MODIS based SIF observation. And for the extreme event, we use the heat is also by our colleagues. They define the extremes as a hot and dry compounding event over global and based on the Area 5 land, which cover 1950 to 2023, and which is pointed out here. It's a meteorological variables generated data set, so which means it's about the climate stress. And the minimum duration of this event, it is said, is about 3 days. So what's possible SIF yield changes maybe we want to see from our data? Just to defining the stress from the vegetation, we can say that the direction can be always from the right to the left, which is a decreasing of the fluorescence yield, but also the photochemical yield. However, because of the overpassing time of the tripomi, it can be also only observed from the middle, so which means these two patterns will be mostly we were observed, which is stress but not stress. So as the light increase, it's going to be decreased first, but after the stress, it will be increased back to the before. And if we have a severe stress, it can be decreased, but whether it will be recovery, it depending on the elasticity of the ecosystem. So we selected the extreme events mainly in Germany in 2019, and I labeled some city here to help you to locate the boxes I used in here. It's like one maybe like close to Bonn, and one is more than like the middle of the Germany near Leipzig and Erfurt. And I also use a 100-meter land cover by the companies, which they classified the cropland and also different forest. So, well, for my workflow, I served first for the boxes, I extracted the SIF observation with its footprint, the latitude and longitude boundaries. With this, I use the center and specific overpassing time to calculating the paths from the sources. And then I also use a lazy method to overall the near V images from the sources to select the clear sky for 1 day. And then we, based on the SIF observation footprints, we calculating the near V of this specific criteria, and then we calculating the SIF yield, and then we compare with other products. So here's a very preliminary results so far. Like we firstly, here is a closed evergreen needle forest, which near the Leipzig, and it is. First impression of me is like Area 5 based fluorescence yield is always higher than the 15 minutes and geostationary fluorescence yield, and also the Sentinel 5P. If you see from this side, it can be like Sentinel 5P based near V. Fluorescence yield is always higher than Sentinel 2 near V. However, we have the problems of the SO course, which is kind of hard to understand. And then on the trend of the SIF field overall, before this, the event happens, like the fluorescence field shows a similar pattern increase comparing with other products. Like it can be decreased a little bit and increase before the event, decrease and increase, and then it can be during the event can be decreased and then increase, and then after event it can like show the similar pattern but slightly different. Because of the different combination, especially here for the signal 2 area 5 fluorescence field, it's like it's a little bit different. So we solve the problems, and then we took deep into like what it happened of the different combinations, and we see like before the event, the SIF near V parts, like it can be decreased, and then it I'm sorry for here. It's always before the event it can be increased a little bit, and for the near V it can be so near V and also part can be increased, and during the event the SIF can decrease, and while the near V it has an increase first and decrease, but for the near V here, because we assume the signal 2 near V as a stable, so we only consider about the signal 5p near V, which is decreasing. So this different trend contributing to different patterns of the SIF field, which we are now still as a question here. And the question is, we have the stress we defined before is about the photochemical yield is decreasing, which is the direction is from this side. However, we have the extreme is defined by the climate conditions, so we don't really know if the yield is decreasing or not. So the direction is the first question I want to ask myself, and the second, if I compare the different criteria with the same length cover, it can be a different non-photochemical quantum forms to regulating the energy partitioning strategy. So for now, it's my results, and comparing to the take-home message, I was like more open to questions or recommendations, because for next step I will compare more different combinations and more heat data set with a broader length cover, but also a larger criteria. And also I was recommended by David from JULES. He recommended me to use a best par compared to other par products, which can be performed better. And also we're gonna integrate with the in-situ observation, may help me to define which the fluorescence yield the direction of the relation. And then finally to answer the question, if it is graded better or ungraded better. Yes, that's all. And thanks for listening here.
Good, I'm happy. Are there any questions? I think we've got time for some. I see a hand up in the back.
Thank you for your great talk. My question is about your SIF input data. I mean, when your input SIF measure overpass time, I mean the local time. If it is over the noon time, I guess the stress factor effect should be low. And then if the input SIF data's overpass time before the noon time, it should be the effect should be the low. So I'm just curious, what is the overpass time for your input SIF?
Yes. The mainly overpassing time of the SIF is from 11 to 14, but the triple SIF is around 1:30. So the mainly is afternoon SIF.
Okay, thank you.
Yes.
Okay, very good. I think we are overall almost in time. We've got one more presentation. So Timon.
The next talk will be from Gregory Deveillet, with a very nice title hitting the nail of this session, basically, discussing a roadmap for the study of diurnal dynamics and which role FLEX can play in that.
Thank you. And I hope there's not too much expectation on a definitive roadmap. This actually comes from a discussion. So yeah, I'm Gregory Duveillet from the Max Planck Institute in Jena. And this actually stemmed more from a discussion I started to have with people at Max Planck, some of the presenters that we saw before, Shishi and So Ying, but also others like Bastian and also Philipp Köhler in EUMETSAT, and Georg and Sebastian, who was showing things on daily cycle. And it pushed me a bit to try to think about how to go in this direction. Now, from Max Planck, I mean, to put the bigger picture again somehow, I mean, we've seen a lot of things on the local scale, looking on parameterizations and calibration, but at the end, some of the things is that we want to know is about this large effect on the carbon budget, no? That the land and the land use change with the lancing are one of the most variable things we have and that we want to catch, right? This is a bit one of the big arguments to get SIF, right, to get photosynthesis. But of course, carbon is not the only ecosystem service. We should not say centric to carbon. I think Uwe reminded us a lot that we're talking more about bioeconomy, using this for many other things. So it's important to remember that there's much more than carbon. And also that the landscapes are complex. And so it's inherently difficult to disentangle all these effects. Now, for that, FLEX will provide a great opportunity, I think, and I think I don't need to convince most of you here. There's many pros. No, it's a dedicated instrument to go for a proper full spectrum retrieval. It will allow us to go beyond simple relationships that were like clouding the past years with assuming that SIF equals GPP all the time and things like that. So we'll go beyond this phase 2 in this diagram of Moreno, no? And we actually go beyond and try to understand more things. And I think this is still fine spatial resolution, honestly. 300 meters, I mean, it depends from where you go. I did my thesis on croplands a while ago, and Modis and Maris were supposed to be the big thing. And then I moved more to the climate science, in which, you know, I mean, 5 kilometers for them is high spatial resolution. So I think 300 is still quite good, and you can distinguish quite interesting landscape elements. However, the big cons that we have, and that all of you also know, no? I mean, the thing is, for the things we do at Max Planck, in which we need to look at the global cycle, the global and patterns across the board, well, the low revisit frequency will not allow to establish like a monitoring capacity to see the pulse. So, I mean, there's no way we can go from there. And then we have this thing of the morning overpass, like it was just asked the last question. I mean, ideally, we would want to see more times on the day and to see stress events. So then I thought I would put this in a table a bit. So what would be the requirements, a wish list of a monitoring system if you wanted to have it based on SIF? And yeah, I mean, you could have these kind of threshold or target values, no, for like a threshold would be the minimum and target would be what we want. So I don't know, I'm not the expert on all those details, so maybe I'm putting some things that are a bit approximate and wrong, but basically FLEX would allow us to go clearly on some targets of getting the full SIF out, for instance, to look at fine resolution, I would say, having a good spectral resolution to get there. But of course, the big problem is this, no, as I just said. Now, why am I focusing on this diurnal cycles? The thing is that, I mean, for us at Max Planck also, this is another way of seeing data on flux towers, no, that many people are working on that. Well, here you see how, so basically you have the diurnal cycle here on X and the seasonal cycle on Y, and you're looking at carbon flux uptakes. And in some ecosystems, I mean, we could think European beach forests. I mean, sometimes the seasonal variations are of the same magnitude as the daily variations. In some ecosystems, like tropical forest, it's actually the other way. I mean, the diurnal cycle is the most important thing. Majadas that we've seen a lot also in these days, well, it's different and it's not symmetric, no? So also these are some plots from the paper of Sebastian that he presented us yesterday or the day before, yesterday, in which he's looking at 2 trees, and these are different days, types of days, as he mentioned. And you see that the 2 trees for different variables like APAR, the MPQ and photosynthetic efficiency, these things are not symmetric across the local time. So the diurnal cycle is important. This is my point. No, these are some of his plots, but we won't need to go into details on fluorescence. Also, Zhou Ying talked a bit about her work trying to reconstruct cycles and trying to get, for example, the midday depression. And she managed to look at in the Amazon, looking at the dry season, you can get from OCO3 some effect on the fact that you have an asymmetry in the daily cycle. Now, I think it is one of the next frontiers for land surface remote sensing, going more to the diurnal cycle. Because it's going to catch the fact that stomatas are closing when there is a stress. This is not too new. This paper came out in Nature Plants. This is a perspective that came out already 5 years ago. And they had mentioned, like, there's plenty of satellites coming up that can allow us to go into this cycle. And to tackle here, some of them are OCO3, and Nick was talking about this also, no? That we should perhaps exploit this a bit more. So I think for sure OCO3 contributes, but geostationary satellites should have a role. And geostationary satellites, they look a bit like this. Now, this is 1 day of the data we collected from Severi, an instrument on board of Meteosat 2nd generation. And so you see basically the things going up and down, the pulse of the day. And so, but of course we don't have SIF on board of these. Now, another point, and this is a bit strange that my slide got pixelized. I mean, at some point that I did something wrong when I saved it, but this is a slide courtesy from Philippe Köhler, also from EMETSAT, who has been using this also to show how atmospheric sensors are all increasingly being more attractive for land surface applications, because before they started using these things with GOM and Skiamaki, and you had pixels the size of Berlin. But now with Tropomi, Sentinel-4, 5, and CO2M, I mean, we're getting closer in between Darmstadt and a cornfield. That's the type of resolutions. And it's getting closer to the things that MODIS, VIIRS, and others are getting there. So basically, that's my point, is that actually, to get the threshold values, we do have already Tropomi, no, as a variable, as something that is satisfying a lot of these things. And all this calls for, I think, integration. I know it's not the nicest. I mean, ideally, we would want to make sure that we do things right and don't start flying too quickly, like Matthias Dusch was saying in the beginning, no? But on the other hand, we also have this synergistic capacity to put things together. And, well, a blueprint to integrate these things, I mean, I have some ideas. I don't have a solution right now, of course, but I'm going to present a couple of pieces of some projects that we've been involved in. One is in like dashed, because this is what Julian presented on the first day. This is not yet there, but it could contribute. And so I'm just going to talk quickly about a couple of pieces of ways to integrate things and moving a bit along. One point is this improved machine learning-based SIF retrieval by Dongli from TUM that Shishi mentioned in the last talk. And here, basically, he made a methodology to get another Tropomi retrieval that was cleaner. And basically what he did, the machine learning here, it's not about reconstructing SIF based on climate, like many reconstructed SIF products do, and which I would argue that's not so useful for I mean, if you reconstruct based on MODIS, then the information is in MODIS. We don't need to call that SIF. But here, it's not a reconstruction. He uses the machine learning in the retrieval to basically learn from OCO3 observations and to get something better, because OCO3 gets it better. And so he manages to reduce the noise in his retrieval, in his SVD retrieval, compared it with the one from Luis Guanter and the one from Caltech, and manages to have something quite clean, no? Something that looks quite good. I'm not the expert on this, so I would invite you to see this paper that came out last year, to get the details. But it has perhaps some potential. I mean, the question is whether we're throwing away the signal by doing that. But it might not be. I think there is something there. Another contribution that we're doing in this Open Earth Monitor project is a bit of it's linked to the talk a bit before, but maybe not in such a sophisticated way. But we basically wrapped up some old scripts I had done about spatial downscaling, but put them in the Copernicus data space ecosystem and with OpenEO to actually provide users a way to combine different data and on the Copernicus data space ecosystem and downscale lazily. The idea would be that if you want to combine different products together and change resolution, you can put a formula there that is user-defined, and you could change it. I mean, some people would use random forest. Here it would be more like a functional relationship that you put to associate the data, and it moves on a moving window. So we did, and this could be, we could actually at some point, these kind of things we could just compare with Flex once it's there. Basically, we have some notebooks there to demonstrate a bit the thing. It's nothing new really, but it's more like a tool that probably should be used. I mean, we hope it can be used by others. It's still, we're finalizing these things, but we also chose Spain, curiously, to demonstrate this. I suspect it might not be as good as what they showed before. The advantage here is that it is on the Copernicus data space ecosystem, and so actually, for instance, we use land surface temperature because we can get it there. No? This is a bit the work that Shishi just presented before to try to get to work on the individual footprints. So I'm not going to go into details. And this is the last thing, more on the next-gen carbon project that I'm involved in which here we're proposing something in which we would combine Sentinel-5P, the one from Dong, and use MSG Severi to get land surface temperature. I think we didn't talk too much about this also. But land surface temperature and shortwave radiation to get a SIF yield prototype, maybe something like basically what Shishi is trying to get. And we would try to combine with OCO3 and FLEX at some point. FLEX for the spatial, to see if we're catching the things right. OCO3 to see if we catch different times of the day. And for sake of time, then now the point is, okay, this is a nice combination of different things. However, we also have challenges because I'm talking about Sentinel-5, and here again, this graph got perturbed, but from Philip as well. But actually, one thing that not many people know, I think, or at least users like me don't realize so much, is that Sentinel-5, although 5P is the precursor, but Sentinel-5 will not be on the same orbit as Sentinel-5P. And so it's not going to go in the afternoon. It's going to have a morning overpass, which is a bit of a bummer if we wanted to get the stress on the afternoon. Also, the bands are not the same. And so this is a bit of a challenge. However, another thing that I think might be interesting to talk is that there is Sentinel-4, which is a geostationary satellite for atmosphere, for looking at the atmosphere. And again, according to Philip, we might be able to get something out of that. And I think that would be a nice complementarity to this kind of theoretical monitoring system, if we could do that. So to summarize, I think FLEX is a great instrument that will demonstrate the potential of fluorescence. I think this is what was mentioned in the beginning, that it should be there. We need to show. It took 25 years to get there, but now it's a point, maybe things will accelerate because you can show that it was worth doing it. I think it's going to be a crucial piece, but of a wider puzzle. It's not, I mean, as it is, we cannot also ask the agencies to just send plenty of flex. I don't think that will work like that, no? And then, but I think if we have a target to do a synergistic use of different instruments together to capture these dynamics, and maybe it's not to capture SIF exactly, but it's to capture this relative dynamics in the day, I think that's a bit of an aim towards where we should be going. And again, would just stress this point that I think we should try to get a diurnal signal or SIF signal, a useful signal from Sentinel-4 as part of a wider constellation of using efficiently the sentinels that we already have. That's all from me. And if you have any questions or if you want to contact me about different things that I talked about, I know I went a bit quick and didn't show so much detail, you can always contact me. So thank you.
Thanks a lot. A lot of food for thought before the lunch break, but we also have the discussion. So is there maybe one quick question on this particular talk?
Everyone is hungry.
There's one in the back.
Hey, Greg, that was an amazing talk. Thank you. I guess this is a question you don't have an answer to, and maybe more to the room. I think the idea of retrieving SIF from Sentinel-4 is great. Who's going to do it?
Yeah, that's the point. So here, I'm not capable of doing it, but I'm capable of advocating for it. I think some people, it's a bit of a question because, so I think we would need some funding, someone to try and do some prototype. And so I think this is a question more for NASA, ESA. If there's room for doing such kind of things, I think we can try something. We've been talking with Bastian here in Jülich that maybe there's some things that we can do. Philipp Köhler is interested as well, but it's not in their mandate. No, in EUMETSAT they have to do all these things for the atmosphere. He would be a great guy also to help, but we probably need to get some money together and to do a test and see what's up. It might not be as good as we hope to be, because the signal-to-noise ratio, there's a lot of issues there, but I think we should try. So for me, my call is like, ESA, please let me know where to write, who to write to, and what to do to stimulate that further up.
Okay.
Thanks.
I think it will come. Someone will do it. It will be the first time that a satellite data set is not exploited to the very last little piece of information. So it will come, but it's certainly good to remind space agency to invest money and to foster this, for sure. Good. With this, I think we have enough measurements from different satellites to start, to try to fly. We are ready to jump from the cliff, but all the data sets, they have their own individual characteristics. And something that I was maybe a little bit missing is uncertainties. For me, without uncertainties, it doesn't make sense to combine these data sets. So please don't forget the uncertainties. We had a very nice presentation from NPL, I think 2 days ago. And I think this shall be our guideline to put another value to each SIF estimate, which is really the accuracy or uncertainty you can retrieve it with. There are more questions which we can discuss, I think, later on, whether we should merge level 1 data and make that homogeneous more in terms of a fundamental data or climate data record, whether we do level 2, whether we have common protocols for validation of the individual products before we merge. These are all details we can discuss. I think there's a lot to do, but we are well equipped to do it as a community, or you are well equipped to do it. So with this, we would like to thank all the speakers again. I think we had excellent presentations. And with this, Marco, I think, do we continue with the discussion session right away? Do you want to take over?
I think I miss a round of applause for all the speakers first. No, thank you very much. Actually, Uwe, Matthias, please. Let's stay together here on stage because we have about 15 to 20 minutes. I think this is basically a sort of mini wrap-up because we've had all the purely scientific sessions, I believe, in these days. And now from this afternoon, as you might remember from the agenda, we'll move in a much more targeted discussion about the validation. Not that we haven't seen about validation, we have seen a lot already, but this afternoon and tomorrow morning it's much more targeted. So I would like to take the chance for, let's say, questions which have not been asked or answered, or to highlight, let's say, themes or elements which have not been covered in your opinion, or which would need more attention, and that we can how to say, further explore. And Uwe, I think you might have a couple of comments already to ignite the discussion if you wish, or otherwise just raise your hand.
Idea. Okay.
So to me, the big absent variable was how do we get from electron transport rate to GPP.
Very true. From a flex perspective, perhaps Matthias can also help me, but I think we really focused all, if not all, most of our energies into getting, let's say, the instrument, the measurement, and the level 2 products right first. And now it's a joint effort of you presenting us your ideas on how to do that, and on ISA to invest heavily into exploring this level 4 products, basically. We have, Christian has presented some of the developments in the current level 2, and this is clearly, let's say, linked to single observations. How much we can get in terms of, say, this next step from a single observation is, to me, not completely clear. How much we need time series, how much we need to go beyond even just the flex measurements. So, very interesting point for discussion if you have any opinions on that.
May I maybe take your comment, kind of triggered something in myself. Personally, I would like to see a good GPP product. However, GPP, we know from a physiological point, it's a complex product if you want to really forward model it. The first step is how do we get from fluorescence to electron transport rate, then include stomates to finally get to GPP. For this session, I would actually like to step one back, a little bit further back, because what I saw in all the talks was that you were all really motivated in getting the new SIF data from the satellites, and then you made a big step forward and you empirically compared this to GPP or to other important parameters. And I would also, for this discussion, would like to pick up one comment what Matthias said. How can we really make sure that we can compare the different data from the satellites across the different platforms? And one point which I was missing, I think you hinted it maybe, Matthias, I think we also need to look at the level 1 data, so the at sensor radiance data, really urgently. I totally acknowledge that you want to go to SIF first, but from all the comparison studies which we have done so far, I think the at sensor radiance data after calibration of the specific instrument are really important. If we then have a description of the retrieval, what you do with the at sensor radiance data to retrieve or to come to a SIF product, that's then the next step. So I would advocate or put in your head, I think minimum data which we need from my perspective would be at sensor radiance data after calibration, and then SIF products, and in between a good description of your retrieval steps. And then we can talk the next step to ETR or GPP.
Yeah, maybe one to Georg's question. I think our philosophy was not to include GPP because it's classically not a level 2 product, and ESA is not responsible, and the ESA ground segment is not responsible to do it. Right? So it's also a financial and organizational reason. I think the question is, do you have all the ingredients to come up with a smart processor for GPP at a product level 3 and 4? And if yes, I think we'll find the funding mechanism. In the disk, there will be some sort of, I think, a pot of money allocated to new ideas. So the disk is not frozen when we launch, but you can develop prototypes, and it's also possible to add later on new processors and new processing chains in the disk. But the philosophy from the beginning was always we stop at level 2, and GPP is not a level 2 product.
Yes, I also enjoyed presentations today with fluorescence from the different missions, and then comparing to yesterday, when we talk about the retrieval of the fluorescence, then there are now a few that will use the oxygen band. So it's FLEX, but also this is the 2 presentations of today. And then if Sentinel-4 is going to be investigated, it will also be an oxygen band retrieval. And now in the DESIS, I learned that this is 4th order polynomial is something with emulation. 4th order polynomial is what is used to do that. And in FLEX, the idea is to use a lookup table interpolation and correction. What I would be very much interested in to see some sort of a table with a comparison of these methods, and maybe even trying the other way around and try if what is done for this is how it works for FLEX, and if for FLEX is done, how it would perform on DESIS. Because then we can see what the strengths and weaknesses of these approaches are. In some way, I would like to see that kind of comparison, which may also help then to see what would be the best for Sentinel-4. So it's just a discussion point. I don't know the answer, but it's something that I would be interested to see, sort of a slide like that compares these.
Thanks. And in the context of ESA and CEOS, there is, say, there has been a number of intercomparison exercises, for example, for atmospheric correction, right? So ASICs or for cloud detection, masking. I think it would be, and your comment hints towards a similar, let's say, intercomparison exercise also for fluorescence retrievals. My first question to the community would be, what do we use as a reference data set? And I think we have, and which target variables do we let's say in terms of, let's say, target SIF variables, do we expect to compare? And I don't have the answer. I'm just asking to you. This is a community-based. This can only be a community-based exercise. So from our side, we can provide somehow the platform, the framework, but then it's about the developers of the different retrieval methods to join and to invest some resources into that, into the definition of the methodology, and then into running the exercise and comparing the results. But I think it's a very, very good point. Any other comments in that direction? Yeah, Jorge, please.
Yeah, I have a comment on this, or actually 2 comments. No, one of them is that the fact that on the disk, on the collaborative platform on the disk, it's meant for the community to bring their algorithms, to exploit them there on the FLEX data, and there will be also validation data to validate the algorithm so that eventually we can compare them. So that will be a possible strategy, let's say. You mentioned about this ASICs project or CEMIX for the comparison of atmospheric correction algorithms. Now there has been work a work on that using real satellite data, and the validation indeed was a challenging issue. We don't have validation data everywhere and stuff like this. And there will be a fourth phase now working with on this based on purely on simulations. So maybe that could be a way to go as well, to have a kind of simulated data set that we have perfect ground truth. Of course, there will be some limitations on those simulations as well. We know well that, but maybe that would be another way to go.
I want to change topic, don't want to pile on. I think that we saw over the days a lot of downscaling efforts to the leaf level. Sometimes we can maybe even go to the photosystem level. I have one remark to that. We urgently need to settle on terminology because I was really confused sometimes. I didn't know, is the SIF yield, what is yield, what is efficiency, what's FQE. So just a comment on that. But these are basically all products which are reaching the leaf. There is as well presented new activities, Calval activities supported maybe from national foundings and so on. My question is, do we have actually protocols for measuring consistently and as well equipment, which means some leaf level equipment measuring the variables which we want to validate? I know that maybe ESA can't finance the equipment development, but ESA could coordinate at least development of these measuring protocols within the Calval activities within which are ongoing, because I think this is essential and the focus is on of course SIF, top of atmosphere and so on, but as we will be downscaling, we need as well some standardized, robust data set on this.
Maybe I can comment or answer on this question. For the FLEX validation and for the higher level data products, which are, for example, called ETR, that's how far we are going. We are implementing a few leaf level measurements with established methods with a pump, for example, where we are working with a company to have really intercalibrated pump instruments available which would deliver data really on the leaf level. So there are some of these reference Calval measurements included at the moment. Speak to Bastian about this. However, we are also totally aware that we cannot do this on a sufficient number of leaves in a 300-meter pixel. So it will be not too high the stakes. We will have a few, but limited.
That was my comment about the high throughput device. Yeah. So everybody uses Lycors or whatever gas exchange and so on, but they take too much time. We may think about something what is a little bit simpler than Lycor, but can produce more data in a shorter time.
I had a comment on data latency. I was kind of very excited by all the talks this morning on the diurnal cycle and all the developments that have happened with the retrievals and the production of data and the opportunities to combine the constellation of SIF satellites together to get, to accomplish this roadmap of higher spatial and temporal resolution. And I think we've made a pretty decent case for the science that can be done with diurnal data. But I think from a more operational standpoint, if that data is going to be used to, inform decisions and management and whatnot, it has to be relatively low latency, which I think maybe is outside of the scope of FLEX, but together, I think that needs to be talked about. It's kind of a tough one, but I wanted to put it out there.
Yeah, I can only speak for FLEX. This is something that was very much constrained in the requirements in the mission requirement document in order to allow this, let's say, sort of next day implementation of whatever information we managed to get from the satellite. So we do have very strict requirements on latency. Of course, it's not near real time, but we do have in principle for the level 1. Look at my colleagues from the ground segment, but I think it's 18 hours and 24 hours for the level 2, but I might be wrong with the numbers off the top of my head, for the delivery to users. Sorry, just could you like pass the microphone to my colleagues, just Mark and Marine, just to correct if my numbers are wrong.
6 and 30, respectively.
Oh yeah, okay, even better.
So 6 hours for the level 1, 30 hours for the level 2.
Okay, I have a question. I missed a little bit this nice feature from the FLEX mission, which is having the 2 bands. And I miss a little bit what we will do with these 2 bands in terms of chlorophyll content, in terms of difference in vegetations.
I'm afraid I haven't got.
So you're having the 2 bands in the fluorescence emissions, in the red and the far red. Far red and in early infrared.
With FLEX or with?
With FLEX.
Yes.
I think so.
Yeah, no.
I'm correct.
Well, we have.
So you're having really these 2 bumps that you will look at.
Well, okay. So the instrument has like the high resolution spectrometer on covering both the oxygen absorption bands, and then the low resolution spectrometer covering from 500 to 780. So combining all these together, the FLEX-Fluorescence product will be full spectrum from 650
so you have
to
basically
780.
information on PS1 and PS2 together. So the red band is more on PS2, and the near infrared is on PS1 and PS2. It's a really interesting feature, and I would like a little bit of what we will do with this feature.
Well,
it's
from a
blank.
product perspective or from an exploitation perspective?
From an exploitation perspective.
Oh, great! Great question to the rest of the people in the hall. Yes.
Okay, I wanted to just follow up a little bit on the very good point that Zvinek mentioned before and answered. So first, I mean, there is clearly a really confusion with terms. I second Zvinek on that. And then going to the fluorescence yield. I see the leaf level fluorescence yield in a way is kind of the core variable we want to measure because it links to all the physiology on the one hand, photosynthesis, and then it's the kind of precursor of the signal that we measure from SIF. So, but then again, measuring fluorescence yield, we can deploy micropumps, for example, or have some monitoring pumps, but even like that, it's not trivial. You need to have a relaxed level or maximum level, and then the prevailing fluorescence. So it's something we have to really think how we want to measure it, what kind of protocols to do, and then also integrate many other measurements there. And I have to say we are developing some of these chambers, for example, to measure this over time that probably could be used in this community. And I would be happy to, everybody who was interested, to help in that development, because I think we are, this should be, I agree, with a community effort in a way, to decide how to do it together. But there is so much complication in all the processing the signals that we forget that the leaf level is also a complex system. And there's lots of questions there inside. The contribution of PS1 fluorescence, how the energy is partitioned between the photosystems. This is certainly not 0.5. It changes all the time. The contribution also changes. So we need clips, protocols that we can go and press a button and get it and measure it. And then we'll start to understand how it varies and include it in the models. So I think that's a to-do.
I have a question. As a student, PhD student, I have a question about Albert's comments and the high-level the validation issues. My question is about is that PAM measurement or leaf scale measurement is enough for the validating scope high-level product? I mean, for example, the FluxNet and GPP validations case, we didn't validate the GPP product at the leaf scale measurement. That's because all we know, the leaf scale and the canopy scale is totally different. So my question is, for the validating the high-level product, the PAM measurement is enough? And then for the question to Albert is that what is the difference between the leaf level and the canopy level energy partitioning? The key point. What drives the difference and what we should consider for that?
Well, I don't know. Short answer. But basically, this is a very key point that we are, when we are measuring, for example, going to this definition of terms, if we define the fluorescence yield, measure it at the leaf level with a PAM, then we know that's the fluorescence yield. But if we retrieve the fluorescence yield from SIF measurements on the canopy, this kind of fluorescence yield, it has a very different meaning. It's kind of an aggregation of leaves with very different levels of radiation and acclimation states and etc. So it's yeah, it's a complexity that I think we have taken the right step, just the first right step, which is do it as simple as possible, but there is a bit of more complexity maybe we should still explore. And this also relates to considering the three-dimensional structure. Perhaps we could just use some very, maybe what Zbigniew is developing, this very high detailed 3D models, and just to look at the sensitivity of all these factors, how they are aggregating. But yeah, there's no clear answer for that.
High-level product?
Maybe I can try not to answer it, but as Albert said, it's quite complicated, and we showed one way how we want to tackle that. And it's not only the PAM measurement, it's the PAM measurement in combination with flux measurements. And from my point of view, I mean, in addition to what Albert said with a split in photosystem 1 and photosystem 2, it's the spatial sampling. So we have many data sets from Albert. I think Georg also has a lot of data where we have PAM measurements together with flux measurements at one point, one location somewhere, but we have a pixel which is 300 by 300 meter. And last year in summer in Italy, we really tried to sample in space. But you also have to consider there's a time constraint because everything is changing not only in space, but also in time. So we do not have hours for collecting the measurements. For example, LAI, I can measure one day before, one day after. It's not dramatically changing. But all those higher level products like ETR or FQE, they are changing in space and in time. And what I said, we measured at one plant several leaves, and they are really different from each other. So it's super challenging, and I can only say we try now to establish a first protocol in FRM for flu. You can try this protocol, you can talk to us, we can develop something better, but it's the first try and there's no base available. So we started from the scratch, so mainly Christian and I. So if you have better ideas, please come to us. If you have data sets, as I said before, we are also open to use other data sets. But I think the key point is that we really need to think about a good spatial sampling scheme. Because this uncertainty in the values we cannot change because it's from the nature, it's in the ecosystem itself. So the instruments seem to be good, the PAM instruments, also the flux is well characterized. So we have to more think about this spatial thing, I think.
Good.
I think I gave our presentation 1 day ago. I think my protocol could be used to test the product. It's a kind of propaganda, but yes, I stood in the respective for 3 months from morning to the afternoon, and I collect for shady leaf and sunny leaf. I collect more than 100 samples in the footprint randomly. I think it could be accounted for 1 pixel enough. I think is a kind of particle could be reproduced if you want.
Very good. Yeah. Ah, Yves, yes, Yves and Marco, please.
I would like to come back to the question of that Catherine pointed out about the 2 bands of FLEX. I think that this is a great added value of FLEX compared to the other mission, but we can expect some problem of uncertainty with this, especially on the red band, because the red band has a strong reabsorption caused by the chlorophyll. And if we want to exploit the best of the 2 bands of the red on the far red band, and especially in terms of the distribution of light, for example, between the PS2, PS1, and also about the functioning of the quenching, which is just concerning the PS2 and especially the red band, we must be able to separate between what is coming from the variation of the PS2 quantum yield and what is coming from the radiative transfer, and especially the radiative transfer inside the leaf. And as we see, to my opinion, the current models that has been developed, this model had been developed a long time ago, before the FLEX, in the preliminary study of the FLEX mission. I think that the model are not currently capable of describing, I'm talking about the leaf model, describing the reabsorption of the radiative transfer inside the leaf. So if we want to exploit the best of using the 2 bands, especially in terms of biochemistry, in terms of fluorescence efficiency, I think it could be important to improve and to reduce the uncertainty on the radiative transfer of the leaf in the red band.
Any comments from Christian on that, and perhaps also on the current efforts on this correction for the reabsorption, maybe?
During the coffee event, I already had a chat, so we came to this conclusion, and so we have there are several models, like SLOPE was presented, Fluor spectrum, Fluor mod leaf, but we have the validation data is a bit limited, that we have to do it, and we see that the red, as also in the Tristan presentation, actually also shown that in low chlorophyll, in the red, there is some issue, and we don't know if it is to do with the absorption coefficient or with the representation of the model. So, yeah, there are still issues before using the 2 bands for the interpretation of the photosys PS1 and PS2. I think that we need to get a bit more clarity on.
I would like to just point out that we have 3-dimensional Monte Carlo models at the leaf level as well, but nobody really works with them. And they are even quite fast, but we struggle with parameterizing them. That would need to be really project specifically for this. And these type of questions could be addressed with this, let's say, 3-dimensional simulations better maybe.
Yeah, just a small erratum with respect to the previous discussion we have about the availability of level 1. It's 24 hours our requirement. We have more stringent requirements in terms of processing, but I said 6 hours. I was wrong. It's 24 hours. It's indeed 30 hours for the level 2. So I hope this is still the type of latency the community expects to be able then to use this data for early alerts and integrating into other type of systems.
I
Okay. Yeah. Uwe, you have any final
I
comment?
have one thought or vision which I would like to give the people for the lunch break, but only if you're ready to go for the lunch break. That's Louis, something before? Oh.
Okay, thank you. Okay, now it's working. I thought they were sabotaging me. Okay, no, just first of all, I totally agree with the discussion regarding leaf level measurements and the validation of models, which they're like the cornerstone of everything in FLEX, but not only FLEX, but everything that goes fluorescence. And I think it's a missing link and very important one. On the other hand, my comment here is regarding the amount of machine learning algorithms and AI in it. Basically because, yeah, they become very efficient. The validation has been done regarding a set of data, but I'm worried about the training. And it is an open question. It's like, I don't expect any answers now, but how do we train them? How do we choose the cases for the models, so to build up the models? And I think we had already some struggle when we were building the lookup tables for the atmospheric correction. And I don't know if this has been solved or not, because it haven't been shown. There's only the results, but not how they're built. I think that's something that should be clarified at some point.
Okay. So, what I wanted to give you for the lunch break, from my perspective, really exciting session. And if I pick up your talk, Gregor, this was, I think, a wonderful vision at the end where I could see, and also after the discussion, that in 4, 5, 6 years, we may have a time of fluorescence where FLEX comes over every spot on Earth every 20 hours, or 20 days, sorry, not hours, 20 days, delivers a really high precision 300-meter pixel. In addition to this, what I also understood, Sentinel-4 has the possibility to resolve the diurnal cycle with a 1-hour step. Not so precisely, most likely noisy, but this we can cover if we have also the uncertainties behind and the trust in the data if we have traced it back via that one data, so if we have a good trace back. Then we have FLOX systems standing on the ground, measuring really good diurnal cycles or continuous time series, however, only on a few spots. And then Sentinel-5 and other satellites also deliver data with different spatial, different temporal resolution. Wonderful. Vision makes me really happy. So this would be a dream. But then I ask myself, are we actually really prepared of handling this complex set of data? It will be a complex set of data. It will be sketchy, temporally, spatially, different projection, different resolution. So we had a few animations there, which gave me an idea, a glimpse of the complexity of the data set which we will have there. Even though if we have uncertainty data, even though if we have good metadata to trace it all back, can we really handle all these data in this complexity? And I thought for the lunch break, and then I'm silent, maybe sometimes it helps to think from the back. You perfectly said, for modeling GPP, we need the diurnal information because this is needed for our models. But what's with the other applications? For stress detection in vegetation, precision agriculture, early detection of pest spreads. Therefore, I will start to think about also from this thing. We want to use fluorescence for something at the end, to improve our understanding, for the regulation of photosynthesis, for the happiness of plants in agriculture. Maybe also this helps to come from the back. What do we need for the application? Which kind of data? With this, I'm silent. Thank you.
Great. Thanks a lot. I hope that this discussion will go on over the lunch break and the coming day. I think we have kept you a bit longer than expected, so I suggest we restart at 2:45 in instead of at half past. And we try to do it sharply though. Okay, enjoy your lunch and see you later. Okay, so it's time to start. So please take a seat. I think one of the lessons learned from the workshop is that if I want to start at 45, I have to tell the people that we restart at 30. No, jokes aside, thank you for being back basically on time. I'm very glad of some of the points which were discussed at the end of this morning, because I do hope that at least for some elements we will this afternoon provide some more insights, and between this afternoon and tomorrow morning be able to arrive at the discussion session tomorrow with a much more clear idea on both sides of the stage, how to move on. Always struggle with this. Doesn't like me very much. Okay, so we're talking about preparing for the flex validation, but this is not something which starts today, clearly. So there has been many years of discussion within ESA, with the MAG, campaigns which provided direct insights, test bench basically for protocols by combining all sorts of scale, temporally and spatially. Activities which have been presented to some degree and will be presented also later this afternoon to develop and test in the field already protocols to validate some of the Flex products, those which we are actively developing so far, and also inputs from discussions with the community, particularly in previous workshops, have certainly ignited many conversations and also managed to let's say narrow down some of the strategies. So today, where we are, we have a baseline which we can present to the community, particularly in terms of protocols, in terms of strategy, for then applying, so taking the data collected with these protocols and running them through the Calval tools in order to validate the future Flex measurements and products. But the process, this is my main message, does not end today. So we present the baseline, and this is the first of, I hope, a number of iterations that we will have with the community. In principle, for this afternoon and for tomorrow morning, the objective is to present the strategy that we have developed so far for the validation of Flex products, to collect feedbacks from you on these protocols, both from the measurement side, from the scaling side, and for how to use this validation, this measurement, sorry, and these products in the validation of the Flex satellite ones. We will clarify a little bit more the roles and expectations of all the parties involved, so the DISC, the validation teams, ESA, yourself, and also introducing more details which tools we are preparing and we're putting in place in order to exchange data and information between ESA and you and ESA, basically. So this afternoon we start, with a few minutes from myself, which are not in the agenda, but this will be very short, and we will start then with a presentation from the teams behind FRM for Fluo, which is this activity developing the protocols firsthand, and the DISC, about the whole concept, the protocols themselves, results from the campaigns and tools which have been developed for the validation. Then we will move to another presentation more in depth about what INSIF is, this international network for solar-induced fluorescence, particularly, let's say, recollecting some of the elements which have been presented already by Tommaso a couple of days ago and digging in a bit more details. And then again on the collaborative platform, last time you've seen, let's say, the concept. Today we will have a demonstration live from the collaborative platform team. Tomorrow morning, more on how we want to put all these elements together, okay, together with future campaigns and other elements which have not been introduced so far. A sort of a summary of where we are with the announcement of opportunity. I think I've sensed some, there are some questions around the AO. What is it meant? What is meant for? What's even the process? Will it be reopened or not? So we will try to clarify all this tomorrow morning, and then we will present one of the tools which we are developing for the interactions that I mentioned before, which is Confluence, basically. Again tomorrow morning. Then, very important for me, I hope that most of you will be there. We have 2 hours. Dedicated to further discussion and Q&A and clarifications about particularly these topics linked to the validation, but also others which have been covered in the workshop if necessary. But I would really want to use this time for this bi-directional feedback, basically. And then, okay, we will wrap it up for half an hour. What I want to announce is that as I mentioned, this starts today. It does definitely not end today. On the 11th and 12th of June, we are preparing the first Flex Validation Workshop. This will be a virtual meeting where we will clearly share an update on the latest news, let's say on the Flex status. This will be open to all PIs and co-PIs of proposals endorsed via the Flex Announcement of Opportunity, but this is not completely exclusive. Okay, so if you have an interest, let us know, please. We will ask all the participants to the AO, particularly the PIs of all the projects which have been endorsed, to report on the status of their projects in order to discuss together, identify which are the gaps, and foster potential synergies in between the groups and in overall with the activities that we are covering, and hopefully converging one step more towards a common understanding of which protocols to use and a common adoption of these. With this, I'm finished with this very short introduction, and I leave the floor to Roberto Colombo and then to Tommaso for the next presentation. Thank you very much.
Okay, thank you, Marco. Okay, so the main goal of this talk is just to share with you what we are doing in the context of DISC mainly, and in the context of another project that is called FRM for Fluo. So basically, we would like to inform you about the strategies, the overall strategies that we are following for the validation of Flex. So basically, the talk is split in my presentation related to the Flex validation overview, product approach and documentation, providing some good practice and recommendation. Then Tommaso will explain good practices at the laboratory and field level, and then I will conclude with some example of the Flex upscaling by using real data. So basically, this is just to summarize the products that the mission will deliver after the launch, and basically, besides the radiometric data at level 1C, level 1B, the most important, I think, for the community is the level 2 data. And basically, we have the new parameters, I would say. I would say that this is an Earth Explorer mission, and beside fluorescence, we are also delivering some novel parameters that have been never produced in previous missions. So basically it's something that we develop and will be always in development phase also after the launch. So basically we have a surface apparent reflectance, so which contain also fluorescence, and one important parameter is, for example, the at surface solar irradiance, and this product at ground level has been never delivered, so it's something that could be useful. Another one is a lens surface temperature derived by Sentinel-3, fluorescence, of course, plus the decouple of reflectance, so we will have also the real reflectance. And then we have traditional biophysical parameters that are produced also in other missions like leaf area index, FA-PAR. But it's also interesting, also with regard to the discussion that we had this morning, to underline the novelty of some photosynthesis-related parameters, because we are providing PS1, PS2, MPQ, and this kind of parameters has never been produced. And one important point is that all the products will be generated with an associated uncertainty. In general, this is a general overview of what we are doing for the validation of all the different products, since we have a lot of products, to exploit an umbrella of possibilities. So the first one is based on the quality control test. That is something that is more internal at the beginning, and it will allow us to understand if there is something wrong. Then we have a dock quality assessment that is something that is not automatic like the first one, and currently is expected that all the external support laboratory involved in the disk will check the image that they will receive, and by a visual inspection they will provide the feedback to ESA in order to evaluate the quality of the product in a preliminary way. And the last, that maybe is most important for the discussion with all of you, is the validation by the so-called Calval tools, that are some tools that are generated automatically by the disk and will be included in the collaborative platform, so will be also used by the community. And I hope that in the collaborative platform, at the end of the story, there will be also additional tools that are developed by the community in order to improve the interaction between what we are doing as disk and the overall community. This is at least my wish. And the validation that we will perform by using these Calval tools can be done following two different approaches. One is that we selected reference networks, so basically we exploit the current reference network. Let's assume, for example, that for leaf area index we can benefit from the GBOV. So GBOV is a very good network, and we can ingest the data by using an API that has been developed ad hoc, and we ingest the leaf area index, and we make the matchup, and we validate the leaf area index. And this is the same, for example, for the atmospheric characterization with the AeroNet networks or other lens surface network, or with in SIF network for fluorescence. And this is something that is established by the disk. But at the same time, what we are doing is also to create some Calval tools that will allow to make the proper validation of different products of Flex by using field data collected in ad hoc campaign that can be collected by using single point measurements or by drones or by airborne campaigns. And I think that in this context can be useful to discuss together about which are the protocols that can be used, because we are proposing something but it's not hidden in the stone. So I think that if we receive a feedback, or as suggested by Mark last day, if we think to do after the commissioning, I don't know, something like a round-robin exercise, I think that can benefit everybody, and if we arrive to converge to some common protocols, this is the main wish. Okay, so this is the overall approach that we are following. And just to underline what I already explained or presented the last time is that we are following a different kind of approaches. Basically, we are considering the so-called category A, B, and C. So it means that, let's assume for fluorescence that is quite easy. We are measuring in a certain point with flux. The flux is a specific owner that located the flux in a certain position without considering the exploitation of the flux for Calval. So basically we have to deal with flux that are accommodated for other purposes, but we have to exploit for Calval. So I would like to exclude maybe one flux that is accommodated into the garden of someone, but in principle, if we have some flux that is accommodated in a small agricultural field, we can try to benefit from this flux. So basically we, in principle, try to include all the instruments that are available to participate in SIF. And for example, by using one flux, we can perform the so-called direct comparison. That it means that we compare directly the ground measurements with a region of interest that could be at least 2x2 or 3x3 pixel, considering also the error of geolocation. And in this case, we can compare directly the measurements or by using something that we call transfer function that is able to expand the single point measurement that maybe is on 1 meter by using, for example, additional satellite data like Sentinel. We spread out in a 3x3 pixel these measurements and then we compare these measurements with what we got from satellite. And then we have a category B that is in indirect validation, and it means that we can exploit a forward scheme by using, or an inverse scheme by using a radiative transfer model like SCOPE. So it means that, for example, we invert the model, we derive FA-par, for example, and we compare the results of the model with the satellite data. So this is not a direct measurement, it's an indirect comparison. So it's another approach. And finally, we can also make a validation, exploiting other satellites emission. For example, always thinking about leaf array index, for example, we can compare with leaf array index that is generated by other missions, or fluorescence can be compared with OCO3 rather than tropomi and so on. And basically, one important thing that we considered when we planned this exercise is that the same variable, so for example, always FA-par, can be validated according to different categories. So maybe we can validate FA-par by using direct approach or by using an indirect approach or by using a comparison. So we have more than one possibility to make this comparison. And this is one point. The second point on the right side is that we were thinking in this Pandora box how to validate 3x3 pixel. That it means that we are working with 1 kilometers. And basically, the idea is to try to exploit different strategy. And this strategy can be based by single spot. So single spot can be related to one single measurement in the ground. So flux is accommodated in one site, and we try to evaluate, to exploit this single spot. Otherwise, we can exploit multiple spots. And this is always in the context of a field spectroscopy or airborne spectroscopy. In principle, we are planning to exploit more than image system, field spectroscopy systems. So maybe we can accommodate one spectrometer on board of an airborne or a drone. We sample in space, and at the end we will have a transfer function to extrapolate the data at 3x3 pixel, and then we can make this comparison. Or another approach that we are following with our Calval tools is to have the so-called mapping measurement. So we will exploit an airborne survey, we will do an overpass in a large area, and then we aggregate the airborne data at the spatial resolution of FLEX, and we make a direct comparison. And this maybe is one of the best one, because we are oversampling the area, and this can reduce the uncertainty. So we are using all these strategies. And to do this kind of to apply this strategy, we defined a lot of sites, and each site correspond to the variable that we want to validate. So for example, we have some reflectance sites that will be used for the validation of surface apparent reflectance, and the input data will be based on HyperNet network or by using the in-SIF network. For example, the fluorescence will be validated according to different strategy by using the in-SIF network, and so on. And this information will be provided in the collaborative platform. So if I have to close my eyes, I think that at the end we will have a WebGIS. You click on a specific point and you see, okay, this site is being used for the validation of this variable, and so on. Okay, and this is a first attempt to provide information, a recommendation about how to define the spatial homogeneity and the spatial representativeness of a certain site. So for example, let's assume that there is an owner of of a flux, and this flux is accommodated in a certain place. And in principle, I am quite reluctant to avoid the inclusion of this flux in the collaborative platform. So the first exercise is to evaluate the spatial homogeneity. And if we have to translate these semantic words in something that is a statistical matrix, currently we are using the coefficient of variation. And this coefficient of variation can be computed in a different way. So for example, always thinking about fluorescence, what we are doing is let's try to compute a variable that can be considered as a proxy of fluorescence. Currently, what we are thinking is that the near V rad computed by Sentinel-2 could be a reasonable proxy for fluorescence. So basically, we take the Sentinel-2 data in space and time. We compute within a certain region of interest the near V rad, and then we have to put a threshold. So basically, when we are considering peaks in radical net, I don't know, there is Mark and Bea here, we are considering a coefficient of variation that probably is less than 2%. But in vegetation, this will be difficult. So I think that we'll be more relaxed with the threshold. And probably what we will call at the end homogeneous site will be with a coefficient of variation that probably will be less than 20%. Because if we have to find something that is homogeneous with a coefficient of variation less than 2%, probably we don't find anything. And the second point is, but the measurements that we are collecting in a certain point can be representative of a large area. And to reply at this question, we are working in the context of the spatial representativeness, and the spatial representativeness can be computed according to these two statistical metrics. That one is the so-called relative coefficient of variation, and the other one is the spatial representativeness index. And basically what we are doing is to compare, for example, the area or 30 meters. And we are wondering if we sample in the area of 30 meters, is enough to characterize the area of 300 meters? And this is useful for our perspective, because let's assume that we have a multiple spot acquisition by using drones, and this is almost impossible currently with the logistical constraint due to the battery to fly 1 hour or 2 hours. So basically, if you understand that this site can be sampled in a small area, but this small area is representative of a large area, we can find a way to sample a small area, but to make the match-up in a large area. Okay, so this is the first point. The second point, this is, I don't go into the detail of all the products because otherwise we become crazy, but this is just to provide you an overview of the fluorescence. And this is the overall strategies that we were thinking to apply. So basically, we developed different approaches, and the first one could be based, for example, of the so-called level 2B SIF single point. This is something that I explained before. Let's assume that we have only one flux and we have to compare at a larger area. And this scaling approach could be done with or without a transfer function. And with a transfer function, we extrapolate the data in a larger area and then we compare. Then we have developed other tools that are called the level 2B fluorescence multiple points. And these are also based on airborne spectroscopy. So we accommodate one flux or like flux-like on an airborne platform or a drone platform, and we sample in space according a certain protocol, and we will produce an interpolation, and then we will create the matchup. Another solution that we can exploit is the Calval tool based on the ingestion of an airborne data. And in this case, what is recommended that the community can fly with a certain airborne data, with a certain image spectrometers. Then the community can compute the fluorescence, for example, in the red or in the far red, and then the Calval tool will receive as input the fluorescence map, but the Calval tool in automatic will be able to generate the matchup. And then we have the possibility to exploit also a comparison with other satellite data. So as you can see, the main message of this slide is that there are different solutions for validating the same variable according different protocols. This was the original strategy because it's impossible to have only one solution, in my view. Okay, so for single points, we can exploit the in-SIF network. For multiple points is something that there will be opposite sites where we can sample, for example, by drones. For airborne with an imaging system, we will have maybe other sites, or for satellite intercomparison, we can select other sites. But the collaborative platform will be able to receive all this data. This is the story. Okay, this is, for example, one solution that we can try to offer to the community to discuss with you about the fact that the flux, for example, I still continue talking about flux, but could be also another instrument. The logic is the same. Let's assume that now I am the owner of the flux and I can decide that I can install this flux for Calval purposes, not for garden purposes. So I can try to follow a recommendation where to install the flux. And what we have developed, it is kind of a solution that is a Python tool that is quite is fast and is able to find the exact position within a certain window that you have to pre-select and to accommodate the flux in a certain position in order that the average value of the variable that you are considering, in the case of fluorescence could be always the near V, is close to the average value of the region of interest. And as you can see, we avoid the border just because the PSF is very low, and we are weighting in a proper way the central pixel because the PSF is larger. And this could be something that maybe can be improved, but at least is a starting point. Then, related to the sampling approach, what we are proposing is to exploit in the case of multiple points. What we are proposing is two solutions. One option, or the option one, is let's assume that we want to do a random sampling approach. If we have an homogeneous area with a Gaussian shape of the variable that we are considering, we can derive the number of points by using this simple formulation. So basically, we have to know the confidence level, and we can put, for example, 90.5% or 90%, depends. We know the standard deviation because let's assume that we are always considering the near V computed from Sentinel-2 in a certain area. What is difficult, at least for fluorescence, is to know the associated error that we want to include, because if we are working with the Sentinel-2 near V, we cannot include in this formulation the uncertainty of the fluorescence and to put 0.2. We should know the uncertainty in the near V. And this will help us because can allow to put a certain number of instruments to have a desired uncertainty. The second option is that we decide to select an optimized spatial sampling. So now, as quite often happen, for example with drones, the people knows that one of the limitations is 15 minutes of battery, so more than 10 points I cannot do. So basically the input now is that we know the number of points. And if we know the number of points, we can define an optimal location of the points according to an optimization approach that we selected a genetic algorithm. And basically this is the story. On the right side you can see the number of plot according, in this case, the error in fluorescence. And you can see that, of course, when you increase the uncertainty, the number of points will increase. So you have the red line and the blue line are simulated for two different uncertainty values. Let's start from 0.2, but if you put 0.2 in the spatial representativeness, you completely exclude other uncertainty that can be instead related to the temporal of the temporal domain. And then this is an example of the optimized spatial sampling. And you can see that after a certain number of iterations, starting from a fixed number of points, I can give you where to locate the points into the space. So this can be useful if you have to plan your drone survey. This is another point that is related to the temporal uncertainty, because when we are considering also flux measurements in a continuous way, or when we are considering to collect data with the drones, we cannot include in our Calval tools measurements that are collected after 2 hours. Or if we want to include measurements collected after 2 hours, we need to know the uncertainty associated. So basically we did some tests, and I think that everybody should do this test in his Calval site. And at the end we tested the different solutions. So what happens in 3 minutes versus 10 minutes? What happens in 5 minutes versus 10 minutes? What happens in 15 minutes versus, just to check the relationship. And when the scatter increases, it means that these measurements cannot be included. And basically, after a certain point of this kind of iteration, our first rule of thumb is that if we consider plus or minus 15 minutes at the moment of the satellite overpass, this could be considered reasonable. But if you are acquiring data after 30 minutes, let's assume 45 minutes, we have a backup solution that is to incorporate this simple equation that has been proposed in the past by Philip Kohler and Christian Frankberg that correct the fluorescence measurements according the time of at what you have collected the data. Then another important point that was also raised by Matthias today is that the matchup will be evaluated by considering three primary sources of uncertainty. And this is what I would like to have in the collaborative platform, that all the measurements that will be used in the Calval tool will be collected having an uncertainty that is associated. And if we have an uncertainty that is associated with the flex product, that is associated because we are generating the product with an uncertainty. Then if we know the uncertainty of the reference data, and then if we know the uncertainty that is introduced in the match-up process, that it means that you should know, for example, the angular, the spectral, the spatial, the temporal, this kind of uncertainty, basically we can compute the so-called equivalent ratio, and in this case, when the equivalent ratio is less than 1, putting k, that is the coverage factor, equal to 1, we can say that there is the comparison is within 95% of confidence level. So basically, to summarize the story, I believe that to do the validation of Flex, we have to exploit both spatial and temporal domain. So we have to use an automatic system like FLOX. This is for the bidirectional fluorescence distribution function, but with the SWOT that we have, we can skip this problem at least for fluorescence. And we can exploit point for temporal and drones or airborne for capturing the spatial domain. And what I explained now for fluorescence, please consider that is also in progress for the other variables. So basically you can see in the first column the variable, in the second column the Calval tool that is associated to the validation of the variable, and in the third column the sites that are available for the validation. We prepared a lot of documentation that are still in progress, but you can find that was also associated, if I'm not wrong, Marco, with the announcement of opportunity. And basically, another important point before concluding my talk is the document on the right side. That is an important document because in this document is written the data format that in principle should be considered from the people when they are collecting the data into the field. Because if we are collecting the data with the same protocols, maybe it's better. So here you can find a preliminary idea in the last document. Okay, that's all from my side.
Okay, thanks Roberto for the introduction, and yeah, this other part is basically related to the protocols and the guidelines that we were sort of developing as part of a project which is called FRM for Fluo. You have heard this. FRM stands for Fiducial Reference Measurement. So the idea is that with this project we are trying to provide guidelines to the people that are making the measurement in the field, to develop really some protocols that can be used as a real document that we are providing at the end of the project. But also the conceptual scheme of this project was to start from the theoretical idea of how to make the measurement and then test these ideas with campaigns. So we made also some field campaign. The project is still running. We are close to the end. It was a 14-month project. So we try to do as much as possible, but of course this, as Marco was saying, is a starting point, I would say. Then these protocols I expect to evolve in time. This project was involving different partners, and what we did was really make a campaign trying to scale up everything. So we did a lot of measurement on the ground, like 7 fixed instruments, then a couple of UAV, plus another instrument mounted on an helicopter. That was funny. And the aircraft. So we really tried to cover all the different scale. And yeah, and the expected output of this project that should come soon. The idea is that we are finishing them next month or this month, and will be available. And the idea is that there will be information on how to set up the instrument, calibrate the instrument as well, and then upscaling. And this should be covering different product level. Here is called level 2A, B, and C. Level 2A stands for basically for reflectance, solar irradiance. Level 2B is fluorescence, and level 2C are the higher level product. It's a pretty complex story, so we're trying to cover basically everything from the instrument to the laboratory. So in terms of instrument, basically which are the characteristics of the instrument, the design, because this is important to understand also the uncertainty of the measurement that you are getting. Another part is related to how good you can calibrate the instrument, so really get the radiance out of it. But also, if you do everything perfectly in the lab, sometimes you go in the field and you face some other problem of the setup, and this can really affect the measurement. And of course, if you then want to make a match-up with a satellite, you need to precisely choose the site, as Roberto was saying, try to capture also the spatial variability. And then, of course, another key point is the data processing, because also you can have some uncertainty related to the data treatment, the retrieval, and so on. And finally, the last part was also of the project, try to really go in the direction of a match-up with the satellite, even if the satellite is not yet there, but we try to make that with other tools. So here, well, what we did basically was using at this moment few instruments. We couldn't do the characterization of everything, so we did that with the flux and the air flux, which is basically a lighter version of it that can be mounted on a UAV. But at the same time, we also did that, Bastian did that, as he was explaining this morning, a characterization of other instrument used for the level 2C product. And why this is important? Because one thing is knowing the nominal characteristic of the instrument, but another thing is really to understand each of the details of the instrument that can affect the measurement actually. And there are many. If we are talking about spectrometers, you have the nonlinearity, the dark current, so the noise of the instrument, but also other stuff related to the measurement, the outdoor measurement itself. For example, the diffuser and its response that sometimes can underestimate, overestimate the solar irradiance. And the same, these are for the spectrometer, but the same is also something that is affecting, for example, the PAM measurement or other devices measurement. Then also, when you are making a laboratory characterization and calibration, there are some differences. And this is also something that can affect the results and should be quantified in the uncertainty budget. So again, in this project we had also NPL involved, which was making a lot of characterization of the instrument in the lab, which was really useful to also understand the comparison between different methods of calibration. And why is interesting that and kind of important? Here is an example of the uncertainty sources that we have quantified for the flux. This is an example related to the flux, where we have also the uncertainty related to the calibration, then uncertainty related to each step of the processing, for example, correction for nonlinearity or cosine response error. But also some of them were not really, we were not able to calibrate and characterize because are something that maybe are related to temporal drift, which is something we don't know yet. And thank you. Okay. The point is that when you are able to characterize the uncertainty sources, then what you can do is also understand the contribution of the different sources on the signal itself. And this is something we did with some uncertainty propagation, which is, again, already part of the processing scheme. And here we can see that some of the systematic error maybe can be more important than others. So yes, basically, just to summarize this part, regarding the instrument and the laboratory, it's really important to know the instrument capabilities in a way that then we can trust the measurement itself. And this is really important then to associate an uncertainty and really make a validation. And of course, this also needs to be propagated in the processing. And maybe some recommendation, very few. I mean, could be for each of these uncertainty sources, there could be different recommendation. But one, this was not really coming from this project, but from experience gained in the past. If we want to measure salinity chlorophyll fluorescence, basically one thing that is really key, and this I was also having some discussion these days, the shift in between the two channels looking up and down should not be there, otherwise you have problem overestimate or underestimate really significant. Another thing is the cosine receptor response that sometimes is not really considered. This is probably not really an issue for the fluorescence retrieval itself, but if you have an error in the response, you are sometimes underestimating or overestimating the incoming radiance. And if this is one of the products you want to validate, then this is can be problematic, or at least you need to know that to quantify the uncertainty so that when you are trying to compare, you know that this could be coming from this aspect. And last but not least, in this laboratory calibration, we also found some differences in absolute radiance, which at the end we found to be related to some mistake in the calibration itself. So in this case, for example, the people that was doing the calibration was not used with this field of view, which was larger than expected. So they were putting 2 centimeters farther than expected. And this was already creating a 20% error. And basically, if you have a 20% absolute error, you can expect to have the same in fluorescence, because basically fluorescence is directly derived by the reflected radiance. So if you're out there, basically the same amount is translated into fluorescence. Okay, and then from the laboratory to the field. So what is really important here, as also Alex was pointing out during his presentation, is the assumption of the measurement. So in the case of the flux, which is an hemispherical conical system, you have the channel looking up, which has a 180-degree field of view, and the other one with a fixed field of view. But the main assumption of this measurement is that the light that we are measuring with the cosine is the same that is reaching the target. And as soon as this assumption is not valid, then you have error in the measurement. And I was trying to basically here listing maybe 3 main source of error related to breaking this assumption. In one case is if the cosine receptor basically are shaded during the day, whilst is not the same for the channel looking down, then you have an error because you have an underestimation on the incoming radiance, and this is affecting the measurement. And this, you can try to do your best, but sometimes this is the same cosine in Finland over winter, and sometimes it happens. So this is also something that you need to know in terms of the site. Or another thing is if you're setting up maybe in the wrong way the instrument, sometimes you are measuring just the shadow, whilst the cosine is looking at the clear sky. And this, of course, is creating some problem again in the measurement. So all these kind of things needs to be considered in advance before the installation. And one other point is the distance from the sensor to the canopy, because if you have shadow here, basically is something really visible, but sometimes, even if the setup is nice, you are far from the measurement, and so you have a sort of perturbation, atmospheric perturbation in the oxygen bands, because basically then what we are doing is retrieving fluorescence using the information in the oxygen band, but then if this is changing according to the distance, this is affecting the results. And another source of error, if you are installing not leveled the cosine, so basically the channel looking up, what you can do is having an overestimation or underestimation depending on the sense your sensor is tilted. Also, the selection of the proper location is kind of important because yeah, this also depends a bit on the goal of the measurement. So if you want to compare with satellite, you probably need to find a spot which is representative enough, but also is the case if you want to combine, for example, point measurement versus GPP fluxes. Also there you need to try to set up properly the instrument. And what we did also in this project was also try to define some of the protocol for measuring the higher level product, so what was discussed right before lunch. And in this case, the idea was really to start from the palm measurement, so leaf level, then upscale to canopy level, and this is basically where we arrived, and the idea is then now to move forward and try to also spatialize this information. As was already pointed out, is something really new. There are a lot of uncertainties, and mainly coming from the ecological differences, the ecosystem differences. And in this case, for example, one of the conclusions that will be part of this report is that timing is important, as Bastian was saying, so it's something that is a quick measurement, so you cannot really do the day after or also maybe in the afternoon. Then you need to try to be representative of the measurement, and this means that you need to make, for example, long transect, which sometimes is also not too easy if you are not measuring some fields which are, for example, monoculture is easier than other type of vegetation. And also, yeah, one thing is that what is under development is this match-up between palm measurement and flux measurement, and in this regard, having time series of that would be really helpful. Then regarding the spatial sampling here, so we have talked about the flux measurement, so point measurement. The idea of having a flying system was also to try to capture the spatial variability. In this case, again, is a point spectrometer, so we have a limited field of view, but we are trying to put this on a UAV here, and then we used also this platform which was attached to the helicopter, and we put the same instrument looking down. The idea was to go higher in order to have a bigger footprint that eventually could be comparable with the flex pixel when in orbit. There are some considerations to be made when you are trying to do this kind of measurement. Again, the atmospheric perturbation, and in this case we are always trying to fly lower than 15 meters with the UAV in a way that we do not have or significant influence on the retrieval. But another thing is the proper footprint projection, because as soon as the instrument is fixed, you know that the measurement is coming from this area, whilst if you have something flying, you really need to locate properly the footprint of the measurement, and this is something that you need to develop specific tools in terms of data processing. Temporal uncertainty, as Roberto was saying, basically the limitation of the UAV is that it cannot fly forever, so you need to focus maybe in 20 minutes, so how the battery are lasting typically. And so you need to also plan this in advance, thinking on this aspect. And this is basically linked also to the logistical aspect at the end, so basically the covered area, the flight duration, and so on. Then the other part is the data processing, so really converting the data from level 0, so the raw data, to radiance, to reflectance and fluorescence. This slide I was already showing is basically what we are doing with the flux and the air flux. But consider that each of these steps also has an associated uncertainty coming from the calibration and characterization. And on top of that, if you have a flying instrument, basically, yeah, this is the projection I was referring before. So you also need to quantify the accuracy of this location. These points that you can see, these polygons are basically the projected area of the data collected with the helipod, so the helicopter sensor. And yeah, this is relevant in order that to be sure that you are trying to measure the field or the area that you are really, which is the objective of your measurement. And one of the last points here of this contribution is also the SIF retrieval. And basically, well, I was reporting here some of the retrieval method published in the past. Is something that is coming from the 75, so is a while ago. And then there were a lot of methods, also now many more. But what you need to know every time that you are applying a retrieval method is the assumption. Because sometimes the assumption is not matched, and so this is, again, a source of error or higher uncertainty. In this project, what we did was to select 4 retrieval methods. So IFLD, spectral fitting methods, a single band, spectral fitting giving the full spectrum, and the BSF, which is a kind of newer retrieval method published by Christian van der Tol. And the good thing of this method is basically that is automatically compensating for the atmospheric reabsorption. So basically something that you can apply if you have the flux installed higher, at higher distance from the tower, from the surface. And what we did was basically try to apply this method and also check how good they were agreeing in between them. And in this graph, basically you can see the scatter plot, and the area represents the mission requirement of FLEX. So what we wanted to have as results is that this is falling inside this area, because it means that the methods are agreeing with the very small uncertainty. Still, in some fields we could find a different behavior, but again falling beside or inside this area. And so we did that for the BSF versus spectral fitting, and also the same for the full spectrum retrieval. And I think this is the last slide before going back to Roberto, which is also the importance of the quality flex. So sometimes the instrument which is running automatically in the field is saturating the signal, which means that basically the integration time is too high, and sometimes basically you reach the maximum possible value and you have these flat lines. In this case, the measurement is better not to use, because otherwise you are introducing this error. And what we are proposing also as quality flex, together with some threshold, also for in-SIF, are these measurements, so the dynamic range covered. So we are trying always to optimize the signal, but as you can see, sometimes there are clouds, so the signal is not perfectly matching the 80% of the dynamic range. One other thing is the solar zenith angle. So if the measurements are collected with the sun, which is very low, then the risk is that you are introducing error related to the response of the cosine. So we are also suggesting maybe to filter out the one collected with higher than 80 degrees solar zenith angle. And also another important thing is the stability of the illumination condition, which, I mean, for flex probably is not too important, because you can do the validation only in clear sky, but in order to be able also to use the data collected under diffuse condition, is important anyway to get a sort of information how stable the incoming radiance is during the measurement. And yeah, and I think this was the last slide of my part again. And now Roberto is talking on 5 minutes on the test that we did in this campaign to really also make the upscaling and the match up. Okay.
Okay, thank you. No, another point that I would like to underline is that before making the validation, I think that everybody should know the requirement that are written in the mission requirement document, because not all the variables present requirements. So basically, there are, for example, atmospheric characterization parameters that are not subject to direct requirements in the document, but other variables, like, for example, level 1C or fluorescence or reflectance, exhibit some requirements. And I encourage all the people before starting the validation to check the requirements that are defined. For example, for fluorescence, the integral of the full spectrum should be estimated with an accuracy that is less than 10%, with an error less than 10%, sorry. So this is something that is written in the mission requirement document and is important to read. And this is the same slide before, but just to show that we tested with real data different Calval tool that we developed. For example, the single point with a transfer function or the multiple points without transfer function. But I don't know, yesterday Giulia showed some detail in this context, so I think that we can also refer to the presentation of Giulia. And one point that I would like just to underline the philosophy. For example, let's go back on that. The single point with the transfer function. So we have the input data could be one instrument, one flux on the ground. Another input data is the Sentinel-2 at a 10 meter of spatial resolution that is useful for computing, for example, near V, and this Sentinel-2 should be collected closest as much possible to the flux data. Then we have the flex product, and then we have the coordinates, so the region of interest, and these are the inputs to run the Calval tool. And if let's assume that we have one single point and we need to scale at 300 meters of spatial resolution, because we can try to benefit from the in-SIF network and we cannot go at each site to make a spatial sampling. One idea could be to exploit a transfer function that is based on the knowledge of the near V. So basically you are measuring the fluorescence at the tower. You know the value of the near V at the tower and the value of the near V in the region of interest. You know the Sentinel-2 uncertainty because it's been computed with the COMET tool that has been explained by Peter last time, and you extrapolate in a large region the value of the fluorescence, and then you make the matchup. Instead, if we work in the multiple points, as defined before, we did a different test before concluding that the genetic algorithm is important. And at the end, another point that I forgot to say before, that after positioning the points, the tool can also allow to identify the starting point. So when you plan your flight scheme, you know how you have to move in the area according a pattern that minimizes the time needed to sample all the points. And this is basically the result. For example, just to concentrate on the left side, we have the iPlant SIF, because we tested in this famous FRM for fluo campaign, and we have the airborne data that has been resampled at 100 and 300 meters of spatial resolution to mimic FLEX. And on the x-axis, we have the different fluxes that we accommodated on the ground. And this is a direct validation using only one point. But if you see, always checking the left plot, if you applied the transfer function, for example, by using near V, this is the result. And basically, what we are concluding is that although we are aware that it's not the best solution having one point to compare with 1 kilometer, but the exploitation of this kind of strategy allows to improve the validation. So we are suggesting to exploit this method. Instead, when we are working with multiple points, we can do different convolution by using PSF or by using interpolation method, and then we can directly make the comparison between the FLEX measurement with the higher flux data. So I think that this is the last slide, and just to summarize. So basically, as we know now, that FLEX mission is offering a wide range of products. So we are delivering level 1C data, level 1B, level 1C, and a lot of level 2A. Level 2A encompass from reflectance up to FQE or PS1 and PS2. So we are covering a wide range, and it's impossible to find the same validation strategy that can be adapted for the different products. So basically, what we have developed in this year is to define different strategies for validation of the different product in different way. Then in this short talk, the idea is to start a discussion with everybody about some initial protocols and guidelines based on our experience, but if we receive feedback and if we can interact, we can of course improve everything. So what we showed before is something that we are proposing for the validation of FLEX, but everything is can be improved. So one important thing is that the field measurement should have a traceability, so an associated uncertainty, otherwise it's very difficult to make the comparison. And basically what we are thinking is that maybe according also the input data that we have, maybe we can classify as green data if we have uncertainty, as orange data if we don't have. So maybe we can consider in a different way. This is something that we can evaluate. And then what we show that we tested by using simulated data and by using real data, and it seems that they are working, so everything can be improved, but currently we are confident to be at least on the right track. And we also provided a lot of validation documentations that I hope can be very useful for getting ready in the E1 phase and start also an interaction for the validation in commissioning. That's all from our side, and thanks again.
Okay, thank you very much, Roberto, Tommaso. This, I think, was a deep dive. Some elements have been presented more than once in this workshop, but repetita juvant sometimes. And some were introduced completely new. Any immediate questions on the slides presented? Bearing in mind, in particular, if you're not here tomorrow, let's say, and you want to provide your inputs, otherwise there is really 2 hours tomorrow for that. Please, Jan-Griel.
Okay, yeah, I'm very impressed with very comprehensive Kelvin efforts. My only concern is your transfer function. So you believe Sentinel reflectance is right. But when I did my sabbatical at Carnegie in 2017, I asked Greg Asner, how do you validate reflectance? He said, don't do it, because it is too complicated. And over the several years, my group tried to evaluate the Sentinel reflectance. And then what we found is that it is very complex. It is based on our drone-based spatial map of the reflectance. When you compare, for example, because you use NIRV, then you have to make sure your NIR reflectance is right. But if they are flattened, then that information will be transferred into your 300 meter. So that is one point. And the other point is that the relationship between SIF and NIRV are very different between SIF and SIF4. So that means you have to have very, very careful, high, very precise land color map, crop time map within 300 by 300 meter. So just 2 comments.
Yes, I would like to complement this because I think this is a very important point. And I'm not a big fan of these transfer functions because, as you say, they can add potentially uncertainty. And let's assume in a year from now or 2 years from now, we have 1 year or 1.5 years of data. We have algorithm version 1, version 2, we are comparing. And version 1 is better if we include transfer functions. Version 2 is worse, but it's very good if we are comparing it without transfer functions. So what I'm missing, so I support this point, and what I also am a bit missing, and what we should discuss is the metric according to which we are deciding which algorithm or which product is superior to the other one. Because that will be the challenge. Also in the commissioning phase, we will play around with the algorithm, we will make changes, we will have to make changes, because we see some things we don't like. But then at some point we have to make a decision whether we apply an innovation to the product or not. And the metric according to which we are deciding, I haven't heard much. It's nice to see these efforts and how we generate some sort of independent validation data. But then the second step is, okay, what do we do if we have 10, 15, 20 stations? If we do the matchups, if we are comparing, but what means better? Is it better correlation? It is a smaller RMS? Is it a reduced bias? In 5 out of 10 stations or 8 out of 10 stations in different biomes, or are we happy if we are only improving in one biome? So this part I think has not been really discussed during the workshop, and maybe this is something for tomorrow. And then maybe one last comment. We are focusing a lot about spatial variability and spatial matching. And I had the same discussions with the SMOS 20 or 15 years ago. Now, everyone forgets about it, and we are only looking at time series. So,
we are really looking at the time series after 10 years, and we know our stations. The reference sites are well characterized, spatial variability is understood. We don't care anymore. But temporal stability, you want to have the same station operating for a long time. You don't want to have someone saying, okay, the station is no longer there because the PI retired, or it was moved, or it was recalibrated. No, this needs to be at least traceable, but look at temporal stability for your measurement. I think it's much more important than the spatial issue in the long term, but probably provocative.
Any further comments?
I just can't resist again ask. I didn't really grasp the scaling from the leaf to the flocks. That was very little to, I only saw something like scaling through scope. If this is the case, then you have a chicken egg problem. There is a lot of scope in flex products. There will be scope as well in a validation. And yeah, this is something we already elaborated earlier that needs quite, especially for those products which will be at the leaf level, of course not at the canopy level.
If I could quickly comment on that, I think this part probably is something that is still under development. So I think that what we arrive to higher product and higher testing to spatially upscale, whilst this level 2C is still under definition. I think here the point is that we're really now still testing this matchup in between leaf and canopy with the hyperspectral sensor and inversion of scope. And this is something that maybe can also be a point for discussion tomorrow.
I think that the scope was originally designed for larger pixels, not for such a small footprints you have in a flux. And that's my point as well. The heterogeneity on a higher detail is something scope doesn't reproduce. Maybe Christian can say something about.
Maybe I can first say something about, to Zbigniew and also to Matthias. I mean, we use or we do something pretty new. Nobody has done before. So of course there can be uncertainty in the let's say reflectance data of Sentinel-2, but Sentinel-2 is also validated. So we have some trust that we can use NIRV, and for example we use L1C Sentinel-2 to exclude, for example, the uncertainty that is coming with the atmospheric correction, for example. Regarding the scope, yes, it's true. We use scope, and also in the processors we use scope, but as I said before, we do that for the first time. We come up with the first idea. We need to do anything at the moment, so we have to start with something. If you have better ideas, just come to us. We can talk about everything and we can try to include it. But yeah, it's not perfect at the moment.
I just want to point out that, I mean, you've thought about this CalVal plan very carefully, and you have actually 3 components, and the third component being the satellite intercomparison. And so that kind of takes care of the upscaling problem, I think. It gives you the temporal stability. You have multiple satellites to work with. So I feel like maybe you've thought about this a little bit, and you have a pretty good plan, as far as I can tell.
Just want to make a comment, an additional comment on the upscaling. When you look at what the reflectance community is validating, they're validating over a homogeneous area, at least for their area of interest. What you're trying to do there is to validate over a non-homogeneous area. And that's a much bigger challenge that even the reflectance community is not tackling. And fluorescence obviously has additional difficulties. So I think trying to validate over non-homogeneous areas, trying to upscale over those is probably a too big a step. And it probably would be better to try to focus, at least initially, on large homogeneous areas. Obviously, there are not many available, but the problems are really big with that upscaling.
Okay, thank you for your comment. I think the idea is not really to try to validate starting from non-homogeneous targets, because the analysis that Roberto was showing about, for example, the characterization of the sites as main aim to identify the most homogeneous sites, because we would like to start with the easiest condition. But the point is that often for reflectances, you can use invariant targets like desert or any kind of surfaces that have very low variability. But for fluorescence, we know that we need to have some variability in the vegetation cover, because, okay, we can check if over non-vegetated targets the fluorescence is very low, but to have a proper validation we need to have a range of different emissions, and comparing the coefficients of variation of sites that are usually used for reflectance and the one that we are evaluating for fluorescence, the coefficients of variation increase a lot, because as soon as you have some vegetated cover, the coefficients of variation increase. So this is the first point. And the second, we evaluated different transfer functions, and we also have doubts about using that, but at the moment was the only way we think we can at least try to characterize the heterogeneity. And we use this also to include some spatial uncertainty in the estimates, because another issue is that, for example, for reflectance, you can use high resolution spatial data that at least measure the same quantities, but for fluorescence, we are aiming to validate the highest resolution ever satellite. So we have to find somehow some function that can help us at least to understand if we can try to characterize better the variability. And this is why we are keeping open all the options, so using just single points. Maybe we realize that we really need to have a high resolution map from the airborne platform, for example, to be sure that we have a good characterization. And maybe you were not there yesterday, but we saw that we test different transfer function at the moment based on simulated data and the campaign data of this summer. NRV and the NRV squared times red reflectance are the ones that are performing better, but we test several. So we are open to improve the methods or change the transfer function if we realize that with real data they are not working so well. So even if you have a suggestion on how to tackle these issues, you are very welcome. Thank you.
I think we...
A small point to add. So thank you very much actually for having a consistent way to evaluate. We have a site that is not consistently homogeneous. So it's prairie, but it changes. And so maybe we did, it's good to know, and I should do the whole seasonal evaluation to know when it falls within.
This is a very good point, because we were evaluating the coefficients of variation over the season. So we know that you have also to be very careful about the periods when you can use one side compared to another one. So yeah, thank you for the addition, Peter.
So honestly, I think we... Yeah. No, go ahead, Alberto.
Yeah, just a practical comment. Thanks for this lots of details. I feel like 3 or 4 pages of notes. And then I was hoping, of course, this will be circulated. And so my question is then now for potential site PIs that don't want to go on board and have the vlogs and maybe think of some kind of drone-based scheme to participate in and cooperate with this. So will there be in this collaborative platform now this sort of guidelines, instructions, how you want the sensors to be mounted, and what will all these kind of details for the sampling of the drone flights be also shared there for people. And another thing is that I see this is, as you say, and I think that's the way to go. We start from step one and we keep improving things. So I guess it will be very important also in this platform to just keep open two ways share of information that, look, and now we have tried like this, it works better, and maybe others can start adapting it. But now, just a comment if you want to comment how we should, like PIs, so what we should do if we want to go on board.
Yeah, thanks for the question. So for the protocols, basically the idea, the goal of this project is really to provide this protocol. Not sure if this will be part of the platform.
For the how, I can comment. We're putting in place a sort of web page, but it's a very interactive web page which will be dedicated to not just collecting information from you and from the validation teams on the status of the activities, reporting the specifications of the sites, but also to exchanging information from ESA to the validation teams, including all the protocols, the updated documentation, the updated ATBDs. This will be this famous Confluence page, which is in the end a web page. Tomorrow there will be some screenshots of how it will look like, and it's an incredibly easy tool to exchange information and collaborate. So removing mailing lists and thousands of email exchange from the process, but just collaboratively editing web pages basically. And so this will very likely be the tool of choice also for distributing this kind of up-to-date documentation. I would suggest that we wrap up the discussion for today and we move to the next two presentations, and that we restart tomorrow, I think, based on these points. My feeling is that from many of this conversation would, let's say, hint at the fact that we need some sort of golden data set and some golden metrics to use as a benchmark for our validation exercise. How to define these? I think pre-flight is almost impossible, and I think it's a process that we have to see as we move on in the commissioning phase and in the early validation. But some of the elements, let's say, linked to the amount of multi-scale characterization, linked to the amount of let's say confidence that you have in the in situ measurements and in the let's say degree of homogeneity and stability, which is extremely difficult to achieve and to find actually in any of these sites, would gives me the impression that we could go in this direction. But let's restart the discussion from here tomorrow. And now I would like to give back the floor to Tommaso, basically most speaking time in the conference. Thank you for your availability to dig again into INSIF, because in the end, I think that there are, like Mikkel was bringing up, there are really two elements. One is on the characterization side, one is on the scaling side. On the characterization side, I think that we can afford to use some metrics which we know are not one-to-one to what we are looking at, to SIF, because if they would be, we would have already, let's say, what we are looking for in FLEX. On the scaling, I think it's a different story. But on the characterization of the site, I think this is something that we can do, and INSIF is providing us with access to a number of sites so easily and so large, which I think it's incredibly low-hanging fruit that we cannot miss. Tommaso, please.
Yes, so, well, easily, let's see, but yeah, we are trying to do that. I'm sorry to be again here, but yeah, I was saying in Tuesday that we expected to have a demo, which was supposed to be a live demo. Unfortunately, Thomas from Brockman is sick, so the idea was that Powell was taking over, but Powell this morning woke up sick, so now it's me and Andreas. And so the idea is that, yeah, the introduction to the network, this was already done. Maybe instead of making a demo of the network, the idea was also to show a bit better the idea of this movable calibration unit, which we think is really key for keeping the cross-calibration within the network. This we already know, so the idea is really to develop this network, collecting data, making them available to the community. The focus is fluorescence, of course, can be used for validation of Flex, but really wants to be something to increase the understanding of a terrestrial ecosystem. I mean, this was already discussed in the last days, and I think we've seen, especially yesterday morning, a lot of presentation really going into how to use data for better data modeling, or also investigating better the relationship between vegetation indices, fluorescence, and, for example, GPP. Still a lot of stuff to do, but I think was really cool to see that really the presentation were focusing on this kind of unlinear relationship, which is really the focus now. But this was already discussed. Also, this paper were already shown. Also, the flux, I think now we have enough. And so the idea is that really in this SIF, the idea is really to ingest data from all over the place where the flux owner wants to share the data. And I think the good thing is that this is basically the distribution of where the flux were measuring in the last 3 years. So we have seen a lot of them. Of course, the point is that sometimes some instruments are not really installed permanently because they're used for spot campaigns. And this is also something we will face when there will be SIF on place. Not everyone wants to leave the flux installed for 10 years. Maybe some of them, yes, but not everywhere. Again, this was about the testing phase, so we are testing the network on 10 system at the moment. I've got a lot of positive feedback, so I really hope that during this workshop, so I really hope we can expand the number of the unit in this month before the end of the official end of the project, so the official day of publication of this SIF, because so far is a beta version, not openly accessible yet. And again, one of the points again to stress is about the data policy. So everything that we did was shaping the terms and conditions based on a survey that we made publicly available last summer, and we shaped these terms and conditions. Again, I think we are pretty at good stage, and I think we are now close to release the terms and conditions. What I was not talking about last time is that as soon as you are providing the data, what you need to do is also filling a pretty simple table where there are the metadata of the site, which are then the ones that are reported, part of them reported in the website as well. But this is really key to also, for example, make the people aware if there is another, if the site is also belonging to other network, and also the tower height, the tower distance, because all these kind of details, as we have seen in the previous presentation, can make the difference on the measurement. And so this is why we are asking to give this information. And again, this is what we discussed last time already. The importance of the data citation of the data which will be available in SIF. And again, I would stress the importance of encouraging the people that are using the data to get in contact with the flux owner and the principal investigator of the site in general. Because again, the hyperspectral measurement or SIF measurement, as we have seen in these days, it's a good piece of the story. So if you have this alone, unless you just want to make maybe pure validation, otherwise if you really want to try to understand better the processes, you really need to have other information, and this you can only get being in contact with the principal investigator. And so here maybe I can leave the floor to Andreas, which is carrying the MOX. And yeah.
Thank you, Tommaso. Hello, everyone. This morning I learned I will give you an introduction to the mobile calibration box MOX, which I have here on the back. And the idea was to show it, but since everyone is so far away, I will just put it here and then take you to a trip to a calibration effort. Is movable, yes, but also it's quite heavy. So. The MOX is calibrated in the lab against a calibrated source, and then 2 spectrometers inside store the calibration coefficients. We adopted the system of having 2 independent spectrometers here, like in the FLOX, that have overlapping wavelength range in order to make sure that the calibration is really valid over time. Because as long as both spectrometers, which have individual optical paths, show the same values, we can be kind of certain that the calibration is still fixed, because it's quite unlikely that both spectrometers drift in the same way, because it's completely different types of spectrometers. Let's go to Tuscany. Last year, Grosseto campaign, FRM for Fluo. And after 15 hours of driving south, we arrived with a car in Tuscany. Pretty nice site, super nice sunshine, much better than the, at this days, gray Germany. And we go to the field where is installed a FLOX instrument. It's hidden here below the solar panels to keep them in the shade so they don't overheat too bad. And they are looking at, I think that was small tomato plants. And our aim was to put the calibration unit there and calibrate this MOX in the field, this FLOX in the field. So what we do is we get on the top of the tower and go to these cosine receptors which are installed here. And unfortunately, and this we could not solve by design, they have to be removed in order to be inserted into the integrating sphere of the MOX. So you climb up, unscrew them here, maybe make a picture to prove that they were clean before calibration. And then you put the same, like the downward welling optics of the FLOX instrument into the MOX here. Is lots of cables and fiber optics, so I have a few close-ups to show you how this actually looks like. So we have the integrating sphere here protected below the case of the instrument, and there is, you can see here, 2 optical fibers entering. These are from the reference spectrometers inside of the system. Then you have 2 receptors for the cosine receptors, like they can be put in here, and then 2 for the downward-looking fibers. And on the left side, you see, it's not only integrating sphere, which has a halogen lamp inside, it's also a wavelength calibration lamp, which has decent peaks over the whole spectrum, where we can do a wavelength calibration. And typically, while the lamp of the halogen source is warming up, we can put here the 2 downwelling fibers in order to collect wavelengths calibration data, because this lamp is hot much faster. And then, while all fibers are inserted, it looks like this. Here we make a test calibration, so the cosine receptors are without the fiber, but they're inserted here. It's actually pretty nice to see. And then the MOX will, during the calibration, guide you via the display through the things you have to do. So insert the fibers, wait for 10 minutes to warm up the MOX and the system that is being calibrated, insert all the fibers. Then when everything is warm and the light source is stable, it gives you a note. And then you have to like switch or reset the instrument that you want to calibrate in order to have a new file, and close the MOX, because you can see here is a small opening that is shaded, and we want to have absolutely no light inserting in the instrument during the calibration to make sure it's really only the calibration source that the instrument sees. So it's closed, and then for about 10 minutes there is samples collected to have lots and averages and ensure everything is stable. And then the calibration is basically over. Actually, the MOX is afterwards shutting down the wavelength, the integrating sphere lamp, in order to collect dark currents. So we also know the dark currents of the spectrometers that are connected. So there is a little bit of run over time, but that's it. And the field calibration can take maybe 30 minutes. So it's relatively quick and easy to operate, and even runs from battery. So these small, like 1 kilogram batteries last for 2 or 3 calibration, actually depending on the temperature of the field site, because if it's very hot, the system has to cool a lot. And we can not only calibrate towers, but we can also calibrate here the airflow system connected to the drone. That was done, and in this special campaign, we even calibrated the systems that were installed into the helipod that was slung below the helicopter. And this way we could really calibrate all the spectrometers at the campaign within, let's say, 2.5 days, because we had to drive a lot between the different places. And I think that's it about the practical use of the MOX. Many thanks for listening.
Yes, and I think one also additional part regarding the MOX is that we have made the characterization of it in order together with NPL, in order that together with the calibration file we are providing also the uncertainty of the calibration, which then is used to propagate up to the other product level of the flux. Then I have a slide from Thomas, which I'll try to explain. So, but the main concept here is that we have the data, which can be manually or automatically uploaded in an FTP server, which as soon as the data provider wants to be part of the instrument of the network, we can provide the link to. And this can be done or automatically, because the Flux now has a unit that enables data transmission via Wi-Fi to this FTP, or manually. Basically, you just need to put the data on the FTP, and this is basically triggering then the processing. Then basically the data from the FTP are then ingested in the database, and there is where the processing is starting. So the interface basically for the data provider will be this FTP address where to put the data. And then, there is this processing running, including uncertainty, and then you will have this user interface that you have already seen, and that I think I was put, these things are too detailed for me. But this is the landing page I was already showing how it looks like. And here you can see basically all the information that are requested in this table. The metadata information are reported here. So basically the idea is that if someone is browsing in this web page, can really get an information of the site, the contact of the responsible person which might want to contact, and all this other information, including one picture of the instrument, how the installation looks like, and together with some preview of the data. These are data which are automatically streamed from Brazil in this case. And then just before closing, the data that you can download, this is something that is still under implementation, but we know the format of the data, so what you would expect once you are getting the data. This will be both CSV file and associated CSV file with uncertainties for level 1, so radiance and irradiance, reflectance. And in principle, the idea is that we are providing data which are already filtered, unless the user is feeling so brave to have everything. But there will be this possibility to get already filtered data after quality flags. And at the same time, we also have a sort of summary file, which is including the synthetic informations like the vegetation indices, so not the spectrally resolved information, but the time resolved information like day of the year, solar zenith angle, fluorescence, some of the vegetation indices, which also we got as a feedback from the survey. So we are including basically the vegetation indices which were coming out from the survey. And together with this radiance file and this CSV file, also basically we will have some netcdf file which will already contain also all the information in terms of uncertainties, because what we will provide in terms of CSV file will be the full uncertainty, but if you then have the netcdf, you can see that the file is structured like that. So you will have all the different type of uncertainty, systematic, random, and so on. And this is something that can be really used for further retrieval of other variables. And yeah, that's it. I'm sorry we couldn't make with the demo, but I hope that you will get some news soon, and we will have this available as soon as possible. Thank you.
Thank you very much. Any urgent questions for Tommaso? Yeah, Uwe?
Thanks. And I like the mocks a lot, so I'm really happy to have this mocks seen in reality now here. If I now think about how this will be put into action, I picture that the mocks will travel a lot, from FLOX system to FLOX system, from the one tower in South America to a tower in Northern Europe. How many FLOXes are there, or what are the logistics to actually ship the FLOX around that all FLOX, or how to ship the mocks around that all FLOX systems are properly calibrated?
Yeah, this is something, thanks for the question, it's something we are facing at the moment. So we are trying to make a mocks plan, try to really understand where this could go and when, because as you say, yeah, sometimes needs to go pretty far. And this is something still under this discussion also with ESA, what would be the way to properly ensure that the instrument is covering all these other places. Also, maybe one will not be enough at one point, so that's something that we are considering with ESA. We have some idea, not a final.
And clearly here we will have to prioritize based also on the elements we were discussing before, right? So both in terms of let's say sites instrumented by certain fluxes which are more urgently relevant for the initial assessment and validation, and also in perspective of long-term time series which are, let's say, the most valuable, right? So we will have to prioritize and build a strategy accordingly. But yeah. Okay, I see that many of you have already, let's say, grabbed a coffee or spontaneously so in the interest of time, and also because we have our next speakers who need to take a train. I would suggest that we move to the last presentation, demonstration of today on the collaborative platform by Terra 2 straight away. And after that we will have time for the final coffee and post the discussion. So please.
I need to set this up. Okay. All right. Good afternoon again. So I'm Simone Vaccari from Terra 2, and I will be presenting the demonstration of the FLEX collaborative platform. So I'm going to structure this presentation with first an overview of the web portal, the key component and the forum of the collaborative platform, and then we'll get into a more technical session with some execution of notebooks. Just before we start, you see here the URL is under Terra 2, but as Pedro mentioned, so currently we are doing a DNS change, so this will migrate into the ESA map. So the collaborative platform will be accessible directly from the ESA map. And actually, I think they're actually starting to do some migration right now. So we just experienced some issues literally like 5 minutes ago. So I hope everything is fine. If not, we have some backup videos that I can show you, okay? So be patient. All right, so the platform is really meant to be a collaborative environment where to share knowledge and information among scientists and the whole community. On the top left hand side, you see the key components of the CP. So we have the catalog where the data, the EO products are accessible and can be discovered. We have the geo browser with a standard 3D globe where we can discover data, use search parameters to filter EO products. We have the apps where the applications and remote desktop can be directly accessible from the platform. Then the Git Flex repository is accessible directly so that users and developers can develop code and share code with colleagues. And then we have the drive where users can upload data into their own workspace and share as well with the community. I'll get back to each of these in a second, but the rest of the portal is really a community forum where articles and posts can be posted and be shared. So we have grouped some of these already in some categories that you can see here on the left-hand side panel, but also here in the center. So we have some categories that are really general for the community, some announcements around, for example, this workshop or some of the workshops that were held last week. I'm just going to browse some through a few of these. We have the help and support. This is really for helping users and developers to navigate through the platform, how to register. So there is an onboarding procedure that can support the users to register and use their workspaces. Of course, this post can be written by any registered user, so can be shared within the community. We have some more technical categories as well for helping users, providing some practical hands-on tutorials on how to, for example, discover data using the geo browser or using the catalog. How to interact as well with the in-SIF data, so field data set, how can be searched and used and imported into the platform itself. How to analyze Earth observation products, and how to develop algorithm, so writing code, but also how to package these algorithms so that they follow the standards and the OGC practices, so that this algorithm can be deployed and used by other scientists. We have a section for systematic processing, so the idea of a new Flex data coming into the catalog, and then a Calval tool or a QC tool starting directly automatically as the new data comes in. Okay, so I think that's about it in terms of the overall web portal. Now let's start looking at each of these components. So the catalog, this is really catalog having all the EO products divided and grouped into collections. For example, we have one L1C data, L1C synthetic product that was ingested into the catalog. Here we can see, so on the right-hand side we see the metadata, on the left-hand side we see the assets. So this maybe is not a really good example because it doesn't have much information, but let me get one Sentinel. Oh, sorry. So one Sentinel data, so on the right-hand side we see the metadata that describes that specific item, so that specific product, and on the left-hand side we see all the assets, and we see where it's located in the map. And we can also have some very basic filters for help the scientists and developers to search data on the catalog. Then we have the GeoBrowser. So this is the standard 3D globe where we can browse and visually inspect the EO product. In this panel you see the collections that are available in the catalog, so everything is linked up, obviously. So if I look back at this Flex product, I can see again where it's located. I can download the assets directly from here. And another feature, interesting feature, is that I can export. So say I've done my search and I want to export the IDs or the URLs of the data that was discovered, so that I can use them directly into a notebook or my own algorithms. And we're going to see an example of this in a second. On the right-hand side, you have the standard base layers and also external and additional data sets such as the flex sites. So vector data, raster data can be integrated into the GeoBrowser, and we have also the 3D, which is 3D visualization here working. So yeah, that's covering the GeoBrowser. Now on the apps. There you go. Okay, so we have this issue. So I'm going to switch now to the video. Sorry about this, but it's really okay. So the idea here is that we have yes. Maybe Pedro, if comes back, tell me again. And okay. So let me start again the video. Again, this is a change that is currently just happening right now on the DNS to integrate the platform into the ESA map. We notified them not to work on that this week, but hopefully, I guess something went wrong in the communication. Anyway, the idea is the user clicks on the apps and gets access to the web store that links and contains all the products that are available, so that the user can subscribe to these products, and once subscribed, it can launch them directly from the map, from the portal. At the moment, we have the Visual Studio Code product, the notebooks for Jupyter notebooks, Panoply, and QGIS remote desktop. But other remote desktop applications can be installed and added to this web store, so that user can work on them. So for the first, now we're moving into the notebooks analysis, which I wanted to show you live, but hopefully maybe it'll come back later. But anyway, so the first notebook, actually let's first have a recap. 1 second. I just wanted to give you what sort of notebooks we are going to look at. So this is the Git Flex repository. And I have 3 main notebooks that I wanted to show you. The first one is discovering your products from the GeoBrowser. We are going to do that with the Flex data, and then we're going to download that data into my workspace. And I'm going to open the netcdf file containing the data in Panoply. The second notebook is analysis and visualization. So we're going to look at search your products, in this case Sentinel-2, the entire 2024 time series of Sentinel-2 data. We're going to inspect metadata and visualize the assets in QGIS. And then we're going to do some feature extraction. So for one of the assets, we're going to take the MDVI as a simple example. We are going to build the time series of NDVI in a specific polygon. The third notebook wants to illustrate the case of the user wanted to upload a data set, in this case a Floris data, into the workspace and upload, import this data into a notebook and then show its content and print some graphs of the variables contained in the netcdf file. And I want to show you as well, we have in work in progress other 2 notebooks, but I don't think we have the videos. Well, I know that we don't have the videos for this. One is for interacting with InSIF data, so OpenEO API connection directly from the collaborative platform to the data that Tommaso and colleagues just presented. And the last one is downloading data not from the CP catalog, but from the map catalog, just to demonstrate that the CP is really connected with all these different and external platforms, okay? Right. Let me try again. Okay, now it's working, so I'm not going to do the video. Okay, I just accessed the marketplace, the web store. I'm going to open VS Code, and I'm going to run the first notebook. Okay, so I'm going to explain as I run through the cells. The first notebook is for visualizing searching some data in the GeoBrowser and then downloading into my workspace. And I'm going to do that with FLEX-L1C data. So the authentication you will see in each of the notebook is based on Flex, the identity management. So it links to this external identity management system that enables the user to log in directly with the Flex username and account. So there are no external authorizations that I need to take into account. Everything is dealt by the Flex identity management. So I logged in and I generate a token that allows me to connect with the GeoBrowser and the catalog. Let me close this so that we can see everything. Okay, now I want to search data, and the notebook asked me to provide a product ID. So back to the, let me undo this. So I want to search FLEX-L1C data. This is the result of my search. I can copy the ID of this Flex data, and then I go back to my notebook and I enter it here. And you see the stack, you see? Okay. The item is loaded into the notebook. So from here, actually, let me run the download, which takes a minute or so, and then I explain a little bit more. Okay, now it's downloading. So back to the item. So I loaded the item into my notebook, and here I can see the metadata of that Flex product. I can see it contains only one asset. I can see that it's a netcdf file and is stored in S3, in a S3 bucket. So what this download function does is connected with a signed URL. So with my token that I just generated, I get access to this URL that has my credential that allows me to connect to that specific S3 bucket, which allows me to download the data, okay? It's downloading the netcdf file. So meanwhile, I'm gonna open Panoply, so that once it's downloaded, I can open the data into Panoply. So back to my marketplace, I go on Panoply. This should be almost done. So you can see how I can really navigate through all of these different products, but they are all interlinked and to the user, to the registered user. Okay, the data has been downloaded into this My Downloads folder. So My Downloads, there you go. Here we have my netcdf file. And if I go back into Panoply, I navigate through My Downloads, the Flex data, and then the netcdf file can be opened. Just gonna open one as an example. Okay. Okay, so just to reiterate, there is a dedicated remote desktop that has been created that has Panoply pre-installed, and the same with QGIS. So every time I launch that, automatically launches Panoply and my remote desktop application, so I can do my analysis on Panoply in this example. Okay, that's about it for the first notebook. The second notebook, I'm gonna open it now. So we're running some time series analysis. So in this case, I authenticate as I did before. You can see here it links me to the Flex identity authentication page. And in this case, load query from file. So the idea here is I'm going to look for Sentinel-2 time series. So let me, I select my bounding box around this site. And search for Sentinel-2 data. Let me add the date. The entire 2024. Okay, and I'm gonna add as well clock over 5%, just to reduce a little bit the number of images. So we have 31 Sentinel-2 data selected in this, with these parameters. So what I want to do now, I can export not all the IDs, I can export the query I just used. So you can see that JSON file has been downloaded, and the idea is that I can. So this is the file that just downloaded into my Mac and my laptop, and I want to put that into my workspace in the CP. So I just drag and drop the search file that has the collection, the bounding box, and the time, and I can search info. So I'm telling the notebook, look at that file, it's got all the parameters, query the catalog with those parameters, and then 31 items have been found. Now let's have a look at the first, so the usual stack information where with all the metadata and all the assets for Sentinel-2 data, all the bands. I can plot an asset, in this case the true color overview. I can download, let me put the coastal, because it's a bit lighter and takes a little bit less time. I can download a single asset in my download folder, and I'm gonna open that in a second. First, I'm gonna do some time series analysis. So first, I'm loading all this data from the asset, from the items into a geodata frame, so that I can more easily handle them. And I can very simply and quickly plot a time series of one metadata attribute, in this case the cloud cover. So it searches for all the items, the cloud cover value, and then plots it on a time series. That's about the metadata. Now I want to go a little bit further and look at the assets. So as I mentioned before, selecting a polygon within my bounding box, and I'm gonna plot the NDVI. So selecting one asset, in this case NDVI, and for each of the items, so I will have for each of the 31 products, I'm using that polygon to extract NDVI values and make an average, and then plot it on my time series graph. Meanwhile, let's open QGIS and show you the coastal band I just downloaded. Go back to my marketplace. Okay, so a pod dedicated has been just launched, and you can see it's quite fast. And okay, now you see, okay. I go to my downloads, and this is the coastal band I just downloaded. So you can see how easy it is to download data on my CP, on my code product, and open directly without copy and paste. Like the workspace dedicated to the user is the same, obviously, so I can easily jump from one product to the other. Okay, that's about it for QGIS. I go back to the NDVI. Okay, so it should be almost done, and what I expect to see is a time series of NDVI values. There you go. Okay, third notebook. So the idea here was to upload an external data, so not looking into a catalog, but an external data, and in this case I'm using FLEX-Fluorescence data is a zip file, and it contains, well, let me do this. So I'm gonna drag and drop. I can do it directly as well on the drive from the web portal, but as well I can simply drag and drop it here in my downloads. This is 150 megabytes of zip file, which contains a net CDF of around 2 gigabytes of data, yeah, it contains I don't need to open it here. The upload is complete. Okay, so here I'm gonna look first. I'm gonna import this zipped file into my notebook, enter the path, yes, so I go, so this is the zip file just uploaded, I can copy the path, this is my input path, okay, and so I explore the zip content and what I'm interested in this case is this netcdf file, which is still loading, is about 2 gigabytes, yeah, 2 gigabytes and a half, and so I can, once unzipped, of course, I can open this data in Panoply, as you can see in the screenshot, and this in particular contains 2 groups, binned and unbinned information, having different resolutions, high resolution 1, high resolution 2, and low resolution, and what I'm going to do is looking at the variables contained in each group, and then I'm going to do some plotting. This is the IRSF spectrum on unbinned pixels. This is binned and unbinned data, and this is an example of different binnings on the ISRF sample index. Okay, so these are, I don't know how I'm doing with time, but I'm done basically. I just wanted to show you these 2 other notebooks that I mentioned before without needing to execute them. So Flux Data Network, so access via OpenEO. Again, the connection via OpenEO can be done directly from the collaborative platform with the credential that we've been given by Brockman, so we've been working closely with them and still are, actually. We can list the collections. You see the list of collections here in the notebook. This is still work in progress, and this will have to be updated. But this is the whole list of the collections at that point. We can select one and visualize the properties, the location, and any other attributes, the instruments and the dates and so on. And the last notebook I wanted to quickly show, it's very similar to the first notebook, so the idea of getting data from a catalog and downloading it, not in this case from the CP, but from the ESA map. So searching the collection using the ESA map catalog and selecting the idea I'm interested in and downloading one of the assets. And that's about it from my side. Thank you.
Maybe just one comment from my side to complement what Simone showed, because you saw that he was using level 1C from Flex. Of course, it's not a real data set, it's a simulated data set with the end-to-end, which was processed through the operational processor that is still under development. So if you have any other questions for Simone, please go ahead.
Yeah, 2 questions. What type and quantity of processing resources underlie this platform?
So this can be, I can show you the sort of, so for example, code server, I was running code server on 2 CPUs and 6 gigabytes of RAM. But there is the advanced, sorry, the advanced, the one I used was 3 CPUs and 13 gigabytes. This is just to show that they can be configured as needed really for the users, and we can have multiple instances having different resources.
Okay.
And yeah, more powerful. Yeah, so we can discuss them on a.
But these are planned to be typical setups?
These were the setup that for now that we're used to develop, but again, if more are needed, they can be configured. Exactly.
The second question concerns data download outside of the platform. Is the API open so you can directly mass download data? in the same...
The CP...
you sort of showed how you exported queries. Can you then download directly with this query?
Yeah, the query I downloaded was directly, so I just...
You don't have to go through the platform. That's the question.
No, exactly. Okay. No, exactly. So once you need to be registered on the Geo browser. Once you register and you can access the Geo browser, then you can run the search query and then download the query, download the IDs that are needed. Yeah.
Okay.
Okay.
Great.
I one question here. Can you share your own data product catalog through this platform, so it is accessible for other users?
The catalog, you mean?
I mean, I have my own products, imagine, and I want to share with other researchers.
Yeah. So if you have your own product, yeah, of course, there are some procedures to describe that data. If it's a EO product, I guess, or even like a field data, the idea is to describe this data using the spatial temporal asset catalog. So adding all the metadata that are needed to really describe that data and then upload them into the catalog. So that can be done. That's really the idea. Yeah. I don't know if Pedro wants to add.
Just to comment, show him, because I think you didn't show him, probably this is something that many users are interested, the drive factor.
Yes,
so
I forgot about those
You
two.
forgot to show the drive. So
yes.
if you have structured, like I was saying on Monday, we advise you to structure your results to put metadata. But I know that sometimes it could be cumbersome. You have also a drive. So your Google, it's like Google Drive, where you can put data, and then you can say sharing data with user A, B, and C, or with a bunch of users, or groups of users. So to respond to your question, yes, you just want to share data like this, you just drag and drop onto the drive. This is similar to Google Drive, but this is based on Nextcloud software. So it's a European version of it. Yes. Then the space is provided by the map of ESA, the multi-mission access platform. And currently we don't have any limitations, but let's see.
Yeah, sorry, I forgot actually to show you these 2 points. So let me close this. The Git and the drive. So the drive is really thought to be as similar to Google Drive space, where users can add files and data and have them privately in their own space, but also share them with the community. And the other one is the Git project, dedicated to Flex, so users can register and then write code, develop code, and work with other developers to improve and work on Flex data. Sorry about that.
Luis.
Thanks. This is a great effort to put together this platform. I assume that it will be fully documented, because I've seen that you're using very specific functions in the notebooks.
Yes. So the idea is really to have to really document. So these notebooks that we developed were for development purposes and to showcase the capabilities that a developer or a user can run inside the platform. But the idea is to share also these through some specific posts. So these, for example, how to use the Geo browser to run queries. You will have more on notebooks. Perform analysis on the CP. So, for example, like these are the function that you should run for this and this and that case. And it's really up to the users to use this space as a community forum and to post information and chat and reply on the posts to foster collaboration.
Yeah, and my second question is it enabled to have interactive actions? Like, for example, you were selecting a region of interest for doing the NDVI time series, but it was already hard-coded.
Yes. that was to simplify the notebook, but
Yeah, I guess.
we have another one that allows the user, in the notebook, it prints out a map, and then you select the polygon or with a widget, or put a point, and then gets the bounding box, and yeah.
Thanks,
sure.
because that's really useful, actually.
Yeah.
Thank you.
Thank you.
Maybe just one comment at the first question. We will also organize training sessions for the community. I think as soon as it's open, there will be training sessions or webinars that Radue will organize. Closer to the launch.
Yeah, two questions. One is a follow-up regarding accessing the data. So the FLEX data is intended to be public data. A few days ago, there was shown that the data is stored on an object store, S3-like.
Yeah.
And yeah, can I access it outside of the platform, maybe with a platform user from an external platform or service?
I can take that question. So as we said in the first day, the data it's accessed through the ESA map. So it's something, well, we don't have the link here, but it's a portal that is designed to access the data for all the Earth Explorers. So currently for Earth Care, for biomass, and the collaborative platform will be an element of that platform. And the data is stored there. So you will be able to download the data from there.
Yeah, and accessing the stack catalog from outside.
From that platform. The stack catalog will be on that platform, and the collaborative platform is an element on the ESA map that allows you to do all the operations that Simone showed.
So when I want to do a search on data or accessing the data to download it, I need to be inside the platform and work with the tools that are inside the platform, so the authentication works. But it's not possible to access that from the outside.
As far as I know, I don't think so.
Because, for example, with the CDSE, I could do that.
Pedro, go.
Just to clarify that point, the official distribution of data from those 3 missions is from the map. So if you want to get data and distribute it from the outside, officially go to the map. The IAM, the identity management of each user, it's linked. So if you are linked into the CP, you are also linked to the map. You have no problem. It's just the access point, the mission who is paying, is that the map is doing the download for the outside. When you are in the CP, you can access that same data and using the tools and the CPU and the resources that is in the CP. So if your question is, I want to download data, the entire record from FLEX, you go to the map service and you have the stack catalog and you have all those things and you have the same user, basically. If you want to work inside of the CP, you come to this environment. And here you have desktop tools, CPU, notebooks, and so on to work on it. But it's just a way that the mission to distribute data is assigned to the map, if I say that correctly.
No, but I think what you're after is an API that allows you to download the data even if you don't go to the platform.
So if you have the API, so this is sign URLs. So what you do, you have a stack catalog that you identify which are, and then you have APIs to do the signing of the URL. So you are able to download. He was doing this when he was showing the inside of the CP, when he was showing the Sentinel-2 being assessed. Each of those links was using a sign URL, so you don't need to put your password every time, and it covers that part. So yes, you are able to download multiple stuff.
A small follow-up for that interactive work with that. You explained that as an example with that Jupyter notebook, but it's an optical mission, so cloud cover is an issue of my area of interest, and a percentage does not help. I need to have a look if my site is covered or not before I do the clipping. Is there a way to do that interactively without building a notebook to check every image if there are clouds in my scene and I need to drop that data, then...
So, so if the data is in cloud optimized format, the COG format, it's possible to access specific chunks of data, not the entire product. But in terms of the cloud cover, I'm actually not sure whether you can access the cloud cover of each specific chunk. That maybe someone else from the audience know, because that's what you're talking about, right? So
yeah,
if your
that
area
would be one way to solve that issue. Another way would be having a coarse resolution preview where I can do it simply with low bandwidth when checking it.
Yeah.
So the normal way to do this is or you search it by metadata, as you're saying, a percentage of cloud cover that the ground segment has decided that chunk has, or you have a quick look. So currently in these synthetic products that we have for Flex, there's a quick look, but not very, let's say, good. We're having examples, we're doing as a demonstration and showing how to do that in Sentinel-2 and Sentinel-3. So you could have seen, and you saw it very quickly, but you saw it, the quick looks of Sentinel-2 there. So you would see on the map and you would select which they are interesting or not. This is the way that you have it. This all depends that the quick look needs to be something that comes out also from the PDGS, also of the chain of processing that is adding to the... And the question is, when we are just harvesting the metadata, we need to be, okay, let's hope that the PDGS gave us that quick look. In those scenarios that I mentioned the other day on Monday, where we, for specific actions, for specific studies, we ingest the data in the CP, we are doing, yes, some calibration and some quick look generation. This is the idea. But we don't have the mandate to ingest the full data set of Flex because we'll be replicating the entire collection. I think, and for information that I have, I think that the PDGS will create a quick looks, but this is something that we need to confirm.
Yeah, that's a feature request from my side. That will improve the work significantly.
Hi, thanks for the nice presentation. Well, I don't have experience working with these cloud platforms and everything, so maybe my question is a bit naive. You were mentioning about these catalogs, and you were showing here the example of Flex, Sentinel-2, and so on. Well, we have been hearing these days about the use of TropoSIF, for instance, for cross-validating with the FLEX-SIF, or we have been hearing about this Nmap and DESIS data. We can think about climatologic data or meteorological data from ECMWF and stuff like this. So there are existing data sets. My question is whether these data sets, these catalogs, will be already available in an automatic way, let's say, or we have to make a request to be accessible, or is it my responsibility to put them there? So how it works, this thing?
So at the moment I showed the this is the CP catalog for now, and that has been populated with some Sentinel data, some FLOX L1C data, some FLOX L2 products, some QC and CalVal results have been populated. So these were for testing and demonstrating the fact that we can populate the catalog. If there are other data, the Sentinel-3 as well, if there are other data, climate data and other data of CalVal tools that needs to be in the catalog, that can be done, and I guess the procedure for applying and then ingesting them in the catalog still need to be really fully finalized once everything else has been completed. But yes, so it's not a static catalog. It's not once it's done, okay, that's it. It can be updated, and I guess for some data such as Flex, it will be direct once they are available on map. They will be available here, but for others can be on a ad hoc as needed.
But an important point, sorry, just to clarify this, is that the specific catalog of FLEX is to be used to, let's say, to orphan collections, in the sense that if they are not being, if there is not a catalog already at the CDSC or at the map and so on, we are not going to replicate that catalog to maintain it. So if there are specific needs of specific collections that currently are not available in some other institutional endpoint, they can be added here. I would not favor, but this is something we can discuss in terms of sustainability, to replicate a service that's already being managed by the Copernicus data space ecosystem, for example, if they have a catalog of that data there. Because with the APIs, you can access them afterwards.
Yeah, exactly. My question maybe, again, is very naive because I'm not used to work on this kind of system. So, but yeah, thinking about this application of, okay, we want to cross-validate with TropoSIF. I imagine that we didn't plan this. Imagine we didn't plan this on the Calval tools and stuff like this. So it's a new idea that I come out with as a new user of the CP. And the question is, okay, how do I do this? Is it available? Do I have this? You mentioned this ID of this catalog that I can use. How do I know about this? Because here on this front page, I see these catalogs are available, but Tropomi is not here. So how do I do that? Do I have to do a request?
Some of this data can also be accessed via API from within your workspace. I guess we did work on a notebook that was connecting to ARONET dataset or a HyperNet dataset via API. So as long as the connection is configured, then you can directly get the data via API from your code, your Jupyter notebooks, so that you can literally work with your own application. You can use data that are on the CP catalog. Data that are on the map, data that is on a different API environment. So that's definitely been done.
Thank you very much to everybody. I think I'm sorry to abruptly close this session, but I think Pedro and Simone have a train to catch. So thanks a lot, Simone, for the demo, and thanks a lot for the audience. And I think if Marco agrees, we can close the day today, and we convene tomorrow at 9 a.m. sharp.
Yeah, Pedro and I need to leave tonight, but if you have any questions, please let us know. Happy to chat for sure. Thank you all.